In this video, I will go over various BigQuery concepts such as datasets, tables, and views. A dataset in BigQuery is located inside a Google Cloud Platform project. Datasets are used to store tables and views. In order to start importing data and working with BigQuery tables and views, a dataset needs to be defined first. There are three ways to create BigQuery datasets, either through the bqmake command from the command line, the datasets.insert REST API method, or through the BigQuery web dashboard. You must also have BigQuery.datasets.create permissions enabled for the project in use. Access controls can be applied to roles when accessing either BigQuery datasets or to a role accessing an entire Google Cloud Platform project, in which case all BigQuery datasets belonging to that project, including all tables and views within that dataset, would be accessible to the user role. So next we'll talk about some limitations. There are several limitations when creating BigQuery datasets. One of them is that when creating a dataset, the location of the data can be set, and this option cannot be changed once the dataset is created. As the number of datasets becomes large, so we're talking about thousands of datasets within a project, the performance of the BigQuery web dashboard begins to slow. As datasets contain large numbers of tables, so this could be tens of thousands, performance will also start to degrade. All the tables used for a query must all be within the same dataset for the query to work. Inserting data from US to Europe or Europe to US based datasets can cause a spike in error rates and latency. If copying a table, both the source and destination datasets must be in the same region, and exporting data from Google Analytics to BigQuery has some issues as well. So moving on, there's some considerations for creating BigQuery datasets. So for the naming, you want to have a unique name containing letters, numbers, and underscores up to 1024 characters. You can't start with a number or underscore. It can't contain spaces or special characters. So as I mentioned before, you also must have BigQuery.datasets.create permissions enabled for the project in use to create a BigQuery dataset. The BigQuery.data editor, BigQuery.data owner, BigQuery.user, and BigQuery.admin roles already have BigQuery.datasets.create permissions to them. So now let's talk about BigQuery tables. BigQuery tables are located within BigQuery datasets and are used to store data in rows and columns. Each row represents a single record of data. A table contains a schema which defines the column names and the types of data each column uses. This schema can either be manually entered or it can be auto-detected and populated by the first job that either loads data or queries the table. BigQuery table schemas can be updated either manually by updating the original schema or automatically by running a load or query job. BigQuery data performs better when it has no relational schema requirements. So one way you can preserve relational data previously located in multiple tables all in one table is to use nested columns where you can put all relational data into. So an example of this could be if you have a table that's referencing the types of cars. Instead of having to go to a different table, you could have a new column that is nested in a few rows, and basically it's going to contain information that you would get from that other table all in one table. So similar to datasets, BigQuery tables have limitations such as the name of the table must be unique within a dataset, only one table may be copied at a time through the web dashboard, only one table can be deleted at a time, and tables can only be exported to Google Cloud Storage. So now we'll talk about the table types. There are three types of BigQuery tables. These are native, external, and views. Native tables are the default type where tables are stored in BigQuery columnar storage. External tables are tables where the data is not native to BigQuery and is stored in places such as Google Cloud Storage, Google Drive, and Google Cloud Bigtables. Views are virtual tables and they get defined by running an SQL query on an existing table. The results of the query can then be saved as a view and other queries can be run against the saved view. Tables can be created in BigQuery either through the BigQuery web dashboard, bqmake, BigQuery command line tools, the tables.insert REST API method, by running a query and then saving it as a view, from a BigQuery client supported application, for example in Python, or by loading data from external sources such as Bigtables. So talking about table namings, we must have a unique name for each table within the dataset. Table names can contain letters, numbers, and underscores, and could be up to 1024 characters in length. BigQuery.tables.create permissions or writer access for the dataset is required for a role to be able to create a table in BigQuery. So finally, I'll talk about BigQuery virtual tables or views. As I mentioned, views are virtual tables and they get defined by running an SQL query on an existing table in BigQuery. BigQuery views must have unique names for each dataset similar to tables, along with the limitations of being 1024 characters or less in length and containing only underscores, letters, and numbers. BigQuery.tables.create permissions or writer access for the dataset is required for a role to be able to create a view in BigQuery. So now we'll talk about some limitations with views, and there are quite a few. The table data list JSON REST API method doesn't return data from a set of rows with views. If a view was defined using legacy SQL, standard SQL queries cannot be used on the view. And you're only allowed 1000 views per dataset. You cannot run a job to export data from a view. The schema of the view is based on the schema of the table that the view was created from, so that if the view is changed, the underlying schema won't be updated unless the whole view gets reloaded. It's not possible to change a legacy SQL view to a standard SQL view from the BigQuery web dashboard. And you can only have up to 16 levels of nesting for BigQuery views. So remember I was talking about nesting for the relational type issues, and we can only have 16 levels with BigQuery views. In this demo, I will describe the process of executing queries with BigQuery. There are two types of queries supported in BigQuery. These are the default interactive query, which are queries that get executed as soon as they are submitted, and batch queries, which are queued and started by BigQuery, generally in a few minutes but not more than 24 hours. Interactive queries do add up against the concurrent query limit of 50 concurrent queries and the daily destination table limit of 1000 updates for a table in a given day. You can start more queries at once using batch queries because they do not count towards the limit of 50 concurrent queries. In BigQuery, all the results returned from a query are saved to a table, and you can also overwrite or append to existing tables, or create a whole new permanent or temporary table to store query results. BigQuery queries can be started from the BigQuery web dashboard, the REST API, the Google Cloud SDK BQ command line tool, and various BigQuery client libraries for languages such as Python, Java, and Go. Other limits when using interactive and batch queries is that you can only have a query up to 256 kilobytes in size, and you can only have up to 1000 tables per query. So let's get started. Here I'm going to go into my BigQuery web dashboard, and I have a project that's available to public users called BigQuery-public-data. So this is a publicly available project that Google provides. Scrolling down, you can see I have various different data sets. I'm going to go to the USA underscore names data sets, which contains two tables. The USA underscore 1910 underscore 2013 table, which provides USA baby names between 1910 and 2013. And the USA underscore 1910 underscore current table, which contains baby names between 1910 and current. So what I'm going to be doing is I'm going to click the Compose Query button at the top here. I'm going to click on Show Options, and I'm going to uncheck Use Legacy SQL. I want to run an interactive query, so under Query Priority, I'll select Interactive. So remember, the interactive queries are going to run instantaneously. So now I'm going to copy a query in, and the query I'll be running will simply display how many times the name Mary comes up in the past table that contains the USA baby names between 1910 and current. And I'm going to be selecting the name Mary and just basically grouping by the number of times Mary comes up. I could also see at the bottom here that I have a green check mark, which means that my SQL query is properly validated and I don't have any errors. If I click on Run Query, this is going to execute the interactive query. And because it's interactive, it should execute right away. And I could see I get one row back with the name Mary, and the sum of all the instances of Mary is 3,745,873. So quite a few Mary names. It's quite a popular female name. So let's continue on. Next, I'm going to run a batch query. So I'll show you how to do that in the web dashboard, and then I'll also be doing it using the BQ command line tools. So I'm going to copy another query in. And what this query will be doing is, once again, I'll be querying that same dataset USA underscore names and using the same USA underscore 1910 underscore current table. And then I'm going to group by name, and I'm gonna order by names total, which is just the sum of all the total names. And I'll be basically picking the 10 most popular names in that time range between 1910 and current. And that's going to include both female and male names. So I could see that I get the check mark that my query is validated. I can make sure it's an interactive query. Now, if I do want to change this to batch, like I said, what I could do is I could simply click batch. And if I click on the question mark, it says interactive queries will start immediately. Queries with batch priorities have fewer quota restrictions, but may not execute for up to 24 hours. So this may be better if it's not so time critical and you want to run more concurrent queries. So let's try batch query. I'll pick batch and I'll click on run query. So what we could expect now is, depending on resources, it might take longer because the query gets submitted to BigQuery and then it could take longer to actually execute the query depending on available resources. Okay, continue. So we could see the query completed. It did take 98.4 seconds to complete, and it says it processed 88.4 megabytes. So quite a bit longer because it's a batch query, and we could see the names if we hide the options here. We see that James is number 1, John's number 2, Robert, Michael, William. We could go to the next 5. Mary's number 6, David's 7, Richard's 8, Joseph's 9, and Charles's 10. And we could see the frequency that the names occurred. Okay, so now I'm going to show you how to actually run a batch query using the Google SDK BQ command line tools. So I have a query here, BQ space query space dash dash batch, and then I'm going to put in quotation marks select name coalesce cast sum number as float. So I'm basically just summing all the different instances of the names as names total from BigQuery dash public dash data. So that's that project, USA names dataset dot USA underscore 1910 underscore current table. And then I have a closed bracket where gender is equal to F. So I'm searching for all female names in the year 2013 because I have and year equals 2013. I'm grouping by name and I'm ordering by the names total for the top 10 names. So what this query is going to do, it's actually going to display in a table format the top 10 female names in the US for babies in the year 2013. Okay, continue. So we could see it took 135 seconds, which is once again quite long. But that's because we specified the dash dash batch. If it was an interactive query, we wouldn't have the batch option and it would execute a lot quicker. And we could see the top 10 names for females in 2013 in the US, with Sophia being first, Emma, Olivia, and so on. And on the right, we have the total number of names from all states that were given to those babies. So that's it for running some basic queries in BigQuery. In this demo, I will describe how to load data into BigQuery. It is often possible to use BigQuery to query data without the need to load it. Examples of this are when using public, shared, or external datasets or Stackdriver log files. Otherwise, the first step to use queries with BigQuery is to load data into BigQuery. Data can be loaded from a number of sources including Google Cloud Storage, local machine files, Google Drive, Google Cloud Bigtable URIs, Google Cloud Dataflow, streaming inserts, and with DML statements that do bulk inserts. Currently, the loading of data from Google Drive is not quite yet supported. However, it's possible to query Google Drive data by the use of an external table. A schema needs to be specified when loading a table into BigQuery and can either be manually specified or automatically detected from the source data. You can either add data to an existing table or create a completely new table when loading new data in. The default format of loadable data in BigQuery is CSV. The acceptable formats of loadable data include CSV, JSON, Avro, and Google Cloud Storage Cloud Data Store backups. Once data is loaded into BigQuery, it gets switched to the default columnar format for capacitor, which is just a BigQuery native storage format. The encoding format supported by BigQuery is UTF-8, although ISO-8859-1 is also supported for flat data only CSV files. For compressed files, the Avro format is the recommended file type for loading. That being said, BigQuery works better with the loading of non-compressed files as they can be loaded in a parallel fashion. When loading normalized data into BigQuery, it is best to use nested and repeated fields, in order to denormalize data for increased performance. So let's get started. Here I am in BigQuery. You could see I have a project called Boris Test Project, and underneath I have some public data sets. So as I mentioned, public external data sets could be queried without having to load them in. For example, I could scroll down to my USA underscore names data set, which contains my USA underscore 1910 underscore current table, which just contains baby names per state per year and tells me how many times they got registered. So I could query this by clicking Compose Query without having to load it in. Now let's say I want to load data in, so either locally from my computer or from a Google storage bucket that's stored in the cloud and that's private to me. What I could do is I could click on the downwards arrow beside my project and click on Create New Dataset. Next, I want to give the dataset ID, so I'm going to call it My First Dataset 1, and then I'm going to hit OK. Once that dataset gets created, I'll hit the plus sign beside the dataset to create a new table. I'll pick Create from Source. I'll choose File Upload, and I'll pick on Choose File. I'll go to Documents, and I'll find the file that I want to import. So I have a table called schedule.csv. I'll select that. I'll call the table schedule. I'll pick automatically detect for the schema, so it's just going to detect the schema from source, and I'll hit create table. That's going to import the table, load it in, and I should see it in my first dataset 1. So I could see here, I see my jobs, and I see load, uploaded file to boris-test-project, my first dataset 1.schedule. I could click on schedule and click on preview, and I could see my table, which just contains a schedule of baseball games that occurred. So now what I could do is I could delete this table by down clicking and clicking delete table. And if I want to import it from, say, a Google Cloud Storage bucket, I could do that as well. So if I go into my Google Cloud Storage bucket browser in my Google Cloud platform, I see I have Boris Test Bucket, which is just a bucket that I have. If I click on it, I could see inside it I have that same schedule.csv file containing the baseball games. So now what I'm going to want to do is I'm going to want to click once again beside my data set, the plus sign to create a new table. I'll pick create from source. Under location, I'll click Google Cloud Storage. And here what I want to do is I actually want to give the bucket location. So it's going to be gs:// for all Google Cloud Storage paths, Boris Test Bucket /schedule.csv. So that's the location. I'll give the table a name, call it schedule again, and automatically detect the schema, and then I'll hit create table to load the data and create the table. Once the job's done, I should see that I have that same schedule table with the baseball game data previewed. So those are two ways how we could go about loading data into BigQuery. In this demo, I will go over how to export data from a BigQuery table. BigQuery provides the option to export table data into a Google Cloud Storage bucket, or by using Google Cloud Dataflow to read in data from BigQuery. Supported formats for exported data in BigQuery are CSV, JSON, or Avro. BigQuery exports come free of charge, and BigQuery supports 1 GB files for export. If a table is larger than 1 GB, it can be exported into multiple files by specifying a wildcard with the star key. In order to be able to export data using BigQuery, reader permissions are required for the data to be exported in BigQuery, and writer permissions are required for the Google Cloud Storage bucket that will be receiving the exported data file. Some limitations with exporting include that you can only export to Google Cloud Storage, so you can't export locally or to Google Drive. You can only export a single table at a time. You can't export nested CSV data, and you also can't export data between regions unless the region you are using for your BigQuery dataset is in the US. Then you could export to a Google Cloud Storage bucket that's not in the US region. Exporting data in BigQuery can be done using the BQ command line tools, the REST API, the BigQuery web dashboard, as well as using BigQuery client libraries for languages like Python or Go. Limitations with exporting include a maximum of 1,000 exports and 10 terabytes of exports per day, and 500 wildcard URIs per single export. Okay, so let's get started. The first thing I'm going to do is I'm going to open up my BigQuery web dashboard. And I'm going to go to my public datasets, the ones that are available through Google with the BigQuery-public-data project. I'll scroll down and I'll go to my USA_names dataset, and that contains 2 tables with baby names from 1910 to 2013 and 1910 to current. Let's say I want to export the USA_1910_current table. I'm going to hit the downwards arrow and click on Export Table. The default format is CSV, but we could also change it to JSON or Avro. I'm going to leave CSV, and now I'm going to have to pick a Google Cloud Storage bucket. So if I go into my Google Cloud Platform Storage browser, I see I have a Boris test bucket defined. So I'm going to export it to this bucket, and I'm going to do / and give it a name. So I'll call it babynames.csv. I could now click OK, and it's going to export that table USA_1910_current into my Google Cloud Storage bucket. Okay, continue. So we can now see, if we go to our Jobs tab under Job History, we could see extract BigQuery-public-data USA_names.USA_1910_current to my bucket, and I see it's succeeded. I get the green check mark. I could go into my bucket and I could make sure that I have my babynames.csv file in here, and it's 109 megabytes in size. Let's say I want to export a bigger table. So in this same BigQuery public data, there's a Chicago crime data set, which contains all crimes in Chicago from the year 2001. And it's quite a big data set. So if I click on the crime table and I click export table in the Chicago crime data set, I'm going to try doing the same thing that I did with the baby name. So I'm going to put it in Boris test bucket, and I'll call it /crime.csv. Let's see what happens. I'm going to click OK, and I get an error here for my job. So if I click on the error, it says table crime.csv too large to be exported to a single file. And it's telling me to specify a wildcard URI with a star to shard export, because it's over 1 gigabyte, so we have to export in multiple files. So let's try doing that. Let's retry the export. And this time I'm going to also export it to the same bucket, Boris test bucket. But now instead of just doing crime.csv, I'll do crime. And then I'll do -star.csv. So this is actually going to export it and name the files like 001, 002.csv, and so on. And I'll get a number of files exported instead of just one big file, because it's over 1 gigabyte in size for this crime table. If I click OK, that's going to run the job, and it might take a little bit, but then we'll have all those files inside my Boris test bucket, Google Cloud Storage bucket. Okay, continue. So we could see that our extract job finished. If I go into my Boris test bucket, I could reload it, and I'll make sure that I have all my crime tables. I should have a few of them because I'm exporting with the wildcard. So we could see we have crime dash a bunch of zeros.csv, crime dash a bunch of zeros and 1.csv, 2, 3, 4, and so on. So this is how we could export tables over 1 gigabyte by specifying a wildcard with the star character, and then it'll export to multiple files. Now I'm going to show you how to export using the BQ command line tools. So what I'm going to be doing is I'll be running a command to export. It's the BQ space extract command. And I'm going to be specifying a destination format as new line _delimited_JSON. You could see up here that we have 3 options: CSV, new line _delimited_JSON, or Avro. If we don't specify a destination format, CSV is the default. The compression, by default, it's none, but I'm going to specify gzip. And then I'm going to specify my project, so boris-test-project, :myfirstdataset1.schedule, which is my baseball schedules table. And I'm going to put it in my Boris test bucket, and I'll call it schedule.json.gz because I'm using a gzip compression. So let's see what happens when I run that. I'm going to start the job from the Google Cloud SDK command line tools. And once it finishes, I should see the schedule.json.gz zipped file within my Boris test bucket. Okay, continue. So the job's done. We could go up and open up our Google Cloud Storage bucket. if I reload it, we should be able to see that file that we just exported from BigQuery. And sure enough, here it is, schedule.json.gz. So those are just some ways you could go about exporting data from BigQuery into Google Cloud Storage. In this demo, I will define the process of querying in BigQuery using nested and repeated fields. Nested and repeated fields in BigQuery allow for the storage of complex data types and relationships between various data types with a single table in order to flatten data and improve query performance. An example of this is where in other SQL databases you would have a table containing people and another containing cars. If we then wanted to associate the people in the table with the cars that they owned, we would typically create a third association table where the indexes from the people table would be associated to the index of the cars they own. BigQuery allows for nested and repeated fields so that BigQuery can add the cars record directly into the table of people, and it can also set the cars record to a repeated type in order to allow the addition of multiple cars per person. The exporting and loading of nested and repeated field data in the JSON and Avro formats is supported by BigQuery. With BigQuery Legacy SQL, when you want to query more than one independent repeated field, you may run into an error unless you call the flatten function. The flatten function takes into account each repetition of a nested field in order to allow querying over multiple repeated fields at once. Luckily, if you're using the recommended standard SQL to query repeated fields, the flatten function is no longer required. Okay, so let's get started. I have a dataset called my first dataset. I'm going to hit the plus sign to create a new table. I'll create an empty table. I'm going to call it people and cars. And for the schema name, I'm actually going to define a manual schema. So if I click edit as text, I'll be able to paste my schema in here. And if I take a look at my schema, it's just a JSON style schema. I'll copy it in and then explain it. So basically what this schema does is it defines a string for the ID of the person. There's the first name of the person as a string, the last name as a string, and then we have a cars record that's repeated. So the cars record contains the make, which is a string, the model of the car, which is a string, and the year of the car, which is a string. And since it's repeated, we could enter more than one car per person. Now if we go back to edit as fields, we could see that we have cars as a record, it's repeated, and then we have the attributes. So we have cars.make, cars.model, and cars.year. We could hit create table to create the table people and cars. So now if I click on compose query, I could enter some values into the table. So I'm going to insert some rows into the people and cars table with some people. I'm not going to insert the cars quite yet. I'll be doing that once I insert the rows. So I'll insert my first dataset one.people and cars. I'll insert ID, first name and last name, and the values are going to be John Doe, and number 2 is going to be Walter Doe, number 3 is going to be John Smith, and number 4 is going to be Ted Smith. And I just want to make sure that I also uncheck use legacy SQL to use standard SQL for my statements, because that is the one that's recommended by BigQuery. So if I go ahead and run my query, I should get my table. I could click on it and preview it and just view the different rows. So we could see that the cars.make, cars.model, and cars.year columns are not yet populated. So let's populate these columns. So what I'm going to be doing is that I'm going to add a 1995 Honda Civic to all the owners with a first name of John. So I'm going to copy this query in and then explain it into BigQuery. So what I'm doing is I'm updating my first dataset one.people and cars. I'm setting cars as an array. I'm selecting car from unnest cars as car, and then I'm doing union all, and then I'm selecting Honda Civic 1995. So this is actually going to put Honda Civic 1995 as a car, and then I'm specifying where first name like John. So we could see we have 2 Johns in the table. Row 1 is John Doe, row 4 is John Smith. So we should expect Honda Civic 1995 to appear for both Johns in the table. So once that's complete, I could click on people and cars, preview it again, and we could see John Smith and John Doe now both own a Honda Civic 1995. So let's add a second car to this table. What I'm going to be doing is I'm going to be adding a Toyota Corolla to all the people with a last name of Smith. So if I copy this in and paste it into BigQuery, Same as I did last time, except now what I'm going to be doing is on line 5, I'm specifying select Toyota Corolla 2005, and then on line 7, instead of by first name, I'm specifying where last underscore name like Smith. So if we look at the table, we could see that we have two Smiths. We have Ted Smith and John Smith. John Smith should now receive a second car, which is going to be a 2005 Toyota Corolla. If we run the query and then we reload the table and preview it, we should see that we now have the Smiths. So Ted Smith owns a Toyota Corolla 2005. John Smith now owns two cars. He owns the 1995 Honda Civic and the 2005 Toyota Corolla, as we expected. So now I'm going to display the number of cars per person by doing another query in BigQuery. And the way I'll be doing that is that I'll be doing select first underscore name and last underscore name. So I'm just going to display the last name and first name and the number of cars for that individual. I'm going to specify array underscore length of cars. So that's going to tell me how many cars each individual owns as the number of cars from my first dataset dot people and cars. So if I run this query, I should get a new table created, and we could see that first name Walter Doe has 0 cars, John Doe has 1, Ted Smith has 1, and John Smith has 2 cars. Now what we're going to be doing is finally we're going to be deleting all cars in the table that aren't Toyota. So that's just the Honda Civic that we added in 1995. So we're going to be running another update query. And this query is going to update my first dataset 1.people and cars. Once again, set cars equals array, and then select C from unnest cars as C. And then this is where we're going to be specifying on line 4 where C, so car.make is not like Honda. And then we're going to say where true. So basically all the cars that are Honda in our table should get eliminated. We'll only have the 2 Toyotas left. If we run the query, it's going to execute, and we could take a look at the table again and preview it. And we could see that the Honda Civics are gone. We now only have the 2005 Toyota Corollas in our table. So that's how we could go about doing queries for nested and repeated fields in BigQuery. In this demo, I'll demonstrate how to use query plans and complex queries with BigQuery. BigQuery comes with a query plan feature which displays query performance when using queries through the BigQuery REST API or web dashboard. The query plan is used to improve query performance by showing metadata about each stage, from data read to data output of an executed query. The query plan feature was put in place instead of an explain statement, as explain statements are not supported in BigQuery. Each stage of the query displays data involving the records read, records written, as well as the ID of the stage. For each stage of the query plan, there is a number of steps including read, write, aggregate, compute, filter, sort, limit, and join. The relative max and average timing of worker wait, read, compute, and write operations is displayed in a graphical format for each executed stage of the query plan. So let's get started. I'm just going to do a very basic query. I'm going to query my dataset.temps. So I have a table, and in the BigQuery web user interface, you could see under my dataset, I have a table called temps. And I'm just going to select count star from my dataset.temps where temp is greater than equal to 40. I'm going to make sure I uncheck use legacy SQL, and I'm going to run my query. Once my query runs, I could see how many temperatures I had that were over 40 degrees Fahrenheit. And if I click on details, I'm actually going to get the query plan. So I could see I have various stages. And for example, stage 1, I could see output. I have 2 yellow bars. So I could see that the average time was 32 milliseconds with the darker yellow bar, and then the max time is 65 with the lighter shade yellow bar. And that's for wait because it's in yellow. I could also see for read, which is in purple, compute, which is in orange, and write, which is in blue. I could further click on the stage and I could actually take a look at the operations happening. So I could see that I'm getting temp, I'm reading temp from my dataset.temps where greater or equal to 40, and then I'm aggregating it and writing it to stage 1 output. Then I could go to stage 2 and I could see what's going on. So here I'm reading from the stage 1 output and I'm aggregating the sum of counts, and then I'm writing that to the output, and that's the result that I'm getting of 237 temperatures over 40 degrees Fahrenheit. So that's just a very basic query and how we could go through the query plan. So If the query were to produce an error, it would be possible to view the query plan up to the stage of where the error happened to help in troubleshooting. And basically in that case, we would get a red exclamation mark beside the stage that the error happened and we could troubleshoot further. When you call the jobs.get REST API method in BigQuery specifying a job in project ID, you get a query plan which is retained for 7 days from when the job was run as part of the returned data in a JSON format. So let's do that. I have a job that I ran before and it's in the Boris-test-project. So I'm just going to copy the project as that and I'll paste it into Linux into my command prompt. And then I'm going to go back and I'm going to copy the job ID for that job. And I'll paste that into my Linux terminal as well. And then finally, I'm going to run a command to query the BigQuery REST API with curl. So I'm going to specify curl-h authorization. I'm going to get the bearer token with the gcloud auth print-access-token for my account. And I'll specify the URL as https://www.googleapis.com/BigQuery/v2/project. I'll specify the project variable, which contains my Boris test project, jobs, and then the job ID, which I specified. So if I run this curl command, I should be able to get the job returned. And inside that job, I'm actually going to have my query results, and I'll be able to see what happened. So if I scroll up here, I could actually see that I have a bunch of stuff returned, and I should have my query plan right here. So if I look at my query plan, I see I have stage 1, ID 1, I have my weight ratio average, weight ratio max, read average, read max, compute average, compute max, write average, write max, and so on. And I could see the status of the stage, it's complete. And then I could scroll down and I could take a look at stage 2 and so on. So that's how we could look at the results, which are stored for 7 days that get returned from the jobs.get REST API command. So now I'm going to look at a case where we could improve the performance of a more complex query. So what we're going to do is I'll just copy this query in to BigQuery. And this query that I'm going to copy in has one major inefficiency, which we could fix by taking a look at some various things that we could do. So if we take a look at this legacy SQL query, we could see we're selecting the outpatient charges.provider name, and then we're basically counting all the provider names for the different hospitals. We're selecting it from BigQuery public data project in the Medicare dataset, and inpatient charges 2012 is inpatient charges. And then we're joining it to the outpatient charges 2012 table as outpatient charges. And then we're doing the join on the provider ID because it's common between both tables. And on line 6, where inpatient charges.average_total_payments is greater than 20,000. So anytime we have over 20,000 average total payments in the inpatient charges, we're going to join that provider ID with the outpatient charges table. And then we're just going to specify here group by 1, and we're just going to write it out. So if we run the query, we're going to see that we basically get a list of all the provider names, all the hospitals, and the count that we returned from the join operation. And what we could do is we could take a look at the details, and we could take a look at the query plan. So if we take a look at the stages, if I go under stage 2, I could see I have a read and a write. I could go under stage 3. I could see I have a read, I have another read, I have a join, and I have a filter. So it says filter greater inpatient charges.average_total payments is greater than 20,000. So I have an inefficiency here because basically what I could do is instead of actually doing the filter after I do the join, I could do the filter beforehand on the inpatient charges 2012 table. So I actually reduced the size of the join by filtering earlier. So let's do that. I'm going to copy in another query. And what this query is going to do is that it's going to have a subquery here. So it's going to select star from the inpatient charges 2012 table where the average total payments is greater than 20,000 as inpatient charges. And after that, it's going to join to the outpatient charges table on the provider ID. So this should be more efficient because I'm actually doing the filtering before I do the join, and it's going to reduce the size of the join. So once the query is run, I could go back to details. I could go to my execution plan for my query plan. If I click on stage 3, you could notice that I no longer have a filter operation here. Instead, under this read operation, this second read operation, I have the statement where greater average underscore total underscore payments 20,000. So I improved the performance of my query by moving the filter before the join, because it was only based on the inpatient charges 2012 table, and we didn't have to use the outpatient charges 2012 table after the join for the filtering. So that's how we could improve query performance on a more complex query by using the query plan. In this demo, I will describe the process of querying multiple tables in BigQuery. When using standard SQL for queries in BigQuery, it is possible to query multiple tables in a dataset by using a wildcard star character to match table names. This is best used when the tables contain like schemas and are similar in naming. This could be useful if, for example, you have a dataset that tracks medical patient records over the course of several years, and you have a table for each year which you want to query. If the schemas are not similar for tables being scanned through a wildcard query, BigQuery will return an error. When using wildcards in BigQuery to query multiple tables, it is worth mentioning that the wildcard query will not work for external table or view queries, and will only work for tables stored in BigQuery's native columnar storage, and also cache queries cannot be reused for wildcard queries on multiple tables. The underscore table underscore suffix statement can be used in the where clause of a query to restrict the tables that get queried. One example of this could be restricting the queries of the patient records tables for the past 2 years. The underscore partition time statement can be used in the where clause to further restrict the query to only scan a particular region of a table during the query if you are querying an ingestion time partition table in BigQuery. It is also worth to note that the more detail given regarding the table names to be queried will improve the wildcard query performance. So let's get started. What I'm going to be doing is under the BigQuery public data project, I'm going to go to the CMS Medicare dataset, and we could see these 5 tables: outpatient charges 2011, 12, 13, 14, and 15. Now these tables just contain charges per hospital, per patient that were given in these years. So I'm going to be doing a standard query without using wildcards just to show you how that could be done, and then I'll introduce wildcards, which is going to greatly reduce the query size. So if I paste the standard query in, I'm selecting the provider ID, provider name, provider street address, provider city, and the average estimated submitted charges per patient. And then you could see I'm basically selecting from all 5 of these tables. Now that's not the most efficient way of doing it, and I'll show you how you could make it better with wildcards. If I order it by the average estimated submitted charges, I'll get the maximum charges out of all that time frame per hospital, and I'll see which hospital is the most expensive. If I do run query, I'll be able to see the results. And I could see the Heinemann University Hospital has the biggest charges with about $49,000 per patient. So now what I'm going to be doing is I'm going to be rerunning the same query, except I'll be using a wildcard, and the query will get a lot shorter. So I'll simply copy this query back in, and you could see how short it is. So the select is the same. I'm still selecting the provider ID, provider name, provider street address, provider city, and the average estimated submitted charges. But now I'm actually going to specify the CMS Medicare dataset dot outpatient underscore charges star, which is basically going to match with all the different tables 2011, 12, 13, 14, and 15. And I'm going to order it by the average estimated submitted charges to get the highest charges. So now once I do this, I'm going to get the table again, and it should be the same result, and it is. And I could see how much room I saved and how much time I saved by using this wildcard character. And this would be even more relevant if I had more tables to query. So let's go actually restrict the range of our queries. So let's say instead of wanting to query all 5 of those tables, we only want to query the last years, 2014 and 2015. So in this query, once again, I'm selecting the provider ID, provider name, provider street address, provider city, and average estimated submitted charges. But you could note in my from clause, I'm also using the BigQuery public data project, the CMS Medicare dataset. But for outpatient charges, I'm actually specify underscore 20 star. So I'm creating a longer prefix that's going to get matched with the wildcard. And this is because the 20 is the same in every table, but the unique element is the last two characters. So 1, 1, 1, 2, 1, 3, 1, 4, and 1, 5. And then I have a where clause here on line 10, and it's the table suffix between 14 and 15. So it's basically saying any tables that end in 14 and 15, I'm going to want to take the select statement from, and then I'm going to order by average estimated submitted charges descending. So I'm not going to include the 2011 or 2012 or 2013 outpatient charges tables. I'm only going to include the 2014 and 2015 tables. And I could do that to save on query time, and query performance will improve. So now what I'm going to be doing is I'm going to query an ingestion time partition table in BigQuery and return the coldest temperatures of February 2017 in Celsius. So I'll copy this query in, and basically what I'll be doing is I'll be running a select statement, selecting the station on line 2 and temperature in Fahrenheit on line 3. On line 4, I'll be converting the temperature in Fahrenheit to Celsius. I'm going to be selecting it from a data set I have. It's a private data set under my Boris test project called my dataset, and I have a table called temps. So I'm basically selecting everything inside my dataset, which is only temps. So I don't have to use a wildcard, but I am here just for the demo. And then I'm specifying a where, and on line 9 I have underscore partition time, and I'm specifying the timestamp as 2017-01-01. So basically I'm saying get all the temperatures from January 2017. Now I also have temperatures from January 2016 and January 2018. And then I'm ordering by Celsius ascending, so I'm going to get the coldest temperatures in January 2017. If I run the query, I should see that the coldest temperature in January 2017 is minus 26.6 Celsius. Now for fun, let's just comment out the where and the partition time statements. And if I do this and I rerun the query, I'll get the coldest temperatures for January 2016, 2017, and 2018. And I could see now the temperature is much colder, minus 37.3, because I'm using 3 years time for January temperatures. So that's how we could go about and do queries on multiple tables using wildcards in BigQuery. In this demo, I'll further demonstrate how to create queries in BigQuery, and we'll go over writing query results, using cache queries, using parameterized queries, and saving and sharing queries. In a previous video in the course, I showed how to use the 2 types of queries that BigQuery supports, which are interactive and batch queries. I will now go into more detail about queries, talking about some of the other things you can do with queries in BigQuery. The first thing I will go over is writing query results in BigQuery. Query results are written to either permanent or temporary tables in BigQuery. Temporary tables are used for caching query results and are stored in a hidden dataset and generally stay alive for around 24 hours. A permanent table is an existing or new table which gets created based on query results in an existing dataset. Permanent tables can be created in BigQuery using the web dashboard, BQ-CLI command line tools, REST API, and client libraries for BigQuery. So here I am in my BigQuery dashboard. I'll just go over how I could create a permanent table. So I'm just going to copy a command in a query, which is just going to select from my temps table inside my dataset. It's going to select the station, the temperature, and it's going to convert the temperature to Celsius on line 4. And it's going to find that on line 9 for the partition time. The timestamp will be 2017-01-01. So it's going to find basically the coldest temperatures in January 2017. So what I want to do now is, before I run the query, under my options for destination table, I want to click select table. And here I want to select a project. So I only have one project, Boris test project. I want to select the dataset. Let's say I want to save it in my first dataset 1, and I'll give it a name. I'll call it temps2. If I click OK, I could now run the query. But before I do that, I could also specify write preferences. So I could specify write if empty, so that means I'm basically going to write everything to the table. I could specify append to table, so if I specified an existing table, I could append the results of the query to that table, or I could specify overwrite table, which is going to basically overwrite all my results into the new table if that table had any other data inside it already. So I want to uncheck use legacy SQL, and I see I get the check mark for the validator. If I do run query, I should see it my first dataset 1. I should have a temps2 table, and I do, and if I preview it, I should see I have my temperatures. So that's all working like expected. So next I will discuss parameterized queries. When queries are made from user input using standard SQL and BigQuery, query parameters can be used to prevent SQL injection attacks. Query parameters cannot be used in place of table names, identifiers, or column names, and they can only be used for arbitrary expressions. So I'm going to demo this by going to my Linux command prompt, and I'll be running a parameterized query using the BigQuery CLI command line tool. So BQ space query -- use legacy SQL false, because I want to use standard SQL, and then -- parameter equals MO. So I'm specifying the month for the temperatures, : as 05, and another parameter which will be min underscore temperature. It's a float64 type and 40. So what I want to do is I want to select all the temperatures that are above 40 degrees Fahrenheit from May 1930. So I'm selecting the month and the temperature from the BigQuery public data project, the NOAA GSOD dataset, and the GSOD 1930 temperature values from 1930. And I'm saying where month or where MO is equal to @MO. So I'm basically specifying that parameter of 05 there. And temperature is greater than equal to @min temperature, which I have as 40 degrees Fahrenheit, and I'm just going to order it by temperature descending. So if I run this query, it's going to submit a job to BigQuery, and I should see all the temperatures that are above 40 degrees Fahrenheit going from greatest to least in May 1930. So now continuing on, next I will talk about saving and sharing queries. There are 3 levels of saved queries in BigQuery: public, private, and project level. Queries need to be saved at the public or project level in order to be shared. When a query does get shared, only the query and not the data that the query is run against is shared. So if I go back to my BigQuery web dashboard and say I want to save this query, I could click on Save Query under Run Query, beside Run Query. If I click on Save Query, I could give it a name. I'll call it My First Query. And I could change the visibility, so if it's private, only I could see it. If it's project level, any project members could see it. Or if it's public, anyone with the link can see it. So I'll select project level and hit OK. That's going to save my query. Now what I could do is, once that's done, I could click on Query History under Compose Query. And if I scroll down, I could look at my saved queries. And I see I have no saved queries for myself, but if I go to project queries, I could see I have my first query. I could click on that and I could actually see my query. I could then edit it by clicking edit query, or share it by clicking the share link. I could then copy the share link, post it in my browser, and I could open that window with the saved query, and then I could execute it. Now just a note, this actually won't execute unless I have the underlying data in the query available, because only the query gets shared, not the underlying data associated with the query. Finally, the last thing I'll talk about is caching query results in BigQuery. As I mentioned, BigQuery saves all query results to either a permanent or temporary table. If a table with the query results already exists, no costs are associated with doing a cache query. Temporary tables are automatically created when a query is executed and incur no additional data storage costs. Some restrictions with caching is that it cannot be used against multiple table wildcard queries, queries with external data sources, and if a destination table is specified. So I'm just going to go ahead and I'm going to remove this destination table. And you can notice that I have use cached results checked. I'm just going to do a very simple query. I'm going to select everything from my dataset.temps, and I'll be selecting everything where the station is 014140. So I'm going to paste this very simple query in. And if I click on the query, I should be able to run the query. And once it runs, the next time I execute the query, I should get the results that it was actually a cache query. And you can see I actually already did run this query. So it says query complete, 5.4 seconds elapsed, and cached. Now if I uncheck use cached results, I could rerun the query. And if I rerun the query, I should get that the query was completed, 2.1 seconds elapsed, 6.25 kilobytes processed. So I'm getting charged for those 6.25 kilobytes because I'm not using my cached results because I unchecked query caching. So that's pretty useful. If you want to turn on query caching, you could turn it off by unchecking use cached results. So that's it for building queries in BigQuery. I just went over how we could write query results, use cache queries, use parameterized queries, and save and share queries. Now that we are all done our lessons, it's time to do some practice. In this exercise, you will define BigQuery and its use in the Google Cloud Platform, describe BigQuery datasets, tables, and views, execute interactive queries using the BigQuery web dashboard, load data saved in a Google Cloud Storage bucket into BigQuery, query a table containing nested and repeated fields, use query plans to improve query performance in BigQuery. Now pause the video and perform the exercise, and I'll get back to my solution. Okay, continue. So the first thing I'll talk about is defining BigQuery and its use in the Google Cloud Platform. Google Cloud BigQuery is an enterprise-level data warehouse which can be used to process and analyze big data sets using underlying Google Cloud compute, networking, and storage technologies. BigQuery is fully managed by Google and is located in the cloud. Since BigQuery is deployed in the cloud and it keeps storage resources separate from compute, it can auto-scale very quickly depending on demand in order to analyze petabytes of data instantly. Standard SQL is supported for BigQuery queries, so there is a low learning curve to get started. There are a variety of ways to use BigQuery. You can launch it through the Google Cloud Platform web dashboard, through the Google Cloud SDK BQ command line tool, through a REST API, and through client libraries for languages such as Ruby, Python, Go, and Java. BigQuery also integrates with industry-leading tools for data integration, data visualization, and analytics, such as ETL tools like Informatica and business intelligence tools like Tableau. Next, I'll describe BigQuery datasets, tables, and views. A dataset in BigQuery is located inside a Google Cloud Platform project. Datasets are used to store tables and views. In order to start importing data and working with BigQuery tables and views, a dataset needs to be defined first. There are three ways to create BigQuery datasets, either through the BQ make command from the command line, the datasets.insert REST API method, or through the BigQuery web dashboard. You must also have BigQuery.datasets.create permissions enabled for the project in use. Access controls can be applied to roles when accessing BigQuery datasets, or to a role accessing an entire Google Cloud Platform project, in which case all BigQuery datasets belonging to that project within the dataset would be accessible to the user role. Next, I'll talk about BigQuery tables. BigQuery tables are located within BigQuery datasets and are used to store data in rows and columns. Each row represents a single record of data. A table contains a schema which defines the column names and the types of data each column uses. The schema can either be manually entered or it can be auto-detected and populated by the first job that either loads data or queries the table. BigQuery table schemas can be updated either manually by updating the original schema or automatically by running a query or load job. BigQuery data performs better when it has no relational schema requirements. One way you can preserve relational data previously located in multiple tables, all in one table, is to use a nested column where you can put all relational data into it. There are three types of BigQuery tables. These are native, external, and views. Native tables are the default type where tables are stored in BigQuery columnar storage. External tables are tables where the data is not native to BigQuery and is stored in places such as Google Cloud Storage, Google Drive, and Google Cloud Bigtables. Finally, I'll talk about views. Views are another type of table, and they're virtual tables, and they get defined by running an SQL query on an existing table. The results of the query can then be saved as a view, and other queries can be run against the saved view. BigQuery tables.create permissions or writer access for the dataset is required for a role to be able to create a view in BigQuery. There are several limitations with views, including that you cannot run a job to export data from a view. If a view was defined using legacy SQL, standard SQL queries cannot be used on the view, and you're only allowed 1,000 views per dataset. Next, we'll talk about executing interactive queries using the BigQuery web dashboard. So I'm going to go into the BigQuery web dashboard, and I'm going to go ahead and open up my notes here, and I'm going to execute some interactive queries. So the first query I'll be executing is going to search for all the names Mary in a data set that contains a table with all the USA baby names from 1910 to current. So I'm going to be selecting the name, and I'm going to be coalescing and casting the sum of the number as float 64 of all the names per state as names total. So I'll get the total number of names from the BigQuery public data project USA names dataset USA underscore 1910 underscore current table, where the name is equal to Mary, and I'll group by the name and I'll order by names total. So I'm just going to change the option to uncheck use legacy SQL to use standard SQL. I should get a check mark in my validator. If I run the query, I'll see how many Mary names there was in the US between 1910 and now. And I could see it's quite a bit, it's over 3 million. So I'll run another query against this same table. I'm going to get a list of the 10 most common names in the past 100 years. So the way I'll do this is I'll just paste the query in. So once again, selecting name, I'm going to select the number as well, but I'm going to cast it to the names total number from that same USA underscore 1910 underscore current names table. And I'm going to group by the name and order by the names total. And I'm going to specify a limit of 10. So I'm going to get the 10 most common names from 1910 until now. If I run the query, I should see 10 names pop up, and I could see the most popular name in the past about 100 years is James, followed by John, Robert, Michael, William, and I could go to the next table, Mary, David, Richard, and so on. So now what I'm going to do is I'm going to load data saved in a Google Cloud Storage bucket into BigQuery. So I'm going to load it in the data set in my Boris test project called My Dataset. I'm going to hit the plus sign, and I'm going to pick Create from Source. I'm going to pick Google Cloud Storage. I'm going to go into my Google Cloud Storage bucket. I have a Boris test bucket that contains a schedule.csv file. So I'm going to specify gs:// Boris test bucket. And then I'm going to go / schedule.csv. File format I'll leave as CSV. The destinational table name I'll call schedule. And the schema I'll pick auto detect, which is going to automatically generate the schema from the table that I'm importing, and I'll hit create table. That's going to create a load job, and I'll be able to load my table in, and I'll see my schedule table. If I click on it, I could look at the schema and I could preview some of the data inside my schedule table. So now I'm going to query a table containing nested and repeated fields in BigQuery. So I have a table called people and cars in my first dataset 1 dataset, and if I take a look at this, this table contains some nested and repeated fields for cars. So basically each person can have one or many cars, and each car has a make, a model, and a year. So what I'm going to do is I'm going to go ahead and I'm going to add a 1995 Honda Civic to all the owners with a first name of John. So I'm just going to copy this query in and replace this old query. So I'm going to update my first dataset 1.people and cars. I'm going to set the cars to an array. I'm going to select the car from the array of cars as car. I'm going to specify union all, and I'm going to select Honda Civic 1995 as the cars.make, cars.model, and cars.year. And then on line 7, I'll specify where first underscore name like John. So all the people that their first name starts with John, so we have John Doe and John Smith, should get a 1995 Honda Civic when I run this query. So once the query finishes, we could take a look at the preview of the table. If we click on people and cars and hit preview, and we could see that John Smith and John Doe now both have a 95 Honda Civic. Now if we want to add a second car, we're going to go ahead and we're going to add a 2005 Toyota Corolla for all the people in the table who have a last name with Smith in it. So we're going to update my first dataset 1 people and cars, set cars to the array. We're going to select a car element from the array as car. We're going to specify union all because we're adding a car, and we're going to run a select Toyota Corolla 2005 for the make, model, and year, where on line 7, where last underscore name like Smith. So in this case, we have two Smiths. We have John Smith, who already has a Honda Civic. He's going to get another car, a Toyota Corolla. And we have Ted Smith, who doesn't have any cars, but he's going to receive his first car, the Toyota Corolla. So if we run the query and then we look at the table, we should see that we now have John Smith now has two cars. He has a 2005 Toyota Corolla and a 95 Honda Civic. And John Doe has his 95 Honda Civic, and Ted Smith received his first car, the 2005 Toyota Corolla. So now moving on, I'm going to use query plans to improve query performance in BigQuery. So I'll be doing this using legacy SQL. So I'll check use legacy SQL, and I'm going to execute a query against a Medicare dataset that's publicly available. And the query is going to have some inefficiencies in it, which I'll correct. So I'm going to select from the Medicare dataset in the outpatient, using the outpatient charges 2014 and inpatient charges 2012 and outpatient charges 2012 tables. So I'm going to select outpatient charges.provider name, and then I'm going to count basically all the cases that my join is true and display that from the BigQuery public data project, the Medicare dataset, and the inpatient charges 2012. As inpatient charges, I'm going to join it to the outpatient charges 2012. And I'm going to do this on inpatient charges provider ID is equal to outpatient charges.provider ID in the case where the inpatient charges average total payments is over $20,000. And then I'm going to group it by the provider name, which is the name of the hospital, and order it by the number of occurrences. So if I run this query, I should see the result, and I could see all the different provider names and the count for my join where the case over 20,000 was true. I could click on details to look at my query plan. And if I click on stage 3 here, I could see that I have a filter. And this filter says greater inpatient charges.average underscore total underscore payments and 20,000. So I'm basically adding an extra step because I'm not doing the filter when I'm actually doing the from. So I could do another select statement when I'm actually getting my inpatient charges 2012 data, and I could actually do the where clause here for the filter, which is going to reduce the amount of data I need in my join statement and make my query more efficient. So what I could do is I'll load another query in, and this query is going to have that filter moved up. So once again, I'm selecting outpatient charges.provider name, I'm getting the count, and then here on line 3 is the difference. So from, I have a subquery selecting star from the inpatient underscore charges underscore 2012 table, where the average total payment is over 20,000 as inpatient charges, and then I'm joining it to the outpatient charges 2012, and I'm joining it on the provider ID. Now, because I'm moving the filter up into the inpatient charges 2012 table, I'm actually making my join smaller, which is going to increase the performance of my query. If I now run the query, I could see it got the same result. I could click on details to look at the query plan. If I go to stage 3, I now see that I no longer have that filter operation. It's instead in the read operation. In this second read operation, I have where greater bracket average underscore total underscore payments 20,000. So I've increased the efficiency of my query by moving that filter into a subquery select statement up above before the join. So that's it for the exercise. I'll just go over what we talked about. So in this exercise, we defined BigQuery and its use in the Google Cloud Platform. We described BigQuery datasets, tables, and views. We executed interactive queries using the BigQuery web dashboard. We loaded data saved in a Google Cloud storage bucket into BigQuery. We created a table containing nested and repeated fields. And we used query plans to improve query performance in BigQuery.
In this video, we'll describe the machine learning workflow and how the process works in various scenarios. The machine learning workflow begins with a problem, one that is well defined. Machine learning is not a perfect solution. It is, in fact, an iterative process requiring adjustment. The goal is to end with a predictive mechanism that can efficiently and reliably be used to make predictions with new data. Data patterns, which may not be obvious at the outset, are key to problem resolutions. Large amounts of data are typically required in order to make valid inferences based on the data. This rather large data set must include the attribute which is known as a feature in machine learning. A machine learning algorithm, or set of algorithms, can then be selected and trained with the input data in order to come to a final collection of settings and configurations. These settings and configurations are also known as hyperparameters, and these ultimately make the machine learning model effective and accurate. Now let's look at some considerations. First, is the problem one that is well understood? That's going to be key. Absent a clear purpose, one can end up with an entirely inappropriate model. Next, is machine learning the best approach? Machine learning should only be considered when you have access to a large data set, as this will be key to training the model. Furthermore, consider whether there may be a more traditional approach involving a well-understood mathematical model that might just be more suitable. And finally, how do you know when you are finished? That is, you can continually tinker with your model, obtaining incrementally small improvements in accuracy, but you need to decide how accurate you need to be. Using machine learning effectively comes down to preparing so that you have good data. And this means understanding the data thoroughly. It also may include aggregating existing data and visualizing to see if there are noticeable trends. In addition, you should use whatever tools you have at your disposal to identify patterns and identify features, that is, a subset of data attributes in the raw data that are applicable to the model you're developing. Finally, clean the data of anomalous values, particularly paying attention to those that may be a result of data entry or measurement errors. The last step to preparing good data is pre-processing. And this typically means normalizing numeric data so that it has a common scale, eliminating redundancies through simplification, applying formatting rules to the data, for example, removing HTML tags from a text feature, and assigning key values to data instances. For this step, you can use Google Cloud Data Lab for some aspects of data exploration and prep, but other cloud platform services can help here as well. And these services include BigQuery, Cloud Dataprep, as well as Cloud Dataflow. Once the data is well understood, models can be designed to use that data to predict target values in new data. Each model will undergo a series of steps to make corrections and refinements. First, develop the model using established machine learning techniques and in a cloud machine learning engine context using TensorFlow. You train the model, providing it with the data for which you already know the target values. The model will predict target values based on the training data, and the model can adjust to more accurately predict or fit those targets. Then you evaluate your trained model by using data that includes target values. Compare results of the model's predictions to actual values and use statistical techniques that are appropriate to your model to measure success or accuracy. And once again, it's an iterative process, so you make adjustments to the model, changing operations and/or settings accordingly. To test the model, you need to give it data in a way that mimics its eventual final application. A different data set should be used for testing than that used for training and validation. Each time you test it, you should try to use a different data set, one that it has never processed before. As the model is tested, it should be connected to the application's infrastructure and make adjustments as necessary based on the results derived from testing. Finally, test the model by requesting predictions using Google Cloud Machine Learning Engine. In this video, we'll look at Google Vision API and its purpose. Google Cloud Vision API is a Google REST API. It's one of the more interesting applications using machine learning. Vision API applies machine learning to the analysis of images. Consumers can use Vision API to quickly and easily perform image classification. Vision API can classify any number of images across thousands of categories. For example, cat, house, mountain. It also performs object detection within images, as well as face detection. But be careful here, it's not facial recognition, it's just face detection. It uses optical character recognition to recognize and read printed words and text within images, and couples that ability with automatic language detection supporting a wide range of languages. Using machine learning models, Google indicates that results will improve over time as accuracy improves and new concepts are introduced. Some key use cases include detecting inappropriate content. Vision API can be used to detect inappropriate content, including adult and violent content. It can incorporate Google image search to find interesting objects like logos on the web, and when combined with visually similar search, find similar images on the web. Again, optical character recognition technology can recognize characters within images. So for example, one could scan an image of a document and convert that into a document that may be edited. And face detection is an interesting use case. Vision API can detect multiple faces, in fact, within an image, which is very practical, but it can also detect facial attributes like emotional state, or was that face wearing glasses, for example. In this video, we'll look at the Google Natural Language API. The Natural Language API provides a number of methods for performing analysis and annotation on some given text. There are multiple levels of analysis, and each delivers valuable information for understanding language. First, sentiment analysis. You use the Analyze Sentiment method to inspect a set of text and identify the dominant emotion exhibited by the writer within the text. Typically, this is used to determine whether the attitude of the writer is neutral, positive, or negative. Syntactic analysis employs the Analyze Syntax method, and this is used to extract syntactical information. It can divide a set of text into a series of sentences and what are known as tokens, which, for all intents and purposes here, are simply words. Those tokens are then evaluated to determine their syntactic meaning within the text. And for content classification, we can use the Classify Text method to analyze text content and return a list of related content categories. We can use the Analyze Entities method to perform entity analysis. And this is used to examine a set of text for familiar entities and provide information about those entities. There are two broad categories of entities: proper nouns, like specific people or places, and common nouns, like, for example, restaurant, building, and so on. It returns information about those entities, for example, the entity's type, locations in the text referring to the entity, and the entity's relevance to the overall text. And finally, entity sentiment analysis. The Analyze Entity Sentiment method examines a set of text for familiar entities and returns information about those entities similar to the Analyze Entities method, but it also identifies the dominant emotional state or opinion of the entity within the text. This is particularly useful for determining whether the author's attitude towards the entity is neutral, positive, or negative. And this is an example of a simple natural language JSON entity analysis request. So within this JSON document, my doc contains the data for this request, and the request is specified in the subfields. So for example, the document type here. And that can be plain text or HTML. Then there's content. Here, you specify either the content directly or a content URI pointing to the text to evaluate. If the content is passed directly, as in this example, the text is included directly in the JSON request. If passing a content URI, the field must specify a URI pointing to the text in Google Cloud Storage. And language. The language of the text in the request is optional. If the language isn't specified, it will be automatically detected from a wide range of supported languages. Unsupported languages will return an error in the JSON response. And finally, encoding. The encoding type is required, and this specifies the encoding format that's used. In this video, we'll describe the Google Translation API, Speech API, and we'll also have a look at Speech API best practices. First, Translation API. Google Translation API uses what's called neural machine translation. Neural machine translation uses a large artificial neural network to predict how likely a sequence of words will occur, typically modeling entire sentences. This makes the Translation API very responsive. The Translation API also supports language detection if you're not sure of the source text language. This can occur when, for example, user-generated content doesn't include a language code. Translation API supports over 100 languages and thousands of language pairs. You can input HTML and receive HTML with translated text returned. There is no need to extract the source text or reassemble the translated content. It's also very easy to integrate since the Translation API is, after all, a Google REST API. The Translation API can scale to almost any volume. Google provides a generous daily quota that allows limits to be set below the daily quota. You can also request an increase if a higher quota is required. The Google Speech API is a tool that's used for speech recognition. It's another Google REST API that allows developers to convert audio to text. It uses artificial neural network models and supports more than 100 languages. The service is capable of handling audio noise and can be customized for a specific context, which is particularly useful for device or app control use cases. Use cases include voice-based command and control, transcribing dictation, as well as transcribing audio files. Key Cloud Speech API features include content filtering. So this means that inappropriate content can be filtered out. Streaming recognition returns results of the speech recognition in real time while the end user is still speaking. That's how responsive it is. With the Speech API, you can capture the input from an application's microphone or from a pre-recorded audio file supporting a number of formats, including lossless FLAC. Automatic speech recognition is made capable thanks to deep learning neural networking, providing voice search or speech transcription. Word hints can be provided to customize speech recognition for a specific context. For example, you can specify custom words or names in voice control scenarios. Now let's look at some best practices for speech data. For optimal results, audio should be captured using a sampling rate of at least 16,000 Hz. A lossless codec should be used when recording and transmitting audio. For example, FLAC or Linear 16 is recommended. Word and phrase hints should be used where possible to add names and unfamiliar terms to the vocabulary, which serves to enhance the speech recognition engine's accuracy. When audio is being captured from more than one person, and each person is recorded on a separate channel, each channel should be sent separately. If, on the other hand, all those speaking are mixed in a single channel recording, then the recording should be sent that way. Although the speech recognition engine has been designed to ignore background voices and noise without the help of supplementary noise canceling, best practice is to position the microphone as close to the person speaking as possible, especially when there is background noise. For short queries or commands, use streaming recognize from the client libraries and set single utterance to true. This will optimize speech recognition for short utterances and also serves to minimize latency. When using live audio, the stream is split into frames and sent in consecutive streaming recognize request messages. Keep in mind that larger frames are more efficient, but they also add latency. Google recommends a 100 millisecond frame size as a good compromise between latency and efficiency. And finally, the cleaner the audio, the better, obviously. It may seem counterintuitive, but applying noise reduction signal processing to audio prior to sending it to the service typically reduces the accuracy of the speech recognition, and the service is, after all, designed to handle noisy audio anyway. So best practice here dictates that, again, place the microphone as close as possible to the person speaking, especially when there's background noise. Avoid audio clipping. Don't use automatic gain control. Disable all noise reduction processing. And sample some of the sample audio. It should be clear with no distortion or unexpected noise. In this demo, we'll invoke machine learning APIs. First step is to log into your Google Cloud Platform account. And I've done that here. So now I'm going to click on the burger menu at the top left. And I'm going to point to APIs and services. And I'll go to library. So I'm going to click on library here. Now I'm going to search for the API that I want to play with. So I'm going to type, first of all, Vision. And there's the Google Cloud Vision API tile. It's the only one that shows up now. So I'll click on that tile. And you can see I can enable it here. If I click on Try This API, I'll get additional documentation. But scrolling down under Tutorials and Documentation, if you click on Learn More, this will allow you to scroll down and actually play with it. Now I've already got this tab open, and I'm not going to search for each individual API. So you can see I've got the API, the Vision API open here. That's just cloud.google.com/vision and natural language. Notice it's the same URL with the natural-language route, and translate is just the translate route, and speech is just speech route. Okay, so let's play first of all with the Vision API. So on this page, I can either drag a file from my computer or browse the computer for a file. So let's click on this tile, and you'll see now I've got this image here in the working folder for this video. So I'm going to click on that, click open, and now it's going to analyze that image. And this is pretty cool. So look at the labels that it put on it. Sea, sky, reflection, coast, water, ocean, shore. So cool. Under the web tab, we see any web entities related to this image. And we can see some properties for the image. And under safe search, we see that it's not likely that it's adult material or spoof or medical or violence or racy. Okay, so very unlikely for all four of those. And then under the JSON tab is the JSON representation of this image and the data associated with it. Next, let's look at the natural language API. So I'll click on this tab. And again, that's just cloud.google.com/natural-language. Now, let's scroll down. And we can try the API by putting some text in here. So why don't we just grab this text? So we'll highlight this text here by holding down the mouse key, right-clicking, selecting copy, And let's replace what they've got in here. So Control V to paste this in. And now let's click Analyze. And then now you can see the entities, okay? And under Sentiment, you can see the sentiment for the entire document, as well as entity level sentiment, syntax, as well as categories. All right, now let's look at the Cloud Translation API, and that's just cloud.google.com/translate. So here we're going to try the API. So if you scroll down, you'll find this source here is Chinese. Now when you click inside this field, you're going to have to select I'm not a robot from the reCAPTCHA here. So I'm going to click on that. Okay, and now let's just remove this. And what we'll do is we will select French. Okay, so let's enter our own text. How about Allô le monde? And you can see that it translated on the fly, hello world. Very cool. Now, if you click the down arrow here beside each of these, you'll see the request URL as well as the JSON response. Under detect language, you'll see that the language detected was French anyway, even though we specified it. And supported languages include all of these languages. Okay, so now let's look at the speech API. And this is located at cloud.google.com/speech. And now what we can do is we can start translating right now with our streaming audio. So I'm going to click Start Now. And the first time you do this, you should see a request from your browser that will ask you to enable your microphone for this API. Okay, so you see how that works. Very cool, very cool. So let's look at this. So here's what I said. And the first time you do this, you should see a request from your browser that will ask you to enable your microphone for this API. In this demo, we'll demonstrate the use of machine language REST APIs. The first step is to enable the API you're going to use, and for this one we're going to use the Translate API. So for that, click on the burger menu. So assuming you've logged into Google Cloud Platform with your Google Cloud Platform account. So I'm going to click on the burger menu. I'm going to point to APIs and services, and then I'm going to click Library. Now I'm going to search for Translate, and there's the Google Cloud Translation API. So I'll click on that tile. And now I'll click on Enable. And make sure that you have the right project selected. So I'll click Enable. Okay, so that has been enabled now. The Translation API has been enabled for this particular project. Now the next step is to create a new service account and generate an API key to use in the Cloud Shell so that we can access the API. So for that, let's click on the burger menu again, point to APIs and services, and now we'll click on Credentials. Now click Create Credentials. And what we're going to do is we're going to create a service account key. So I'll click on Service Account Key here. And for the service account, click the down arrow. This is going to be a new service account. So I'll just call this My Service Account. We won't specify a role. And we see that it generated the service account ID. And now the key type, we're going to specify JSON here. So let's click Create. And it says service account has no role. So click on the down arrow, select a role. And now we'll select project owner, and select create. Okay, so private key was saved to this local computer. So I'll click close here. And I'm going to close the notification across the bottom of my browser. And now what we'll need to do is we'll need to use that key wherever we're going to try to access the API from. And what we'll do is we'll access the API from Google Cloud Shell. So to activate Google Cloud Shell, in the toolbar, click on Activate Google Cloud Shell. And now that's provisioning my Google Cloud Shell machine. I'm going to click the Open a New Window icon here to pop that out into a new tab. Okay, so now it's activated, so I'm going to type clear to clear that. And now what I'll do, I'm going to open the README in my Notepad++, any text editor will do. And this is the command that we're going to use first. We're going to set the default project. So if you have multiple projects, just to make sure that you have the right project, you can set the default project. So I'm going to highlight that, right-click, select copy. I'm going to go over to Cloud Shell here, and I'll paste that in. And we'll specify this project. For me, it's GCD-2019. Okay, so now I've set that project as my default project. I'm going to type clear and press enter again to clear that. And now the next thing we need to do is we need to authorize the service account by using our key file. And what we're going to do is first we're going to click on the More icon here in Google Cloud Shell, click on Upload File, and I'm going to go to Downloads, and I'm going to click on the downloaded JSON key here. So I'll click on it, click Open. Okay, so now that's uploaded to my home directory. So if I do an ls, I'll see that here. And while we're at it, let's just highlight that. You see the little scissor notification. That means that that has been successfully copied. Okay, so now let's type clear again, press enter to clear that. And now what we need to do is type gcloud auth activate dash service account. And we specify a key file by using the -- key - file flag equals, and we can point to that file. Okay, so that's done. So now we can access the API. So we enabled the API, the translation API for this project. Then we created a service account and generated an API key so that we can use Cloud Shell to access our API. So let's go over to the README again and look at what we're going to do here. Okay, so now what we're going to do is use CURL to make a post request to the translation API. So we're going to translate this, hello world. The source language is English, target is French, the format is text, and Q, that's the document or the text that we're going to convert. And the CURL command is just using -s for silent, -x because we're going to execute a post request, and -h for the header data. Okay, so let's copy this. So I'll highlight the CURL command. Oh, and one last thing. This is where we're pointing to. This is the translation API. So let's highlight that, right-click, select copy, and if it works right, then we should see hello world translated into French. So let's go back to Cloud Shell. We'll click inside Cloud Shell, press Ctrl-V to paste our CURL command, and press enter. All right, and you can see here that the response body returned exactly what we were expecting. So it was translated from English into French. In this demo, we're going to use Cloud Vision API and Kubernetes to label or classify images from Reddit's AW subreddit, and will display the labeled results in a web app. The AW subreddit is a subreddit for cute and cuddly pictures. So there's three components here. We have a minimal Redis instance, we have a web app to display the labels along with their associated images, and a worker that scrapes Reddit for images and classifies them using the Vision API. This demo uses multiple worker instances, and Cloud Pub Sub is used to coordinate tasks between them. So the first step is to activate Google Cloud Shell. So click on the Activate Google Cloud Shell icon in the toolbar, assuming that you're logged in to your Google Cloud Platform account. Okay, and you can see that's up. I'm going to click Open in New Window to pop that out into a new tab. While it's doing that, just have a look at this tab. This is the subreddit that we're going to be scraping. Okay, so first let's get us started by creating a new alias for clear, because I'd like to clear after each command. So type alias C equals clear. So now every time I type C, that will clear my Cloud Shell. Okay, next, gcloud auth list, and this will see whether we're authenticated or not, and you can see that we are. I'm authenticated with my account here, and if you're not, you can just set the account this way with gcloud config set account and your account specification. So I'm going to clear that by typing C and pressing enter again. Now I'm going over to the README for this demo, and you can see those commands here. Okay, so the next command we're going to issue is gcloud config list project, and this will tell us if we're using the right project. So I'm going to highlight this command, right click, select copy, back over to Cloud Shell. I'll click inside here and press Control V to paste that command and press enter. Okay, and you can see that I'm in this project, and that's the project that I'm targeting, so that's good. So I'll type C and press enter to clear. And now the next thing that we need to do is enable the Vision and Kubernetes APIs. So let's go back over to the Google Cloud Platform console. I'll click on the burger menu, point to APIs and services, and click library. Now you can search for the APIs. So for here, I'm going to search for Kube. The Kubernetes Engine API tile appears. I'm going to click on that, and you can see that I've already enabled this API. So I'm going to go back, and now I'm going to search for Vision. And now the Cloud Vision API appears. I'll click on that tile, and I'll click on Enable, and now it's enabling that API. Okay, the API is ready. Now let's go back over to the README again, and now we're at this point. We want to set up Kubernetes, and what we're going to do is first we set up the default compute zone, and we're going to use US West 1-A. So I'll highlight this command, right click, select copy, over to Cloud Shell. I'll click inside here and press Control V to paste that command. And so the property has been updated. Type C and press enter to clear, and back over to the README again. So this is the command that we're going to use to create the cluster, and it's going to be created in the default zone. We're not specifying the zone here, but we're specifying the scope. And we're specifying the scope because what we want to do is we want to use Cloud Platform Scope to allow access to the Pub Sub and Vision APIs. So let's go ahead first, and we'll highlight this command, right click, select copy, back over to Cloud Shell. I'll click inside here and press Control V, and now we'll create that cluster. Okay, so now it's creating that cluster. Now this can take a couple of minutes, so while it's spinning up, I'm going to pause the video, and then when it's done, I'll resume. Okay, our cluster is up and running, so we'll type C and press enter to clear that. And now just to verify everything, we can type kube control cluster-info. Okay, and our master is running and everything seems to be running. Awesome. Okay, so let's clear this by typing C and pressing enter. Okay, and now let's bring in some sample data. So we'll use Git to clone the Cloud Platform Cloud Vision repository. I'm going to go over to the README, and this is what we're doing now. So we're going to bring in that data by cloning this repository. So let's highlight that, right click, select copy, over to Cloud Shell, Control V to paste that in, and let's clone that repository. And it's done. So now if I type ls, I'll see a Cloud Vision directory there. And what we're going to do now is we're going to cd into Cloud Vision Python Vision. Okay, and now we're going to build and deploy everything by running make all. So that's make all. What's happening here is that Docker images are being built and deployed to the Google Container Registry, and the required YAML files are generated from templates. The YAML files are configured with information specific to the project and then used to deploy the Redis web app and Worker Kubernetes resources for this demo. And once that's deployed, what we'll do is we'll type kubectl get pods to have a look at the pods and make sure that the Kubernetes resources are up and running. Okay, so it's done. So we'll type C, press enter to clear. And again, kubectl get PO for pods. And we can see that our Redis master is running and these other containers are not quite ready yet. And we need those to be ready before we check the deployment. So we'll just clear this by typing C and pressing enter. And we'll up arrow to bring back the get pods command. Okay, and we can see that the web app container is now running. And now they're all running. So let's type C and press enter. Okay, now we'll type kubectl get deploy for deployments -o for output y. So we'll get some additional info here. Okay, so you can see our deployments. You can see the desired and current number of replicas there. Okay, so let's clear this. Type C and press enter. And now we'll type kubectl get service, and we want to get the AWW Vision -web app service because we want to get our external IP. Now I can see I've already got the external IP here. If you don't see an IP address, just give it a couple of minutes because sometimes it can take a couple of minutes for that to show up. Okay, so now that's copied. Let's go over and open a new tab. We'll right click, select paste and go in the address bar, and there's our app. And we'll click start the crawler. And it says crawler started, images should start appearing. So let's click go back, and there are our images. And you can see the labels, and each has associated images with it. And there you go. So we've successfully used the Vision API with the Kubernetes cluster to scrape this subreddit for cute and cuddly pictures. In this exercise, you'll practice what you learned about Google Cloud Platform Machine Learning APIs. You will describe the Cloud Machine Learning Engine, describe the machine learning workflow, define the Vision API and its purpose, describe the Natural Language API, and demonstrate the Translation REST API. Now pause the video and perform the exercise, and when you come back, we'll go over these exercise tasks. Okay, task 1, describe the Cloud Machine Learning Engine. Basically, the Cloud Machine Learning Engine does two things. It allows for the training of machine learning models at scale by running TensorFlow training applications, and it hosts trained models in the cloud, providing the ability to use them to obtain predictions about new data. One of the key aspects in creating a machine learning solution we learned is training an application with TensorFlow. With the trainer package and data ready, the next step is to use Cloud Machine Learning Engine to train the model. And once that's done, the trained model can be output as a model resource, then deployed as a hosted model version used to obtain predictions for new data. The Cloud Machine Learning Engine provides two types of predictions, online and batch. Online predictions are optimized to handle a high volume of requests while minimizing latency, while batch predictions are optimized for making inferences based on large amounts of data. At the heart of the Cloud Machine Learning Engine is the REST API. It's comprised of a set of RESTful services that manage jobs, models, and versions, and enables predictions to be made on hosted models on the Google Cloud Platform. We learned that many Cloud Machine Learning Engine tasks can be performed using gcloud command line, and models and versions may be managed from the Google Cloud Platform console, providing a graphical interface for working with machine learning resources. We also learned that Google's Cloud Machine Learning Engine functionality is integrated right into Cloud Data Lab. Next task is to describe the machine learning workflow. And we learned that machine learning workflow begins with a problem that is well defined. And we learned that it is an iterative process that requires tuning and adjustment. And the goal is to end with a predictive mechanism to make predictions with new data. And data patterns, which may not be obvious at the outset, are key to problem resolution. Large amounts of data are typically required to make valid inferences based on the data. We also learned that the large dataset includes the attribute, which is also known as a feature. We learned that the final collection of settings and configurations are known as hyperparameters. We also learned that considerations should be given to understand the problem first. The problem must be well defined. We also learned that we should consider whether machine learning is the best approach. Is there a simpler, more suitable approach? And we also learned that you should consider, how do you know when you are finished? That is, you can continually tinker and tune your model, obtaining incrementally small improvements in accuracy, but you need to decide how accurate you need to be. Using machine learning effectively, we learned, comes down to preparing so that you have good data. And this means understanding the data thoroughly. It may require aggregation, and using tools to visualize the data to see if there are any noticeable trends or patterns. Finally, clean the data of anomalous values, particularly paying attention to those that may be a result of data entry or measurement errors. The last step to preparing good data is pre-processing, and this may require normalization, eliminating redundancies, applying formatting to the data, for example, removing HTML tags, and assigning key values. We learned that you can use Cloud Data Lab for some aspects of the data exploration and prep, but there are other cloud platform services that can be used as well, such as BigQuery, Cloud Dataprep, and Cloud Dataflow. Continuing on with machine learning workflow, once the data is well understood, models can then be designed to use that data to predict target values in the new data. Each model will undergo a series of steps to make corrections and refinements. So first, develop the model using TensorFlow, train the model with data for which you already know the target values, and the model will predict target values based on the training data, and the model can be adjusted for more accuracy. Then we evaluate the trained model by using data that includes target values, and make adjustments to the model, changing operations and/or settings as required. Finally, model deployment and testing. To test the model, give it data in a way that mimics its eventual final application. A different data set should be used for testing. than that used for training and validation, using a different data set every time. As the model is tested, it should be connected to the application's infrastructure, and adjustments may be made as necessary based on the results derived from testing. And test the model by requesting predictions using the Cloud Machine Learning Engine. Next, define the Vision API and its purpose. And we learned that it is a REST API. It's an interesting application of machine learning that performs analysis of images, and it performs object detection within images, as well as face detection, but not facial recognition. It uses optical character recognition to recognize and read printed words and text within images, and couples that ability with automatic language detection supporting a wide range of languages. And using machine learning models, Google has indicated that results will improve over time as accuracy improves and new concepts are introduced. Next, describe the Natural Language API. We learned that the Natural Language API provides a number of methods for performing analysis and annotation on some given text. There are multiple levels of analysis, and each delivers valuable information for understanding language. So we went over these main methods, like sentiment analysis, which can inspect a set of text and identify the dominant emotion exhibited by the author within that text. Then syntactic analysis, using the analyze syntax method, and that's used to extract syntactical information from text. It can divide a set of text into a series of sentences and tokens, which are then evaluated to determine their syntactic meaning within the text. And content classification, using classify text method, we can analyze text content and return a list of related content categories. Analyze entities method is used to examine a set of text for familiar entities and provide information about those entities. And we learned that there are two broad categories of entities: proper nouns like specific people or places, and common nouns like restaurant, building, and so on. And entity sentiment analysis. The analyze entity sentiment method examines text for familiar entities and returns information about those entities, similar to the analyze entities method, but it also identifies the dominant emotional state or opinion of the entity within the text. And finally, demonstrate the Translation REST API. So for this, first you need to enable the Translation API. So let's go to APIs and Services. We'll go to Library, and let's search for Translation. And there it is. So we'll click on the Google Cloud Translation API, and you need to enable it. Now I've already enabled it, so now if I click on this button, I can manage it. So I'll click Manage. And you also have to create a new service account and generate an API key to use in Cloud Shell to access the API. So if I click Credentials here, I'll see that service account right here. When you create that service account, it downloads the JSON representation of that key. And then you upload that key and use Google Cloud Shell to perform the post request to the Translation API. So I've opened up Google Cloud Shell already, and recall that we set up the config default for the project, and you can see that I'm already connected to this project anyway, so I don't have to do that. And then you need to set the authorization in order to use the API. And to do that, you need to know your key file and the location of that key file. And I uploaded it using the more icon and clicking upload file and uploading that JSON file. So now if I type ls, I can see that file here. And there it is. So I'll highlight that to copy it. And then I'll just type gcloud auth activate dash service dash account dash dash key dash file equals, and Control V to paste that key in, and now I'll press enter. Okay, so the credentials have been activated. So let's type clear and press enter to clear that. And now let's go over to the README for this exercise. And this is the CORL that we're going to use to make our post request. So let's highlight this, right click, select copy, and basically what we're going to do is we're going to translate hello world, that's the content, from the source language, which is English, to French, and the format is text, and here's the API endpoint. Okay, so over to Cloud Shell. I'll click inside here, Control V to paste that in, press enter, and in the body of the response we see here that it did indeed translate that text. Bonjour le monde. In this video, we'll present a very high-level overview of data pipelines using Apache Beam's Python SDK. Apache Beam's Python SDK is, as you've probably guessed, used for application in a Python development environment. One thing about the Python SDK is that even though Python is a dynamically typed language without static type checking, the SDK uses type hints when you are creating a pipeline and at runtime in an attempt to mimic the correctness guarantees that are typically involved in static typing. At pipeline creation, you start by importing Apache Beam and pipeline option classes. Then you instantiate a pipeline object specifying any options like the project ID, the runner, as well as where you want to store the files. You then create a P collection and apply any transforms that you need for your data. At this point, you're ready to also specify any additional outputs required. In this video, we'll conduct a very high-level overview of building data pipelines using Apache Beam's Java Software Development Kit. Apache Beam's Java Software Development Kit delivers an API for the creation and management of pipelines using a Java API. The Java Software Development Kit supports all features that are supported within the Beam model. And to create a data pipeline with the Java Software Development Kit, you start by creating a pipeline object based on any options you specify. For example, you can configure the pipeline runner as well as runner-specific configuration required by whatever runner you're using, as well as other options like project ID and file storage locations. Then you read data into the pipeline using a P collection from an external or local data source. You then apply transforms to manipulate any data as required, and once all the transforms defined for your pipeline have been applied, the last step is to write or output the results by writing the pipeline's final P collections. This actually involves applying a write transform to a P collection. A write transform can write output to an external data sink, like a database table, and you'll typically do this at the end of your pipeline, although you can output a P collection anywhere in your pipeline. In this demo, we'll initialize Cloud Dataprep. So assuming that you've logged into the Google Cloud Platform with your account, what we'll do first is we'll create a new project. So at the top of the screen, click the drop down for the project that's currently selected by default. And in the select dialog that appears, click the Create Project icon. And now let's name this project Dataprep-demo-1 and click Create. Now let's make sure we select that project once it's done being created. So you can see it's still creating that project right now. Okay, so it's done. So let's click on it, and now we've selected that project. Now the next thing we need to do is enable Cloud Dataflow, BigQuery, and Cloud Storage APIs. So in the GCP menu, click APIs and Services. And let's click Enable APIs and Services. And first we'll look for Cloud Dataflow. So we'll just type Dataflow. And there it is. And we'll click Enable to enable this API. Okay, so the Cloud Dataflow API has now been enabled. Let's go over to Libraries. And now let's search for BigQuery. And you may already have both of BigQuery and Cloud Storage APIs enabled. So I have this API already enabled. So let's go back to the library and now we'll search for Cloud Storage. Here's the Cloud Storage API. Let's click on it and you can see that that one's already enabled as well. So the next step is to create a Cloud Storage bucket in the project. So in the main menu, under Storage, so we'll scroll down and under Storage, point to Storage and click Browser. And now click Create Bucket. And we have to give this a unique name. So we'll call this Dataprep -bucket -1. You can leave the default storage class at multi-regional and the location by default, which is United States, so we'll leave that and click Create. Okay, so now it's time to go and initialize Cloud Dataprep. So let's open Cloud Dataprep, and it's located in the GCP menu under Big Data. So we'll scroll down under Big Data. At the bottom, we'll see Dataprep here. So let's click on that. Okay, so now the first time that you open Cloud Dataprep, you may be asked to accept the terms of service, so you just select yes to those. You might be asked to sign into your Google account. I've already done this once already, so it's not asking me to do this. It'll also ask to choose a cloud storage bucket to use with Dataprep, and you'll also be asked to allow Trifecta, which is a third-party application host, to access your project data. So let's click Allow here to allow Trifecta to access the project data. Okay, now first time setup, it's asking us to choose a cloud storage bucket to use. Let's not use the default one. Let's click Change here. And we'll click Dataprep-bucket-1 that we just created. Select Use this folder. And in first time setup, click Continue. Okay, and now with that completed, the Cloud Dataprep homepage opens to the Flow screen, and you've now successfully initialized Cloud Dataprep. In this demo, we'll ingest data for use in Cloud Dataprep. Okay, assuming that you've initialized Cloud Dataprep, open the Cloud Dataprep homepage and make sure that you've got the project selected that you enabled or initialized Cloud Dataprep with. So click on the burger menu, scroll down, and under Big Data, we'll see Dataprep. So let's click on Dataprep, and this will open to the Cloud Dataprep homepage. And the next step will be to create a flow. Cloud Dataprep uses a flow workspace to access and manipulate datasets. So from the flow screen, we'll click Create Flow. And for a flow name, we'll be using 2016 U.S. Federal Elections Commission for 2016 data. So we'll name this flow US-FEC-2016. And now for a flow description, let's just enter something simple like clean US-FEC-2016 data, and then click Create. Okay, so now we have to ingest some data. So let's add some data sets by clicking Add Datasets. And on the Add Datasets to Flow, you can see that we've got a couple of these already selected. They are showing there because I've already done this for practice. But let's click on Import Datasets. Okay, and on the left here, we could either upload, we can use BigQuery, or we'll select for this demo, GCS, for Google Cloud Storage. Now, click on the Edit Path icon, the pencil icon beside GCS. And now for choose a file or folder, we'll specify Dataprep -samples/us-fec, and we'll click Go. And we're going to add this dataset, CN 2016.txt. This is the candidates data, so let's click the plus icon next to that. You'll see it appear over here. So let's just give this a more descriptive name. Let's call this candidates-2016. And then scroll down in the list and we'll choose itcont-2016.txt. This is the campaign contributions for 2016. So let's click the plus icon to add that. And we'll give this the name contribs-2016. And now we'll click on Import and Add to Flow. Okay, so now we've got our Flow workspace set up. So we've got our candidates data and we've got our contributions data. So we've ingested data or imported it into our flow so that we can now perform our cleaning or any extract, transform, and load operations that we want to apply. In this demo, we'll configure recipes with Cloud Dataprep. Assuming that you have initialized Cloud Dataprep, created a flow called us-fec-2016, and imported some data, it's time to start transforming that data. We do that by using recipes, which are just a collection of data wranglers. Wranglers are processing steps that come from Trifactor Wrangler, which is part of Cloud Dataprep. So let's go over to Dataprep. So we'll click on the burger menu, scroll down, and under Big Data, we'll click Dataprep. Okay, we can see the flow that we created here, us-fec-2016. So let's click on that. And we'll see our two data sets. So click on Candidates 2016. And now we'll click Add New Recipe. And now we'll click Edit Recipe. And this opens the grid view where we can explore our data and apply whatever transformation steps we want to the recipe. If you don't see the recipe pane, just click on the recipe icon at the top of the screen here, and now you can see the recipe pane. Okay, so the first thing to look at is column 5. And these are the years. So what we'll do is we'll just select this range, 2015 to 2019. So we'll click on that. And you'll see here, keep rows where the value is in the selected range. So we'll click Add. And that adds the recipe step here. We can see that. Keep rows where date 2015, comma 1, comma 1, less than equal to column 5, and column 5 less than date 2020, comma 1, comma 1. Okay, so let's apply another step to our recipe. In column 6 here, just scroll over a little bit by grabbing the scroll bar at the bottom. We'll see that we have this red part on our bar that shows that we have some mismatched values. So let's click on that. And now if we scroll down near the bottom, we'll see the mismatched values. And the reason that they're mismatched is because it's looking for state data, which is indicated by the flag here, and it's also got US data. So what we're going to do is we're going to click State, the flag icon, and we're going to click String to change that to a string. Now if we click the recipe icon again to see the recipe pane, we'll see that we've got that second step with our recipe. So let's click the name of our flow again up here at the top in the banner to go back to our data sets. Okay, so what we can also do is we can apply a join, for example. So if we were to click on contribs and add a new step here, we'll click edit recipe, and we can look at our data, and let's expand the recipe pane again. And now if we want to apply a new step here, just click on add new step, and this will allow us to select whatever transformation that we want to make. So let's say that we wanted to do a join. So scroll down and select join, or just search for join. So we'll click join. Now if we wanted to join candidates 2016, we would just click on candidates 2016 and click preview. And there we can preview our data. Now click on join keys, and you'll see that it's got some key selections already. So if we wanted to edit that, let's click edit, and we'll click the pencil icon beside column 11. We'll select column 2, and beside column 6 we'll click the edit icon again, and we'll select column 11, and we'll click save. Now that is our candidate IDs, right? So it will match on those. So what we'll do actually is we'll cancel out of this. I don't want to add this to the recipe because this would take a long time to process this job. So I'm going to click cancel here. I'll click the name of my flow again up here. And now I'll just delete this recipe. So this is what we're going to do. So if I click on this ellipsis here, I can click create output to run and click run job. And in the run job on Dataflow, I'll click run job. Okay, so it started that job. Now if I go up here to the top and I click on jobs, I can see this job that's running. So clicking the ellipsis, the more icon, we'll click view Dataflow job. And now we see the details for this job. Okay, so there's all of the steps that it's going to perform. Now this is going to take some time, so I won't let it finish, but you can get all the details and information about your job over here in the job pane. And you can also look at individual steps. So that's basically creating a recipe with Cloud Dataprep. In this demo, we'll look at importing and exporting flows and running Dataflow jobs in Cloud Dataprep. For this demo, I'm assuming that you've initialized Cloud Dataprep, created a flow called US-FEC-2016, imported some data, and created a recipe. So let's go over to Cloud Dataprep. Click on the burger menu, scroll down, and under Big Data, let's click on Dataprep. Okay, and on the home page we can see the flows here. So here's my US-FEC-2016 flow. So if I click on that, I'll see that I have a recipe here. If I click on that, I can see the steps in my recipe. Now if I click on jobs, I'll see any jobs that have been run or completed, and you can see that I've got one completed job. So let's go back to flows. Now one other thing you can do is you can export and import flows. To export the flow, just simply highlight the flow or mouse over it, click the more icon, the ellipsis, and click export. And when you choose to export, you enter some additional notes and then click download, and it will download to your downloads folder for your browser. Likewise, you can also import flows by clicking the more icon or ellipsis beside create flow and select import flow. It will then ask you to navigate to wherever your file is located, and it will be a zipped archive file, and then click choose a file or drag and drop it here and it will upload to Cloud Dataprep. Okay, so let's click on this flow to open it. And now let's click on the Run Job icon. So we'll click Run Job. And we'll see the job here. Now let's click Run Job. And now you can see that that's running. So now if we click on Jobs at the top here, we'll see the running job. To see details about the job, just mouse over the job, click the More icon, and click View Dataflow Job. And now you can see some details about that job. And in the job pane on the right, you can see a summary of the job, some auto-scaling, resource metrics, pipeline options, and just a whole lot of data about your job. So let's close this tab. We'll go back. And this takes a couple of minutes. So what I'm going to do is I'm going to pause the video, and then when it's done, I'll resume. Okay, so the job has completed. You can see the finished jobs by looking at your completed jobs. So if I click on complete, that's all I will see here is complete, or all shows you all jobs. So I have 2 jobs here, and under the latest run, what I'll do is I'll click on this link, and this will take me to the results. Okay, so I can see the details over here in the details pane. And now if I click on the More icon, I can look at results, the Dataflow job itself, steps and dependencies, or I can even export the results. So I'll click on View Results here. And now this shows me the results from my job. So this applied all the steps in the recipe. And if I want to view dependencies, I'll click on View Dependencies. And now click on a recipe to view steps. So I'll click on the recipe, and I can see the steps for this recipe. And if I click on Display Wrangle, it'll display the steps in Wrangle language. In this video, we'll consider MapReduce process versus Cloud Dataflow. App Engine MapReduce process is a programming model that is used for processing huge volumes of data using distributed parallel processing. It is especially effective for handling large, long-running tasks that require multiple requests, such as analyzing application logs, aggregating data from external sources, applying transformations to alter data formats, as well as exporting data to use for external analysis. MapReduce is a community-maintained open source library that's built on top of Google's App Engine. It is no longer supported, however, by Google. Instead, Google recommends using Cloud Dataflow, which is, of course, supported, and extends the functionality provided by MapReduce. Some of the benefits of migrating from MapReduce to Cloud Dataflow include the fact that it's supported by Google. So that means you can perform, for example, data analytics with Google BigQuery. You can obtain maintenance and updates automatically, of course, since it's supported by Google. And you can also use Google Cloud Storage. Other key benefits include benefits accruing to job scheduling. So for example, you can schedule recurring jobs using App Engine cron. You can use Cloud Dataflow templates. This allows you to stage pipelines in Google Cloud Storage, which also allows you to execute them from several different environments. And it supports Apache Airflow, which is a platform that allows you to programmatically write, schedule, and monitor workflows. With respect to job monitoring, you can use Cloud Dataflow web-based monitoring tools, as well as Stackdriver monitoring, which provides further information regarding your pipelines. With respect to I/O connectors, Cloud Dataflow has I/O connectors for several Google Cloud services like BigQuery, Cloud Bigtable, Cloud Data Store, as well as others. In this video, we'll consider serverless architecture and data analytics. First, let's look at serverless architecture. Full management of servers in the serverless architecture eliminates repetitive tasks and potential errors that are inherent in tasks like scaling clusters and applying security patches. There are no upfront provisioning requirements. In fact, resources are allocated dynamically as needed. With automatic scaling and dynamic provisioning of resources, you pay only for what you use. Now let's talk about the key benefits of serverless architecture. First, you have lower infrastructure costs because you don't have to commit to a specific deployment size, so no upfront costs involved. Operations cost reduction by virtue of the fact that with serverless, you are automating repetitive provisioning and management tasks. And since you no longer have to spend valuable time doing that, it means you have more time for those higher value DevOps tasks, which means that you get to market faster with higher quality products. With serverless architecture, you can design cost-effective microservices which significantly reduce management and infrastructure costs over traditional services. The new breed of large data centers are a significant departure from traditional hosting facilities. They're no longer seen as just a collection of co-located servers. Much of the hardware and software resources that exist in the new breed of data centers must be orchestrated to work together to effectively and efficiently provide enterprise-grade internet service performance, which is only accomplished using a holistic approach to data center design and deployment. Consider some key use cases. For web and mobile, you can use Firebase. For microservices, use Cloud Functions and Data Store. For web backend, App Engine and Data Store. For ETL, use Cloud Dataflow and BigQuery. For Internet of Things, Cloud PubSub and Dataflow. You can easily perform analytics with BigQuery and create bots with Cloud Functions. Key products include, for application development, we're talking App Engine, Cloud Storage, Cloud PubSub, Service Endpoints, as well as Cloud Functions. And since we're talking about data analytics here, for data analytics we have BigQuery, Cloud Machine Learning Engine, as well as Cloud Dataflow. In this exercise, you'll practice what you learned about Apache Beam, Dataflow, and Cloud Dataprep. You will describe Apache Beam concepts and SDKs, describe MapReduce, describe serverless architecture, demonstrate Cloud Dataprep, and this includes data, flows, and recipes. Now pause the video and perform the exercise, and when you return, we'll go over these exercise tasks. Okay, task 1, describe Apache Beam concepts and SDKs. First, understand that Apache Beam is used for creating and managing parallel processing pipelines. It supports both batch and stream models. It's open source software from Apache, and is supported using one of the supported Beam software development kits or SDKs. So you execute the pipeline using one of Beam's supported distributed processing backends, which in the context of this course is Cloud Dataflow. Key use cases include embarrassingly parallel or perfectly parallel data processing tasks. Another use case is that Apache Beam is good for extract, transform, and load tasks, as well as data integration tasks. Regarding the software development kits, Beam provides both Java and Python development kits. Beam SDKs utilize the same classes for both bounded and unbounded data, and can perform data transformations on virtually any size data set. Beam is very flexible, allowing you to tailor your data processing to your needs. And pipeline runners translate the data processing pipeline defined in a Beam program into a compatible API based on the distributed processing backend, which again here we're talking Cloud Dataflow. Task 2, describe MapReduce. App Engine MapReduce is a programming model that is used to process huge volumes of data using distributed and parallel processing. It's particularly effective for handling large, long-running tasks that require multiple requests, such as analyzing application logs, aggregating data from external sources, exporting data to use for external analysis, and applying transformations to altered data formats. MapReduce is a community-maintained open-source library that's built on top of Google App Engine, and it's no longer supported by Google. Google recommends using Cloud Dataflow, which is supported, and in fact, it extends the functionality provided by MapReduce. Task 3 describes serverless architecture. Serverless architecture means simplified server management. What that means is full management of servers provided by Google eliminates repetitive tasks and potential errors that are inherent in tasks like scaling clusters and applying security patches. Resource provisioning means no upfront provisioning is required, so resources are allocated dynamically as needed. With automatic scaling and dynamic provisioning of resources, you pay only for what you use. You should understand some of the key benefits of serverless architecture, so I've included those here. For example, lower infrastructure costs are incurred because you don't have to commit to a specific deployment size, so again, no upfront costs involved. Operations cost reduction is achieved by virtue of the fact that with serverless architecture, you are automating repetitive provisioning and management tasks. And since you no longer have to spend valuable time doing that, it means that you and your team can spend more time on those higher value DevOps tasks, which leads to getting to the market faster with higher quality products. And with serverless architecture, you can design cost-effective microservices which significantly reduce management and infrastructure costs versus traditional services. We also spent a moment talking about holistic data centers, and that is that the new breed of large data centers are a significant departure from traditional hosting facilities in that they are no longer seen as simply a collection of co-located servers. In fact, much of the hardware and software resources existing in this new breed of data centers are orchestrated to work together to effectively and efficiently provide enterprise-grade internet service performance, which is only accomplished again by using this holistic approach to data center design and deployment. Now let's go over to the browser and demonstrate Cloud Dataprep. Okay, so for this demonstration, basically we created a project and then we created a storage bucket. So if I click on the burger menu here and scroll down under storage, point to storage and click browser, and you'll see here's the Dataprep bucket that I created. So to create a bucket, you just click create bucket, give it a name, leave the defaults and click create. Okay, going back to the burger menu, scroll all the way down and under Big Data, we'll find Dataprep. So click on Dataprep. And for Cloud Dataprep, what you do is you define some data or import some data to use. In Cloud Dataprep, you create a flow, and then you ingest or import some data, and then you create recipes against that data to transform it. So you can see that I've got a flow here, and to create a flow, you just click Create Flow, give it a name and a description. Now click Cancel, and we'll go and have a look at this flow. So I'll click on this flow, US-FEC-2016, and you can see the data here. So these are two data sources that I've imported, and you can see some recipe steps here in this flow. So if I click on this recipe step, that will bring up this recipe here. Now if I want to edit the recipe, I can click Edit Recipe, and if you don't see the recipe pane, just click on the recipe icon in the banner, and now you can see the steps in this recipe. So to create a new step, you just click on New Step, and you can search for whatever transformation that you want to apply, select it, and then enter the details for that transformation step. Once you're done all that, you can run a job by clicking Run Job, and that will bring you to the Run Job on Dataflow page. where you can click on Run Job to run that job again and perform any transformations that you created with your recipes in that flow. In this video, we'll explore how datasets are used in Google Cloud Platform. On Cloud Platform, you organize, manage, and control access to tables and views using datasets. You create a dataset in BigQuery, and the dataset name must be unique at the project level. You provide access to tables and views using project-level IAM roles and dataset-level access controls. So there is no direct access control to tables and views. Rather, it's done at the project level and dataset level. Project-level access controls can be used to define the users, groups, and service accounts granted access to all datasets, tables and views, and the table data within a project. Dataset-level access controls define the users, groups, and service accounts granted access to the tables, views, and table data within a specific dataset. Information about a dataset is retrieved using the API, the command line tool, or by using the BigQuery web user interface. Permissions required include the dataset level reader primitive role, and at the project level, IAM roles that include the BigQuery.datasets.get permissions. Listing datasets, likewise, can be performed using BigQuery web user interface, the command line tool, or the API. So for example, using the command line tool, you issue a BQ space ls CLI command, and via the API, you use the BigQuery.datasets.list API method. You can update dataset properties, and these include access controls, labels, descriptions, and new table default expiration times. You can also delete datasets, and the permissions required for updating and deleting include the dataset level owner primitive role, as well as the project level IAM roles that include BigQuery.datasets.update permissions for updating and BigQuery.datasets.delete permissions for deleting. Renaming datasets can be done, but it's not directly supported in Cloud Platform. The workaround is to create a new dataset with the new name, copy the tables from the old dataset to the new one, recreate any views in the new dataset, and then to avoid incurring additional storage charges, delete the old dataset. BigQuery has special tables called metatables that contain metadata like the list of tables and views in a dataset. Metatables are read-only. So for example, to retrieve metadata about the tables and views in a dataset, use the _tables_summary__ metatable in a select query. In this demo, we'll configure a dataset for cloud machine learning. I've opened up my Chrome browser and I've logged into my Google Cloud Platform account, and I'm going to be using this project for this demo. The data files we'll be using are named adult.data and adult.test. These data files are hosted in a public cloud storage bucket. The data itself is public census data regarding income. For this demo, we'll copy them to a local Google Cloud Shell environment. So first, let's go ahead and open Cloud Shell. So in the toolbar, I'll click on the Activate Google Cloud Shell icon. And while that's opening, I'll click on Open in New Window. Now we're copying those data files to a local Google Cloud Shell environment because doing that allows us to use the data for local training. And it's always a great idea to get the trainer running locally before running it in the cloud. Local environments like this one allow us to have an efficient dev and validation workflow environment. And this allows us to quickly iterate through our trainer and make sure that everything is working fine. Plus, we won't incur any charges for cloud resources while debugging the application. Okay, so with Shell open, first thing that I usually do is I'll create an alias for clear. So I'll type alias C equals clear, and it just allows me to quickly type C and press enter when I want to clear the shell. Now let's go over to the README for this video. So here's what we just did, the alias for clear. Now what we're going to do is on the local Cloud Shell environment, we'll create a data directory and we'll download the data. So that's what we're going to do here, right? mkdir data, and then using Google Storage util -m, copy, and there's our public cloud storage bucket. And we're directing that data to the data directory. So let's go ahead and do that. Over to Cloud Shell, and first we'll type mkdir data. I'll type C for clear, and now gs util -m cp gs : // and now cloud ml -public /census /data /star. So we want to copy all the files in that cloud storage bucket, and we're going to copy those to the data directory on the local file system here. All right, so let's do that. So press enter, and that's copying over. So let's do an ls on data. ls data, and there they are. And you can see that they're CSV files. So we'll type C and press enter to clear. Now what we want to do is we want to set up some environment variables to the local file paths. And again, if I go back over to the README, this is what we're going to do. So we're going to set train data to pwd, which is the working directory, data, adult data, and eval data is going to point to data adult.test. Okay, so let's just copy these. So I'll highlight both these commands. I'll right click, select copy. Let's go back over here to Cloud Shell. I'll click inside the shell and press Ctrl V, C to clear. And now if I want to echo, and first we'll see where train data is pointing. And there you see it's pointing at the adult data CSV. And the next one, eval _ data. And that should be pointing to the adult test CSV, and you can see that it is. So let's press C and press enter to clear that. Now let's have a quick look at that data. So I'll just type head $train _ data, and there's our training data. So this data has a list of different columns. So for example, age, the working class, as well as a number of other columns. And with this data, we're going to train our model so that it can predict whether a person has an income over $50,000 per year. So that's our data. So we've successfully configured data for cloud machine learning. In this video, we'll explore TensorFlow for machine learning. TensorFlow is open source software that can be used for creating machine learning models. TensorFlow uses numerical computation and Dataflow graphs. Nodes in graphs represent mathematical operations, while edges represent multi-dimensional arrays called tensors. And tensors are used to communicate between the nodes. While TensorFlow's flexibility supports a wide range of functionality, it was originally designed for conducting machine learning and deep neural network research, and is primarily used as such. Now let's look at the TensorFlow architecture. The TensorFlow kernel is at a very low level in the architecture, and it consists of key components like the distributed execution engine as well as the distributed master. There's also a C API, and the C API serves to separate user-level code, and the user-level code supports many languages but is primarily focused on Python and C++. And again, used to separate the user-level code from the core runtime. Users write client TensorFlow programs that build the computation graph. So you have input and output tensors, and the build and run are separated out. You create a session object to perform an operation at the run stage. It's done this way to support distributed execution. Now, this program can either directly compose individual operations, or it can use one of the higher level convenience libraries like the Estimator API. The lowest level client API uses C++. Then we have the Python API. This is a little higher level API, and it makes calls to the C++ API. You can also use other higher level abstractions like TF layers, TF losses, TF metrics, and the Estimator API is at a higher level. Now, it's object-oriented and is used to compose neural network layers and other higher level abstractions. In this demo, we'll run a TensorFlow Python program in Google Cloud Shell. I've logged into my account on Google Cloud Platform and I'm using this project. Now, I've already activated Google Cloud Shell by clicking this icon, and I've opened it in its own tab. So this is, again, the project that I'm working on here. Now, if you need to set the project, you can just type gcloud config set project and the name of the project. And just want to make sure that you're using the project that you're going to use for machine learning. Okay, so the first thing that we need to do is enable the Google Cloud Machine Learning Engine. Now, because we're in Google Cloud Shell, we can actually either enable it using the console, or if you want to try the command using gcloud ML engine models list, you'll be asked if you want to enable it for the project. So let's go ahead and do that. So here in Cloud Shell, we'll type gcloud ml-engine models list. Now, because I don't have Machine Learning Engine API enabled, it will ask me if I want to enable it. So I just pressed enter, and now I'm getting this message. Would I like to enable the API? And I do. So I'll type Y, press enter. While we're waiting for that to complete, let's go over to the README for this video. So you can see this is the command that we just issued here. Now, the next thing that we're going to do is open a Python interactive shell. And keep this in mind. Because we're using Cloud Shell, Python and TensorFlow are already installed. So it's very convenient. So we can run our simple TensorFlow Python program without having to install Python and TensorFlow. So that's what we're going to do. So let's go back over to Cloud Shell and see if that's done. It's not quite finished yet, so we'll just wait till that's complete, and then we'll resume. Okay, so that operation completed successfully, and you can see the output from our gcloud ML engine models list right here, listed 0 items. So we have 0 models right now. And one other thing is that for convenience, I usually create an alias to clear using C, and I just type alias C equals clear for that. So I've already done that. So if I press C and press enter, then it'll clear my Cloud Shell. Okay, so now let's start an interactive Python shell. So I'll type Python, press enter, and you can see we've got Python 2.7.13. So the next thing to do is to import the TensorFlow. So let's type import TensorFlow as TF. And then press enter. Okay, so now that's complete. So now we'll create a constant containing a simple string value. So type hello equals tf.constant, and then in brackets we'll specify our string. How about hello Python and TensorFlow? Okay, and press enter. So that's done. Now we need to create a TensorFlow session. So type ses equals tf.session. And you can ignore that warning. It doesn't really affect us. So now, in order to print the value to the console, we need to type print and sess.run. So we're going to run the session that we just initiated, and we'll specify hello. That's the name of the variable. And now press enter. And there you see the response. And successfully run a TensorFlow Python program in Cloud Shell. So now to exit the Python interactive shell, just type exit, open bracket, close bracket, and press enter. And now we're done. In this demo, we'll use TensorFlow to run a local trainer in Google Cloud Platform. Okay, I have the README for this video open in my text editor. And you can see the top line, we have some prerequisites for this demo. So let's go and have a look at those. They are contained in a file in this directory called prerequisites.txt. So basically what we're doing here for the prerequisites is just getting some data, setting up variables to point to the data files, and enabling the machine learning engine API. So if you haven't already done that, just take a couple of minutes and do that before continuing. Okay, so back to the README. So the first thing that we're going to do is download some code for this demo from GitHub. So let's highlight this command, right-click, select copy, and let's go over to the browser where I've got Cloud Shell open in its own tab here, and I've got the project that I'm using for this demo. And if I do an ls right now, you'll see that I have a data directory. If I do an ls data, I'll see that I have those two data files that I downloaded earlier. And that's what you should have as well. You should also have a couple of variables set up, train_data and eval_data. So if I go echo $train_data, I'll see that point to my training data. And if I do the same thing, only this time with eval_data, then I'll see the evaluation data. I also created an alias C that points to the command clear. So if I type C and press enter, it clears my Cloud Shell. Okay, so let's go ahead and download the sample code. So I'll press Control V to paste that wget command in here, press enter. Okay, and you can see that it downloaded already. So if I do an ls, there it is right there. So I'm going to press C and press enter. And now I'm going to unzip master.zip. Okay, I'll press C and press enter again to clear. And now I'm going to go to CloudML samples master /census/estimator. And that's where we need to run the commands for this demo from. So if I do an ls, I'll see that there's a trainer directory. If I do an ls and trainer, I'll see the files for the initialization, for the model, and for the task. And I've got those in the editor as well, and you can see those here. So let's quickly have a look at the model. Okay, and you can see that we're importing some classes that we require. Then we're defining the columns, the label column, and the labels, and the input columns. Now these are for ingesting and representing features, and you can see that we set up the features here using the categorical column with vocabulary list, right? So that's the key, and that's the vocabulary list. So now let's scroll down all the way down to line 167. And this is where we're returning the TF estimator, and we're using a deep neural network linear combined classifier. And what that is it's an estimator for TensorFlow linear and deep neural network joint classification models. And this estimator is also known as wide and deep. So just keep that in mind. So here we have a number of arguments. So config, we're specifying to use config. And for linear feature columns, we're specifying wide columns. For DNN feature columns, we're specifying deep columns. Now this is an iterable that contains all the feature columns that are used by the deep part of the model. And all items in that set must be instances of classes derived from feature column. And then we have DNN hidden units, and we specify that's either hidden units or the value in this list. And here's the thing. This is a list of hidden units per layer. And keep in mind that all layers are fully connected. Okay, so that's the model. And then for the task, basically again, we're importing, and then we're defining run experiment. And at the bottom of this file, we're running the training job by calling run experiment and sending the hyperparameters as an argument. Okay, so back to the README. Now we're in this directory at this point, and what we need to do is, in the next step, consider this, that even though TensorFlow is installed on Cloud Shell, we need to run the requirements.txt file, which is in the census directory, because the code for this demo requires TensorFlow 1.4. And you can check your TensorFlow version using this command. So I'll just highlight this, right-click, select copy, and I'll go over here to Cloud Shell. Clear this first by pressing C and pressing Enter, then Control-V to paste that command in. And you can see it returned version 1.6.0. So let's clear this again, back to the README, and let's install 1.4. And again, it's just located in requirements.txt, and it just specifies to use 1.4. Okay, so let's go over here. We'll paste this in. It's going to do some preliminary work, and it'll end up uninstalling 1.6 and installing 1.4 in its place. Okay, so while it's doing that, let's go back over to the README for a moment. And the next thing that we're going to do is we'll specify the model directory, and that's going to be specified as output. So you can see the comment here. The local trainer loads the Python training program and starts a training process in a local environment. And this local environment is similar to a live cloud machine learning training job, but when we run it locally, it gives us an efficient development and validation workflow environment. And this way we can quickly iterate, and it also means that we won't incur charges for cloud resources while debugging the application. So first, let's specify the model directory. So we'll highlight this, right-click, select copy, over to Cloud Shell, and we can see that it did successfully finish installing TensorFlow 1.4. So let's clear this, C, and press Enter. Control-V to paste that model dir specification in. That will clear again by pressing C and Enter. Okay, and now you see in the next note, it's always a good idea to delete the contents of the output directory, just in case there is remnant data from a previous job. So we'll run this command. Now this is the first time I'm running it on this machine, so the output directory isn't there, so I strictly really don't need to run this command at this point, but I will anyway. It's good practice. Okay, let's clear that again, C and press Enter. Now back over to the README, and now to run the local trainer. So let's go through this command. Now, as you can guess, this runs a cloud machine learning engine training job locally. So gcloud ML engine local train. Okay, and the backslash is to separate the different lines. Okay, so now let's go over these. Module name is basically just the name of the module to run, and the package path is a package path. And basically it's a trainer here. So it's a local path, and it's on Google Cloud Shell. So if I go back over here to Cloud Shell and I type ls, you'll see that I've got that trainer directory there, right? So type C, press Enter, and let's go back here. Now the job dir, that argument specifies either a Google Cloud Storage path or a local directory that will store the training outputs and other data needed for training in. Okay, and the rest of these arguments are user arguments. And these have to be on the right side, or if you're doing it like I am here and separating them out line by line, they have to come below or to the right of the other arguments. Okay, so the user arguments are the last ones that are specified. Okay, so now let's copy this command. So we'll highlight the whole thing, right-click, select copy, over to Cloud Shell. Click inside and press Control V to paste that in. And now let's press enter. So now this runs our job locally, and we'll start seeing output here shortly. Okay, and you can see all the training steps that it went through and the evaluation steps. And we can see the saved model was written to this directory. Okay, and we can see the statistics for this model. Okay, so that's it. We've successfully run the trainer locally. In this demo, we'll use TensorBoard to inspect TensorFlow logs. You can view the evaluation results of a model using TensorBoard. TensorBoard is installed with TensorFlow, and it's a very cool tool that allows us to visualize our TensorFlow graphs, plot quantitative metrics, and show a lot of other additional data. Let's go to the README for this demo. I want to show you, first of all, the prerequisites. So I'm going to open the prerequisites file here, and you can see two things. So basically, in step 1, get some data, set up some variables to point to data files, and enable the machine learning engine API. And then in step 2, configure and run a local trainer. Okay, so if you haven't done those prerequisite steps yet, then take about 5 to 10 minutes and do those. Okay, so now in the README, what I've done to make things easier for myself is I have added these lines into my profile file, and that's in Cloud Shell. So to do that, you just launch vi using sudo, and you point it at the .profile file, and then once in there, you add those lines, then press escape and :WQ to save the changes. Then relaunch Cloud Shell. Now I'm going to go over to Cloud Shell. I'll just show you how to quickly do that. So I've opened up or activated Cloud Shell already, and I actually have 2 tabs open here. And that's why I added those entries in the .profile file, because it just makes it easier when I open a new tab in Cloud Shell that I don't have to recreate the wheel, so to speak, every time. I don't have to recreate the model dir variable. I don't have to create or recreate train data or eval data. Okay, so to do this, again, just do this. Sudo vi and the name of the file. And it's actually my home directory, so I'm going to preface this with a tilde / .profile. Okay, and there it is. Now, once you're in here, it actually works very well. I really like the way that they have vi working in Cloud Shell. So now just press escape and A to insert new lines. And then if you've copied those lines, you can actually just paste them in here just like you would in any other editor. So it's very convenient. Now when you're done making your changes, you're just going to press escape and then type :WQ and then press enter. Now I'm going to do this, but I have no changes, so it's not going to change anything, right? So one of the lines is to create an alias for clear, and that's C. So I've done that, so I'll press C. And now let's get down to the steps for this demo. So let's go over to the README again. Okay, so here we are. Now we're launching TensorBoard here. And basically what we're doing is we're pointing it at the summary logs that were created during training. All right, so let's go ahead and do that. Let's copy this command. So we'll right click, select copy over to Cloud Shell, and let's Control V to paste that in and launch TensorBoard. Okay, so now TensorBoard is running, and now to see it, just click on Web Preview in the toolbar and click on Preview on port 8080. Okay, and now you can see some data on previous runs. So for example, we're talking accuracy here. So if we scroll down, we've got average loss, we've got deep neural network layers, we've got global step. Now we've got also all of these different items: accuracy, accuracy baseline. We have all kinds of other data here that we can look at. Now, something that's really cool is this. Let's have a look at the graphs. Okay, so there is our graph for our model. And we can zoom in and we can navigate around this graph. We can see, if we click on this, the gradients. Okay, so I mean, this is just an awesome tool. So if you're looking to visualize and analyze your model training and evaluations, this is an awesome tool to use. Now you can also keep this open. So I'm just going to go back here to scalars for a sec. So I'll click on scalars. I'll go back to Cloud Shell. And now in the second tab, I'm going to click on that second tab. And I'm going to go back to the README. And what I'm going to do is I'm going to remove the data and run that training again. So I'll highlight this entire section of code. I'll right click, select copy, back over to Cloud Shell. I'll press Control V to paste that in and press enter, and now it's running the training again. Okay, so let's go over here and now we'll refresh. Okay, and now we can see that there's some previous data and some new data. And actually, it will tell us that too. Well, if we go back to Cloud Shell, we'll see all those steps as it's completing the training and the evaluation. But if we go back here, it's telling us that, first of all, we deleted, and now it's telling us that it's overwriting the graph with the newest event. Okay, so we can run this and keep it open while we run our training and iterate through. So it allows us to have some real-time, almost real-time view into our model and see how we're progressing as far as our training is going. Now, when you're done, first I'm going to clear this by typing C and pressing enter. I'll go back to the other tab and I'll close the TensorBoard tab. We're done with that now. Now to close this, you just kill the process by typing Control and C. And that killed the process. So C, press enter, clear, and we're done. In this demo, we'll run a local trainer in distributed mode. A model can be tested to see whether it works with the Cloud Machine Learning Engine's distributed execution environment by running a local trainer and using the distributed flag. So I've logged into my cloud platform here and I've got a Cloud Shell activated. And you just simply click to activate it here. And then once you've done that, you can pop that out into its own window. So this is the environment we'll work in. Now I'm going to go over to the README for this video. And there are some prerequisites. And they're listed in the prerequisites.txt, which is in the same directory as this demo. So if I click here, here's the prerequisites. And basically, prerequisite 1 is to get some data, set up some variables that point to the data files, and enable the Machine Learning Engine API. And then configure a local trainer. So if you haven't done that yet, then go ahead and do that. Take about 5 or 6 minutes and go ahead and do that. Then come back here to the README. Now what we're going to do is we're going to change the model directory to point to a different directory. This one's output-dist, right, for distributed. Then we're going to clear the directory. It's always a good practice to delete the contents of the output directory just in case there's any remnant data. Then we run locally with the distributed flag. And I have a comment here, note its placement. Now its placement is above this dash dash, and this is there to separate the command line arguments, which are here, from the user arguments, which are here, right? So there's our dash dash distributed flag. And then once we're done that, we'll list the output, and then we'll start TensorBoard and have a look at it. So let's go ahead and do that. Let's copy these two commands. So I'll highlight them, right click, select copy, over to Cloud Shell, click inside Cloud Shell, and note the directory that I'm in, cloudml-samples-master, census estimator. Okay, and let's press Control V to paste those commands in. Done. And one of the things that is set up in the prerequisites is an alias to clear. And if I type C, press enter, that clears everything. All right, back to the README. So now that we've cleared that, it's time to run the trainer locally with the distributed flag. So let's copy this command. So we'll highlight everything, right click, select copy, back over to Cloud Shell, click inside, Control V to paste that command in, and press enter to run it. Again, you can see the progress as it scrolls through. And now it's doing the evaluation, and now it's evaluating loss. Let's clear by typing C and pressing enter. And now we can list the output. So ls dash capital R output dash dist. Okay, and there you can see all the output files for our model run. So let's clear this again. C, press enter. Now let's run TensorBoard. So I'll highlight this command, right click, select copy. And notice that we're pointing at the summary logs. We're using model dir, which now points to output dash dist, right? So again, let's copy this. We'll right click, select copy, over to Cloud Shell, click inside here, press Control V, press enter. Okay, now click on Web Preview, preview on port 8080, and there it is. So you can check out the accuracy. You have a number of other things that you can check out here, like loss prediction and all of that. You also have graphs. So if I click on graphs, have a look at this. This is the graph. So pretty cool. You can zoom in here, you can navigate around and so on. And click on projector, and this is pretty cool. This will load all of our data up into the dimensions. Pretty cool. Okay, so with that, we've successfully run a local trainer in distributed mode. So now we know that our trainer will work with Cloud Machine Learning Engine's distributed execution environment. In this demo, we'll run a single instance trainer in the cloud. Okay, I've logged into Google Cloud Platform with my account, and I've activated Cloud Shell. You can see that here. Now there are some prerequisites for this demo, and they're contained in a prerequisites.txt file, which is in the same directory as the README for this video. So let's have a look at those. I've got that file open here. So basically what we're doing is we are getting some data, setting up variables to point to the data files, and enabling the machine learning engine API. And again, these are prerequisites. And in the second step, we're downloading the code for the demo from GitHub. And I've also included the master.zip file, which contains all that code, in the directory for this video. Okay, so that's the prerequisites. Now let's go over to the README. Okay, step one, create a bucket in cloud storage and copy files to it. Cloud Machine Learning Engine services require access to cloud storage in order to read and write data during model training and batch prediction. So for this demo, we'll first create a cloud storage bucket. Now we have to specify a unique name for the bucket across all buckets in cloud storage. So one excellent strategy in order to accomplish that is to use the project ID as part of the name and append a string that means something. So for me, I've appended the string -MLE for machine learning engine. Okay, so that's what we're doing here. First, we're creating a variable called project_ID, and we're using gcloud config list project to get that project ID. Then we're specifying a bucket name variable, and we're using that project ID and again appending -MLE. So let's go ahead and we'll copy these two commands. So we'll highlight that, right click, select copy, over to Cloud Shell, click inside the shell and press Control V. Okay, so now with that done, let's echo bucket name. Make sure that we have it right. Okay, so there's our bucket name. So the bucket isn't created yet though, keep that in mind, right? So let's clear this by typing C and pressing enter. Okay, so now we can create a variable to hold the region that we're going to use. Now yours may be different than mine, but for this demo, I'm using US-Central1. So we'll highlight this command, right-click, select copy, over to Cloud Shell. Okay, so that variable has now been created. And now we create the new bucket using the gsutil command. So we specify gsutil mb-l, and for that location, we use our region variable. And for the cloud storage bucket, we're specifying the Google Storage, the fully qualified Google Storage name, and we're taking advantage of the variable that we created by specifying $bucket name. So let's go ahead and do that now. So let's copy this. So we'll highlight it, right-click, select copy. Let's go over to Cloud Shell, paste this in. Okay, so that's successfully completed. Let's go back over to the README. And now we'll use gsutil again to copy the data files to that cloud storage bucket. Now keep in mind, now those data files are located in Cloud Shell, and that was part of the prerequisites. So first, let's highlight this, right-click, select copy. Let's go back to Cloud Shell, and let's type ls. And we don't see any data directory there, do we? And that's because that data directory is off of my home directory. So I'm going to cd tilde, go to my home directory, and now if I do an ls, I'll see there's my data directory. So let's clear this. We'll type C and press enter. Now we'll Control V to paste that command in. So now what it's going to do is it's going to copy the contents of the data directory over to our bucket name in a folder named data. Okay, so let's go ahead and do that. Press enter. Okay, so now that's done. Press C to clear that. Now we have to cd back to cloud samples -master census estimator. Now you could have hard-coded that tilde directory into that last command rather than cding back and forth. So for example, instead of cp-r data, you would preface that with the tilde character and a /, like so. So we can do that. Let's go ahead and try that, see if that works. So we'll highlight that, right-click, select copy, back over to Cloud Shell, Control V to paste that in, and success. Okay, so I just thought I would show you that. Now, we need to set the train data and eval data variables to point to the files in cloud storage. We're not running this locally anymore. Again, this is going to be run in the cloud, right? We're going to request the job in the cloud. So let's highlight these two commands and change those. And notice that these are using, again, the fully qualified Google storage name. So I'll highlight that, right-click, select copy, back over to Cloud Shell, Control V to paste those in. Okay, done. Now we'll use gsutil to copy the JSON test file named test.json, and we need to copy that over to Cloud Storage Bucket. So that's what we're doing here. Okay, so let's go ahead, copy that. So we'll highlight that command, right-click, select copy, over to Cloud Shell, Control V to paste that in. Okay, so done. Type C and press enter to clear that again. And now we'll create a test_JSON variable, and that will point to that test.json file we just copied over there. So let's highlight this, right-click, select copy, over to Cloud Shell, Control V to paste that in, type C and press enter to clear. And now we're ready to run our trainer in the cloud. And I've included some notes here that basically in this demo what we're doing is we're requesting a single instance training job, and we're going to use the default basic scale tier so we don't have to specify the scale tier. And Note that the first time that you run this job request, it can take a few minutes to start, but in subsequent jobs, it will run quicker, and that enables quick iteration as the training job is developed and validated subsequently. Okay, so the first thing we need to do here actually is to specify a name for the first training run. And we want to distinguish it from subsequent runs, so it just makes good sense to append a number to represent the iteration. So I've got a job name variable, and I'm specifying census underscore single underscore 1. A subsequent job might be census underscore single underscore 2, and then 3, 4, and so on. The other thing that we need to do here is specify a folder to store the output generated by the Cloud Machine Learning Engine. And that's what we're doing here. Okay, so we're specifying that output path. So first things first, let's go ahead and we'll highlight these two commands. So we'll right click, select copy over to Cloud Shell, click inside and press Control V to paste that in. Okay, and now that's done. And now we are definitely ready to run our job. Now you can see here that this command that we're using submits the training job in the cloud, and it tells it to use a single process. And notice that we set the verbosity flag to debug. That allows us to subsequently examine the full logging output, and then we can also retrieve things like loss, accuracy, and a number of other metrics as well. So that's what we're doing here. So if you'll just take a look here, verbosity, we set to debug. Okay, and you can see here that we're specifying gcloud, ml-engine, jobs, submit, training, and the job name. Okay, so that's it. Let's go ahead. We'll highlight that command, right-click, select copy. Oh, and one thing before we go over there, we're specifying the runtime version. TensorFlow is going to be 1.4. Okay, so let's go over to Cloud Shell, click inside, Control V to paste that command in, and now we'll press enter. And now it's running. And the last comment that I make in the README is this. Note that you can monitor the progress of the trainer by watching command line output, or you can also navigate to the Machine Learning Engine jobs in the Google Cloud Platform console. Okay, so we can see that that job has been queued. Let's go over to console. We'll click and we'll scroll down to Machine Learning Engine, click on Jobs, and there's our job ID, and it's a training job. You can see that. Let's click on it to drill down. Okay, and you can see that it's running right now, and it's going to take some time, right? So that will take some time. So what I'll do is I will pause the video, and then when that's done, I'll resume. Okay, so the job completed, and we can see that it took a total of 6 minutes and 6 seconds. Not that bad, really, for the first run. Now, if you want to quickly view the logs, you click on View Logs, and that will open the logs into a new tab in the Cloud Platform, and you can drill down and see additional data there. Okay, so we've successfully run a single instance trainer in the cloud. In this demo, we'll inspect the Stackdriver logs for a machine learning engine job run in the cloud. Logs are obviously useful for capturing data and understanding how training code is working in the cloud. When Cloud Machine Learning Engine runs a training job, it captures all the standard out and standard error streams and other logging statements. These logs are stored in Stackdriver logging, and they are visible both during and after execution. One way to view the logs is in Google Cloud Platform console. So first, let's go over to the README. I just want to describe some prerequisites for this video. Those prerequisites are found in the prerequisites.txt file, which is found in the same directory as this demo and the README for this demo. So looking at prerequisites, so first we're getting some data, setting up variables to point to the data and enabling the Machine Learning Engine API. Next, we download the code for the demo from GitHub. And I've also included the master.zip file, which contains all that code in the directory for this video. After we've done that, then we create a bucket in cloud storage, and we copy files to it. And then finally, we run a trainer in the cloud. Okay, so those are the prerequisites. If you haven't done that yet, then go ahead and take 10 or 15 minutes and do that. Now over to the README. Now, again, what we can do is we can navigate to Machine Learning Engine jobs in Cloud Platform Console. So let's go ahead and do that. Over to Cloud Platform Console, click on the burger menu, and scroll all the way down and point to ML Engine and click Jobs. Okay, and here's the training job that I submitted a few minutes ago. Now, to view the logs, click on View Logs. Okay, and because we have all logs specified here, we are going to see logs from all workers. We could specify, for example, master replica 0 or census single 1. Now, master replica 0 is going to give us specific information about the job's execution from the perspective of the master. And because in the prerequisites, what we're doing, and I'm just going to quickly go back to the README here, back to prerequisites, and when we run this trainer in the cloud, we're specifying a verbosity of debug. And because we're looking at verbose logging, that means we can inspect the full logging output. So going back over here to Cloud Platform Console, now we can filter by label or search. So let's search for accuracy, for example. And there, so you can see that we can pull up all that information in the logs about the accuracy. So we can expand each of these and look at detailed data about that. Now, if you want to view these logs in the terminal in Cloud Shell, you can also do that. So let's go back here to the README. And to do that, you use this command. gcloud ml-engine jobs stream logs, and we specify the job name, right? So let's highlight this, right click, select copy. Let's go over to Cloud Shell, click to paste this in, and press enter. So there's our detailed logs in Cloud Shell. In this video, we'll explore cloud machine learning scaling on Google Cloud Platform. Cloud Machine Learning Engine has flexible and scalable pricing options for training models and making predictions. The pricing is based on region, that is being US, Europe, and Asia Pacific, and each has different pricing based on whether the service is training, whether it's batch prediction or online prediction. You define how Cloud Machine Learning Engine scales, and this means the number and types of machines to run a processing cluster. So you have scale tiers, and these offer predefined cluster specifications. In general, as you select a more advanced tier, the virtual machines are more powerful and the number of virtual machines allocated to the cluster is increased. Another option is to specify a custom scale tier, which allows for fine-grained control over the different machine types. For example, you can set a different machine type for the master worker, parameter servers, and workers. Processing resources used by Cloud Machine Learning Engine to run a model for prediction are called nodes. And this can be thought of as virtual machines. The number of nodes used to do the work for online and batch predictions is scaled by Cloud Machine Learning Engine. Charges are incurred for the time that your model runs on a node. So this includes when processing an online prediction request, when processing a batch prediction job, and when your model is in a ready state for serving online predictions. In addition to the costs discussed thus far, cloud storage buckets in Google Cloud Storage are required for storing data and program files across the Cloud Machine Learning Engine lifecycle, and this storage incurs the usual cloud storage pricing. Resource management operations on Cloud Machine Learning Engine are free although a quota policy does impose some limits. Nevertheless, the free operations allow you to manage models, versions, jobs, and operations free of charge. In this demo, we'll run distributed training in the cloud. We can configure our training in such a way as to take advantage of Google's scalable infrastructure for our training jobs. And we do this by configuring the trainer to run in distributed mode in Cloud Machine Learning Engine. And to run a distributed job, we set the scale tier flag to any tier above the default basic scale tier. So we have some prerequisites for this demo. So I'm just going to go over to the README for this demo, and those prerequisites are in a file called prerequisites.txt in the directory for this video. Let's have a quick look at those. So first we get some data, set up variables, point to data files, and enable machine learning API. Then we download the code, which I've also included as a file called master.zip in the directory for this video. And then, because Cloud Machine Learning Engine services require access to cloud storage in order to read and write data during model training and batch prediction, we're going to create a bucket. And that's in the prerequisites, right? So we create that bucket here. So if you haven't done that, take a few minutes and do that. Now over to the README. So first, we're going to specify a name for the distributed training run, and we want to distinguish it from other training runs. So what we'll do here is we'll use the string dist to represent a distributed training run and a number for the iteration. So here I'm defining job name. That variable will be census_dist_1. Then we configure the variable output path to include the job name, and that way we don't reuse checkpoints between jobs. So this output path variable points to a folder named census-dist-1. We're taking advantage of the variable here, job name. And then we submit the training run in the cloud to use multiple workers, and we do that again by specifying a scale tier above the default basic, right? So we're specifying here standard_1. And note the location of that flag. We need to put it above this dash dash that separates the user arguments down here from command line arguments up here. So let's copy these two commands. So I'll highlight them, right click, select copy over to Cloud Platform, and I've already activated Cloud Shell, and I'm in the Cloud ML Samples Master Census Estimator directory. So now I'll press Control V to paste those commands in, and now those are done. So let's go back over to the README and let's grab that command, gcloud ML Engine job submit training, the job name, and again, we're specifying a scale tier of standard_1. So let's highlight this command, right click, select copy over to Cloud Shell, press Control V to paste that in, and press enter to run it. Okay, so now that that has been queued, let's go over to Cloud Platform Console, click the burger menu, and scroll all the way down the menu, point to ML Engine, and click Jobs. And now you can see that that job has been submitted. Now keep in mind the first time that you run this job, it may take a while. It may take a few minutes for it to spin up. But what I'll do is I'll pause the video at this point, and then when it's done, I'll resume. Okay, so our distributed job is now done. So let's click on View Logs. But you can see here that we've got a couple of worker replicas. And this is different than running a job in the default basic tier, which would not spin up multiple workers, right? So we can specify to look at any of the replicas or the master. Okay, so we've successfully deployed a training job in the cloud, taking advantage of Google's infrastructure to scale. You can use hyperparameter tuning with Cloud Machine Learning Engine to aid in optimizing a model's predictive accuracy. In this demo, the hyperparameter configuration settings are stored in a YAML file named hptuning_config.yaml. We use it by specifying the file in a training request by using the config flag. So let's go over to the README for this video. And there are some prerequisites, and they are in prerequisites.txt, and that file is in the directory for this demo. And here they are. So basically, we get some data, set up some variables, enable the Machine Learning Engine API. Then we download the code for the demo, which is also in a file called master.zip in the directory for this video. And then we create a bucket in cloud storage and copy the files to it, since Machine Learning Engine will require access to cloud storage and the bucket that we specify for reading and writing output. Okay, back to the README. So the first thing we're going to do is we're going to specify a new job name, and we're going to create a variable called hptuning_config that references the configuration file, which I mentioned just a moment ago. And that file is in this directory: CloudML samples, master, census, and let's go and have a look at that. So let's go over to Cloud Shell. I've activated Cloud Shell already. So now we can do a cat /hptuning_config.yaml. Press enter. So there is our hyperparameter tuning file. So you can see that we've set the goal to maximize. The hyperparameter metric tag is accuracy. We set the maximum trials, parallel trials, and here's the params. So first layer size, then number of layers, then scale factor. Okay, so let's type C and press enter to clear. Back over to the README. Okay, now the next thing that we do here is we're actually pointing the data files at the bucket name and the data files themselves. Okay, so let's highlight this, right click, select copy, over to Cloud Shell, click inside and press Control V. Okay, so that's done. Type C and press enter to clear. Back over to the README. And now we're configuring the output path variable to include the job name in order to avoid reusing checkpoints between jobs. And what we're doing here is we're setting this output path variable to point to a directory which ultimately is going to be named census_core_hptune_1. That's how we set it up here, job name. And we're taking advantage of that variable here, as well as the bucket name variable. So let's copy that command. We'll highlight it, right click, select copy, over to Cloud Shell, Control V to paste that in, type C and press enter to clear. And now we can run this command to submit our training job. And this training job is using multiple workers and hyperparameter tuning. And note that the config flag is above this -- line. And that's because it is a command line argument. And these are the command line arguments. And these ones below are user arguments. Okay, so highlighting that, right click, select copy, over to Cloud Shell. Click, press Control V to paste that in, and press enter. And you can see that it's been submitted successfully. So now if we go over to the console, let's click the burger menu, scroll all the way down, point to ML Engine and click on Jobs. And we'll see that job has indeed been submitted here. Now keep in mind that this job may take a few moments to start up. So while we're waiting, I'm going to pause the video, and then when it's done, I'll resume. Okay, so the hyperparameter tuning job has completed. And as you can see, the elapsed time is quite a bit more than the regular distributed training job and the single training job. And that's because hyperparameter tuning works by running multiple trials in a single training job. Okay, so we've successfully run a hyperparameter tuning job on Google Cloud Platform. In this exercise, you will practice what you learned about TensorFlow and cloud machine learning. You will load a dataset for cloud machine learning, use TensorFlow and cloud machine learning engine. And in that regard, you'll run a local trainer in Cloud Shell, run a single instance trainer in the cloud, and run a distributed trainer in the cloud. Now pause the video and perform the exercise, and when you return, I'll go over these tasks. Okay, so we're going to do all of these tasks one after another. Okay, so for the first part, I'm just going to assume that you set up your project properly. And I'm assuming that you've created an alias for clear. It's not necessary actually, so if you didn't do that, don't worry about that. So the first part, we're going to get some data. So the first thing that we want to do is perform an mkdir data command, and that will create the data directory. And then we'll use gsutil. Then we'll copy one of the public data files, or actually a couple of them, and they're located here in Google Storage. Okay, I'm just going to highlight these two commands. I'll right click and select copy. Let's go over to Cloud Shell. I'll Control V to paste those in. Okay, so now that part's done. I'll press C and then press enter. Now we need to set variables to point to the data files. So we'll grab these two commands. So we'll highlight, right click, select copy, over to Cloud Shell, Control V to paste them in. Okay, excellent. And we won't bother checking out the data, but the next thing that we'll do is we could issue this command. However, I've already got the machine learning engine API enabled, but let's just quickly go over and have a look at how you do that in console. Okay, so let's click to go to the APIs overview. We can go to the library, or we could have clicked enable APIs and just look for ML engine. And if you type ML, it'll come up. So here's the tile for cloud machine learning, and you can see that I've got this API enabled. Okay, so let's go back to the README. So that's our data. We've loaded our data for this exercise. So now we need to download the code from GitHub and install dependencies. So let's highlight this command. Right click, select copy, over to Cloud Shell. I'll Control V to paste that in. And now while it's downloading, and it's already done, let's go here to the README again and see what we're going to do next. So we're going to unzip master.zip, and then we're going to cd to this directory. So let's highlight those two commands, right click, select copy, Control V to paste those in. Okay, and I'll press C and press enter again. So now you can see that I'm in that directory. Okay, so the next thing we need to do is install the requirements, and the requirements include TensorFlow 1.4 because currently we have 1.6. Now that's not true. I have 1.4 on this machine, so we're fine, but I'll just show you what to do. You just highlight that command, right click, select copy, over to Cloud Shell, and then Control V to paste that in. Now I'm not going to run this step because again, I have TensorFlow 1.4 installed on this virtual machine in Cloud Shell. Okay, so now we need to run our local trainer. So the first thing we need to do is set up a model directory, and we'll call that model directory output. Okay, so let's highlight this. And then the next step here is to do an rm-rf on that model directory. And it's just good practice to get rid of all the previous contents. So let's right click, select copy, over to Cloud Shell, Control V to paste that in. Now let's clear. And now we can run our local trainer. So let's highlight this command, right click, select copy, Cloud Shell, Control V to paste that in. And while that's running, go back to the README one more time. And the next thing that we're going to do is we're going to run a trainer in the cloud. So we'll need to create a bucket. And we need that to do that because in order to run a trainer in the cloud, we have to provide access to cloud storage. So this is what we'll do. We'll name it after a project ID and we'll append -mle at the end of it. So let's copy these three commands. Right click, select copy, Cloud Shell. Okay, and we can see that that model is complete. So let's clear this. C, press enter, Control V to paste those commands in. Now let's echo the bucket name. So there's our bucket name just created. So let's clear this again. Back over to the README. Now we have to set a region, and then we'll create that bucket, right? So we created the bucket name and everything, but we'll create a region variable. Then we'll use gsutil to create that bucket. And then we'll use gsutil to copy the data files to the cloud storage bucket. So let's copy all three of these commands. We'll right click, select copy, over to Cloud Shell, Control V to paste them in. Okay, the bucket was created. Now we're copying those data files over. Excellent. So we'll press C and press enter again to clear that. And now we'll set the train data and eval data variables to point to the files in cloud storage. And then we'll use the GS utility to copy the JSON test file over to cloud storage as well. So let's highlight these three commands. And actually we'll highlight this command as well, because that will create that test_JSON variable. So right click, select copy, over to Cloud Shell, Control V. Okay, so now that's done. So now we're ready to run our trainer in the cloud. So the first thing we're going to do is give it a job name. We're going to call it census single 2. This is the second iteration. And then we specify the output path, and that will point to census single 2 as well. So let's copy these two commands. So we'll right click, select copy, over to Cloud Shell, Control V to paste that in. And now we're done. All right, so now we can run our trainer in the cloud. So let's copy this command. So we'll right click, select copy. And the big difference here, if you look, gcloud, ML Engine, jobs, submit training. And if you look at the local trainer, we specified local, right? Okay, so again, let's make sure we copy that. Let's go over to Cloud Shell, Control V to paste that in. And that will queue our job up. Okay, so now if we go to console and scroll down, point to ML Engine, click jobs, we'll see that that job has been submitted. Okay, so while it's running that one, what we'll do is we'll go back to the README here. And now what we'll do is we'll run a distributed trainer in the cloud. And this is called census_dist_2. The output path, now we're going to specify a different output path. And the reason why we can do all this is because the other job is now running. So we don't need these variables for that other job at this point. So now the big difference here is that we're specifying a tier, a scale tier, other than the basic scale tier. So we're specifying standard 1, right? So let's grab all three of these. So we'll highlight everything, right click, select copy, back to Cloud Shell. I'll clear this by typing C and pressing enter, Control V to paste those commands in, and we're ready to go. So I'll press enter, and now that job's been queued as well. So if I go over to jobs, refresh, I'll see that there's my distribution job, there's my single instance job, and both are running. In this video, we'll consider the benefits of quality features with feature engineering and feature selection. Let's look at feature engineering. One benefit is more efficient model training. This is the case because feature engineering can often lead to faster training of the machine learning algorithm. Engineered features can offer additional information and enhance the extraction of meaningful data. In addition to that, another benefit is strong data classification. Better features can produce simpler and more flexible models, providing better information to enhance the ability to differentiate patterns in the data. Enhancing the feature set can also lead to a reduction in dimensionality, which often means a reduction in computation complexity. Now let's look at some other key benefits. So we briefly touched on this before, but it's important to consider how fast we can train a machine learning algorithm. And this is often enhanced by using a higher quality, more relevant feature set. Furthermore, by simplifying a model, that is, reducing the complexity of the model, it makes it a lot easier to interpret. Better feature sets lead to a more accurate data classification and reduces overfitting, which is a type of modeling error that can result when a function too closely fits a limited set of data points. And typically, this results from generating an excessively complex model. In this video, we'll explore the process of input selection in feature engineering. In a traditional input selection cycle, we have an input dataset. Then an engineer typically writes new feature code and applies it to a sizable raw dataset. This step can be time-consuming. The feature code is executed in a scan of the data. This results in a training dataset delivered to a machine learning system. The resulting trained model's accuracy is evaluated, typically using a set of human-labeled examples. If the model is considered good enough, then we have a quality function. Otherwise, we return to alter the feature code and repeat this cycle until we're satisfied. Feature selection techniques are used to remove non-useful features, resulting in a simplified model. The end goal is an economical model which computes faster with very minor or zero degradation in predictive accuracy. To end with a model like this, some feature selection techniques must train more than one candidate model. So feature selection doesn't necessarily mean a reduction in training time. Filter methods pre-process features by measuring characteristics of the data to make feature selections. So this first filter method is based on a correlation coefficient known as Pearson's correlation coefficient, which is a statistical measure of the linear correlation between variables. Then we have LDA, or linear discriminant analysis, which is a method used to achieve a linear combination of features that can be used to differentiate or classify two or more things. The combination that results from this method can be used to reduce dimensionality prior to classification. Another filter method is analysis of variance. This is using a group of statistical models along with their related procedures to analyze the differences amongst group means. And then we have statistical tests. For example, chi-squared tests are typically composed from a sum of squared errors or sample variance. Wrapper methods can be used to score different subsets of features according to their predictive capabilities, typically applying cross-validation to make feature selection. In forward selection, we have an iterative method where you begin with having no feature. In subsequent iterations, we add the feature which optimally improves the model until the point that adding a new variable no longer improves the model. In backward elimination, we have an iterative method where you start with all the features and remove the least significant feature in each iteration that improves model performance. This cycle is repeated until there is no longer performance improvement upon removal of a feature. And recursive elimination. This method repetitively creates models and then iteratively eliminates a certain number or percentage of the lowest ranking features. Once all features have been used or exhausted, they are ranked based on their order of elimination. Okay, so let's dig a little bit deeper into sequential feature selection. So feature selection seeks to reduce the dimensionality of data by selecting a subset of features, we call them predictors, with which to create a model. Selection criteria typically involves minimizing some measure of predictive error or cost function minimization, which essentially means minimizing errors. Algorithms seek out a subset of predictors that best model measured responses, and sequential feature selection is a common method used for selection. It has two components: an objective function, which is called the criterion. The sequential feature selection method tries to minimize the criterion over all practical feature subsets. Typical criteria include mean squared error, which is suitable for regression models, and misclassification rate, which is used for classification models. A sequential search algorithm is the second component, and this algorithm adds or strips away features from a candidate subset while at the same time evaluating the criterion. Since an exhaustive comparison is typically impractical, sequential searches move in one direction only, either growing or reducing candidate feature sets. Now, finally, let's talk about embedded methods. Embedded methods combine filter and wrapper methods and are executed by algorithms that have integrated feature selection methods. There are two common embedded methods. The idea behind these two methods is to penalize the magnitude of coefficients or emphasis of features while minimizing the predicted versus actual observation errors. This is known as regularization. The two embedded methods that we're going to talk about here differ in how they assign that penalty. First, ridge regression uses L2 regularization. What this means is that it adds a penalty equivalent to the square of the magnitude of the coefficients. And lasso regression uses L1 regularization. This adds a penalty that is equivalent to the absolute value of the magnitude of coefficients. In this video, we'll demonstrate feature engineering in use cases. We're going to take a look at three common use cases in feature engineering, and that is decomposing categorical attributes, decomposing date-time values, and reframing numeric values. Let's go over to Excel here, and I have three worksheets representing those three use cases. Okay, so first, decomposing categorical attributes. Suppose that you've got an attribute like attribute underscore color or attr underscore color here. And we have some values, red, green, blue, unknown, and transparent. To you, as a human being, unknown and transparent may represent something unique or different. However, to a machine learning model, those are simply just other colors. So there may be a better way to reveal this to the model. So for example, you could create a new binary feature called attr underscore has underscore color and give the value a 1 if it actually has a color and a 0 if it's unknown or transparent. Now let's look at decomposing date time. Okay, date times are structurally complex, and as a domain expert, you might be thinking that there is some level of time dependence in your data. In that case, decomposing date time data is one way to enhance the feature set. So for example, here we have a date time. So that we're taking the date out of that, we're extracting just the date. So let's say that you suspect that there's a relationship between the time of day and some other attributes. You could take the time and extract the time only. Other familiar attributes like weekday as well as month are also indicated in some cases. Now let's look at reframing numeric values. Most data contains numeric values or quantities of some type. These values may be reframed in order to reveal some kind of relevant structure. This may mean transforming them into new units or new types of measurements. For example, going from metric, as we see here, to the English measurement system of inches. A linear transformation, the basic linear transformation, may also be useful for regression, for example. So, for example, we go from 5,000 meters to 5 kilometers. Or in smaller measurements, we go from 0.05 meters to centimeters to inches. And for very small measurements, from 0.01 meters to 1 centimeter to 0.39 inches. So suppose that you've got some domain knowledge that distances greater than 1 centimeter represent some special case. That domain threshold could be used to create a new binary feature called ln_gt_threshold, for example, and assign it a 1 when it's over that threshold. So if it's greater than 1 centimeter, then give it a 1. If it's not greater than 1 centimeter, and this one is exactly 1 centimeter, then give it a 0. In this video, we'll explore the concepts of streaming data and real-time stream processing. Real-time stream processing typically is used to manage and process streams of data that could come from millions of intelligent devices and sensors in the Internet of Things. A platform suitable for real-time stream processing has to be able to handle importing the data, processing that data, as well as storing and analyzing that data. What's more, this could mean events numbering in the hundreds of millions per hour need to be handled. Devices on the Internet of Things generally interact with the environment and collect data. They can be broadly categorized as constrained and standard devices. Constrained devices tend to be very small and are limited in terms of compute, storage, and other resources. For example, a constrained device may only be capable of communicating over networks like Bluetooth Low Energy, unable to contact Google Cloud Platform directly. Essentially, constrained devices then must use some form of gateway device in order to reach Google Cloud Platform. Standard devices, on the other hand, can be thought of as small computers, capable of transmitting data over networks to Google Cloud Platform directly. Ingesting data refers to the process of getting information from Internet of Things devices to Google Cloud Platform services. Different import targets exist, and which one to use depends on whether the information consists of data about the environment or operational data concerning the device and the Internet of Things infrastructure. Cloud Pub Sub is a messaging service that can readily scale to handle data spikes from swarms of devices to respond to events. Cloud Pub Sub can absorb shocks for incoming data streams in addition to changes to application architecture. Cloud Pub Sub uses topics and subscriptions, which allow different functions of an application to subscribe to device-generated streams of data. Cloud Pub Sub is also plugged into Google Cloud Platform services, thereby merging data import, pipelines, and storage services. It's important to ensure that devices are healthy and functioning well in order to make sure that you have a consistent and reliable data stream. Stack driver monitoring can provide key metrics related to the health of devices and can be configured to raise an alert if a problem does occur. Stack driver logging collects startup and runtime data concerning applications running on devices. That logging data can also provide an important source of device-related application analytics. Pipelines manage data once it arrives on Google Cloud Platform. Data computations can be added to the pipeline, thereby applying streaming analytics to the data while it's still in the processing pipeline. Data checks can also be added. for example, averaging data across several devices. And data transformations may also be performed, like converting data from one format into another. You can enhance data by combining device-generated data with device metadata or other data sets. For example, you could combine device-generated data with traffic data for analysis. The processed data can also be stored in desired final storage locations. The Cloud Dataflow service is capable of performing all of these pipeline tasks, whether batch or streaming data. Cloud Dataflow also has native connectors to Cloud Pub Sub, as well as several storage destinations. Data from devices out in the environment aren't necessarily homogeneous. That is, data comes in a variety of forms, formats, and volumes. Cloud Platform has a variety of storage services that can handle data in the form of unstructured blobs like images or video using cloud storage, structured data storage with Cloud Data Store, and fully managed high-performance datasets with Cloud Bigtable. Some analytics can be performed while still streaming in Cloud Dataflow pipelines. However, a lot of important analytics processing is performed over data that's been accumulated across multiple storage systems. BigQuery is a fully managed data warehouse service that has a familiar SQL-like interface. With BigQuery, you can analyze aggregated real-world data from several devices. Cloud Dataprep offers a fully managed cluster solution for running big data solutions like Hadoop and Spark, and supports integrated adapters to other cloud platform products and services. The value of device-generated data might extend beyond its original purpose. Cloud Data Lab offers an interactive data workbench enabling the exploration of datasets. It uses a notebook approach, which means that you can combine code, commentary, as well as graphs. In this video, we'll explore Dataflow triggers and late data. When Dataflow collects the data in a pCollection class object, it groups that data in what are known as finite windows. Windowing divides the elements in a pCollection by their timestamps. Dataflow requires a way to tell when it's time to emit the aggregated results for each window. Dataflow uses a method called triggers to determine that enough data has been collected in a window. When a Dataflow trigger gets triggered, it emits the aggregated results of that window. Triggers are especially valuable for handling two particular conditions. First, when you want to emit early results, that is, before all the data within a given window has arrived, and when you want to handle instances of late data. Late data is data arriving after the watermark passes the end of the window. Now let's talk about types of triggers. Dataflow has three major types of triggers that can be set for pCollections. Time-based triggers operate on a time reference. This could be event time, which is given by the timestamp on each data element, or the processing time, which is the time when a data element is processed at any point in the pipeline. Data-driven triggers operate by examining the data when it arrives in each window. The trigger fires when a specified data condition occurs. For example, the trigger can be set to emit results from a window once the window has received a specified number of data elements. Composite triggers combine multiple time-based or data-driven triggers. You can set a composite trigger to fire at the point that all triggers are met, like a logical AND, or when any trigger is met, like a logical OR. Time-based triggers include after watermark and after processing time. These triggers take a time reference in either event time or processing time and set a timer based on that time reference. Cloud Dataflow currently provides only one data-driven trigger, and that's the afterPane.elementCountAtLeast trigger. This trigger works on a straight element count. It fires after the current pane has collected at least some number of elements. The afterPane.elementCountAtLeast method is a good way to cause a window to emit early results before all the data has accumulated, especially in the case of a single global window. With composite triggers, you can add additional early firings or late firings to afterWatermark.past end of window. Repeatedly.forever specifies a trigger that executes forever. Anytime the trigger's conditions are met, it causes a window to emit results, then resets and starts over. It can be useful to combine repeatedly.forever with .or finally to specify a condition to cause the repeating trigger to stop. After all takes multiple triggers and emits when all of its argument triggers are satisfied. This is equivalent to a logical AND operation for multiple triggers. When setting windowing and trigger configuration, you can apply allowed lateness by using .with allowed lateness and specifying a particular duration. In this demo, we'll install the Java JDK on a Windows 10 machine. If you're going to build a pipeline using Cloud Dataflow SDK, and you're going to use Java as the programming language to build that pipeline, then you'll need the Java development kit installed on your machine. So that's what we're going to do. So I have the README open for this video in my Notepad++ text editor here. And you can see the first instruction is to install Java JDK on Windows 10. So let's go over to a browser. Now I got to this page simply by doing a search for Java JDK 8 download. And you can see the first link that it returned is actually the page that we want to go to. Okay, and then scrolling down, what we have to do is we have to click on Accept License Agreement, and we're going to install this version, Java SE Development Kit 8U162. So click on the Accept License Agreement radio button there, and then search for the correct binary. And for me, it's a Windows 10 64-bit machine, so this is the one that I would download. So if I click on this link right now, it will download to the Downloads folder for this browser, which is over here. And you can see I've already downloaded that to save us some time. So to start the installation, just double-click the binary. If you see a user account control dialog, just click yes. Okay, and up comes the installation wizard. Now, like I said, it's a very simple install. So just accept all the defaults and just click next and next and next all the way through. So this is the installation location. And you can see that it's pointing to JRE 1.8. What we're going to do is when we create our Java home environment variable, we're going to point it to the JDK directory because it includes the Java compiler as well, which we'll need if we're going to use the Cloud Dataflow SDK. So we'll leave the default here, that's fine. And we'll just click again, next all the way through and allow this to install. Okay, so now that that's complete, we'll click on Close to close the installation wizard. Now let's go back to the README and see what the next step is. So the next step is to create a Java home environment variable. Okay, and we're going to point it again to this directory. So I will highlight that, right-click, select Copy. So I've copied that. And now I just want to go back over here to File Explorer, and I'll paste that into the address bar in the File Explorer and press Enter. And you can see that this is our installation for the JDK. And here's the bin directory. And we're going to set that bin directory to our path. So as you can see here, it contains a lot more than just the JRE. It contains the Java compiler here as well, which is, again, what we'll need in order to use Cloud Dataflow SDK to build a project, right? So let's go over to the Start menu. We'll click Start. Now there's a couple of ways. You could actually press the Win key and pause, but I prefer to just click Start, type env, and you can see the first link, this match, edit system environment variables control panel link. So just click on that. Up comes the system properties dialog. Click environment variables. And here's Java home. Now I've already created this, so you're going to want to do the same thing. And in order to create it, all you do is you just click new, and then for the variable name, you enter that name, Java home. And for the variable value, you're going to point it to the C:\program files Java JDK 8.1.0_162. Okay, and then the other thing that you'll need to do, scroll down a little bit, find the path system variable and double click to bring that up. And now what you want to do is scroll down to the bottom and create an entry here, %Java home %/bin. So that will just go and grab the value in the Java home environment variable and append /bin to it, so that we now have the bin directory for the JDK version that we installed in our path. So let's click OK, OK, and OK again. And go back to the README. So we've done this. We've done this as well. We added %Java home %/bin to the path system environment variable. So now let's open Command Prompt or PowerShell and confirm that our installation worked. I prefer PowerShell, so I'm going to click to start PowerShell. I'll maximize it, and I'll clear the screen. And now I'll type Java-version, and there's our Java version. CLS, press Enter again to clear. And now we need to make sure that we've got the right directory. So we're going to issue Java C-version. This should give us our compiler version as well, and it sure does. So clear the screen, CLS, and press Enter, and we're done. So now we've got our Java JDK set up on this Windows 10 machine. In this demo, we'll install Apache Maven on a Windows 10 machine. If you're going to use Cloud Dataflow SDK 2.2 and Java to build your pipeline, you're going to want to use Apache Maven. Apache Maven is a tool that can be used for building and managing any Java-based project. So let's get started. I've got the README open in my text editor here for this video, and I'm just going to go to the URL maven.apache.org/download.cgi, and you're going to get this file. Okay, so let's go ahead. Let's go over to the browser, and you can see that I've got that URL open here, maven.apache.org/download.cgi. And now scrolling down the page, you're going to want to download the binary zip archive here. That is a link. So if you just click on that, that will download to the downloads folder for your browser. Now I've already done that to save us a bit of time. I'm going to go over to File Explorer and show you. So here it is. It's the bin.zip file. And now what you're going to do is just unpack that. And it doesn't matter where you unpack it. Just make note of where you're going to unpack it, because that's going to be important. Once you've unpacked it, you're going to add a reference to the bin directory for Apache Maven to the path system environment variable. So what I've done is I've expanded this or unpacked it to this directory right here. So you can see that. So I'll double click and double click on bin. And here are the Apache Maven binaries that we'll need. Okay, so again, what we're going to do is we're going to add this path to our path environment variable. So if you go to the one that you've unpacked Apache Maven to, just right-click, select Copy, and now open your System Environment Variable dialog. To do that, just go to the Start menu, click Start, type env, and you'll see that the best match is this one, Edit the System Environment Variables control panel. So let's click on that and open up System Properties dialog. Click on Environment Variables, and under System Variables, scroll down and find Path. And you'll see here that I've already set my Java home, and I've got Java installed as well. But now, double-click Path, and what you're going to want to do is you're going to want to add that bin directory here. So just click New, right click, paste that directory in, click OK. So if you want to just double check, make sure that it did take, and it did. And click OK to close all those windows. And now go back to the README and check this out. So what we're going to want to do now, we're going to want to make sure that Maven was installed and its dependency on Java will come into play here. So for example, here, you're going to issue a Maven or mvn-v command at either PowerShell or command prompt. I'm going to open PowerShell. I'll maximize the window. CLS to clear the screen. I'll type nvn-v. Okay, and you can see the version of Apache Maven that's installed. It tells us our Java version and some other information. So we have successfully installed Apache Maven, so we can now use Cloud Dataflow SDK 2.2 to create a pipeline. In this demo, we'll install the Google Cloud SDK. If you're going to build a pipeline on a Windows 10 machine, or any other operating system for that matter, if you're going to use Java as the programming language for your pipeline, and if you're using Java, you'll want Apache Maven, and you'll also want to install the Google Cloud SDK. So that's what we're going to do in this demo. I've already got Java and the Java Development Kit 8 installed on my Windows 10 machine. I've also got Apache Maven installed and set up. So now I'm ready to install the Cloud SDK from Google. So to do that, let's go over to Google Chrome. And here is the URL that you're going to want to go to, cloud.google.com/sdk/docs/quickstart-windows. And then click on this link, and that will download the installer. Now, I've already done this to save us a bit of time. So I'm going to go over to my downloads folder for this browser. And here's the Google Cloud SDK installer. So double click this executable to start the installer. And in the setup wizard, just click next. Agree to the license terms. We'll make this available to all users on this machine. So I'll click all users. I'll click next. If a user account control dialog appears, just click yes. We'll leave the default installation directory. Click next. Now make sure that you've got bundled Python here, as well as Cloud Tools for PowerShell. And you can also include any beta commands if you want to use some beta commands. Let's go ahead and click that. And we'll click install. Okay, so now it's telling us that the Cloud SDK has been installed. So let's click next. And now you'll want to make sure that you have run gcloud init to configure the Cloud SDK checked here, and also start Google Cloud SDK shell. So with those checkboxes checked, click finish. Okay, and now basically it's going to ask us if we want to use these account settings. Now, the reason these account settings exist is because I have already been in here one time before with this installed. I uninstalled it for this demo. But what we're going to want to do is we're going to want to create a new configuration. That's number 2. In your case, if it's the very first time that you've installed it, you're not going to see this particular message. You're going to see a message indicating that you are going to authenticate to the cloud with gcloud init. So we'll select option 2 by pressing 2 on the keyboard and pressing enter. And here's the configuration name. The naming details are as follows. Start with a lowercase letter, contain only lowercase letters, A to Z, and digits 0 to 9 and hyphens. So let's call this OK, and we'll press enter. Okay, and it tells us that our current configuration has been set to that configuration. And now we're going to log in, not with this email, but with a different email. Okay, so now we're going to log in with a new account, so we'll select option 2 and press enter. Okay, so I've specified my email. I'll click next. Now I have to specify my password, and It's cached already on this machine, so I'll click Next. I'll save that. And Google Cloud SDK wants to view and manage applications deployed in the App Engine, Compute Engine resources, as well as Cloud Platform services. We'll click Allow. And we are now authenticated to the Cloud SDK. So let's go back to Command Prompt. And now we want to click a cloud project to use. So we could choose any of these projects or create a new project. So why don't we go ahead and create a new project? We'll select option 5 by pressing 5 on the keyboard and pressing Enter. Now we have to give it a project ID. Okay, so let's call this GCDE-1002 and press Enter. Okay, so as you can see here, that commands that require authentication will use that email that I specified, and commands will reference this project by default. So let's clear this by typing CLS and pressing Enter. And that's it. Okay, so now we've successfully installed the Google Cloud SDK. In this demo, we'll implement a streaming pipeline with Cloud Dataflow SDK and Java. Okay, so we have a lot to do. Let's get at it. First, we have some prerequisites you can see at the top here. So we need Java JDK installed. We need Apache Maven. We need the Cloud SDK installed and shell initialized and working. And we need to enable these APIs. Now, I've already done that, but I'm going to go over to GCP. That's Google Cloud Platform, and I'll call it GCP going forward. So I'm going to go over to GCP just to show you how to enable one of these APIs. Let's go over to the browser. I've logged into my GCP account. So I'll click the burger menu. I will scroll up and find APIs and services and click on that. I will click Enable APIs and Services. And now let's search for Dataflow. So there's the Dataflow API. So I'll just click on that API. And you'll see that it's already enabled, like I said. And you can see the Manage button here. And it tells us the API has been enabled. So again, I've enabled all these APIs. If it wasn't enabled, this button would be Enable, right? So you're going to do that and enable all of those APIs that we just referenced in the README. So let's go back to the README and have a look at the next step. So now with the prerequisites out of the way, we need to create a bucket in cloud storage, and we need to create output and staging folders under the Google Storage bucket. So I've already done that too to save us some time. Let's go back over here, click on the burger menu in GCP. I'm going to scroll down, find and click on storage. And here's the bucket I created. It's called mybucket-1002. So click on that, and here's the folders that I created. Now to create a bucket, it's pretty simple. I'll just go back to buckets. You just click Create Bucket, specify a name that is unique across cloud storage. So that's why I had to give it a somewhat cryptic name there. And then leave the defaults and click Create, and that's it. Then you create your folders. And to create your folders, once in the bucket, you just click on Create Folder. That's simple. Okay, so back over to the README. So next we're going to create a Maven project that contains the Dataflow SDK for Java, and we're going to use the Maven archetype plugin. Note this, we're also using the caret character to separate multi-line commands like you see here. And the reason why I'm doing that with the caret character is because the Cloud SDK shell that I'm using is based on the command prompt. And that is how you separate multi-line commands. So first, let's go over to Cloud SDK shell. And you can see that I have pinned this to my taskbar. But you can also find it in your Start menu. If you click Start, if you just recently added it like I did, you'll find it at the top here. Or you could use Cloud Tools for PowerShell, but not with the particular line separator that I've used. So that's why I'm using Cloud SDK shell. You can also find it if you scroll down under Google Cloud SDK, click the down arrow, and you'll see those two options there. Okay, so let's click on Cloud SDK shell in the taskbar. I will maximize this. What I'll do is I'll also go to the root of C. I'll type cd, C:\\, and press Enter. Clear this. Okay, and now I'm going to go and copy that command. Okay, so you can see here I've specified version 2.2.0. The group ID is com.google.cloud.dataflow. Okay, and it's actually going to create this first -dataflow directory for us. And we'll in fact be CDing there in a moment. But right now, let's highlight this command, right click, select copy, over to Cloud SDK shell, right click to paste that in, and let's generate that project by pressing enter. Okay, cool. So that project has now been created. So let's type CLS to clear the screen, press enter once more, back over to the README. Okay, and looking at this comment, you'll see after the previous command, you should see a new directory first, Dataflow, under your current directory. And we do. And that's a directory that contains the Maven project that includes the Cloud Dataflow SDK for Java and the example pipeline. Let's just go back here and do a dir on f star. And there you see the first Dataflow directory. So if we do dir first Dataflow /star, has to be backslash because it's Windows. Okay, so we'll see that XML file, which is basically a manifest for our project. Okay, so let's clear this now. CLS, press enter, back to the README, and now we need to CD into that first Dataflow directory. Then we're going to build and run the Cloud Dataflow example pipeline. It's called word count, and we're going to use the Cloud Dataflow service. So we're doing this remotely just to demonstrate how this works. So let's make sure that we've got the right project. So let's go over to GCP. Here's the project. And we've got the bucket, which is named mybucket-1002. Okay, so back over here, just to verify, there's the project, and there's the bucket. Okay, so now let's copy this command. We'll highlight the whole thing, right-click, select copy, and now let's go back over. Okay, with that copied, what we need to do is we need to, again, remember, we need to CD into that first -dataflow. Press enter, type CLS, and press enter to clear the screen. Now right-click to paste that command in here, and now let's press enter. Okay, so it's building our project, our streaming pipeline. You'll see a number of different messages here. But if you follow down through the process, you'll see how it's creating the Dataflow components, how it's starting workers, and so on. So we'll just let this run through. Now, while we're waiting for that to finish, let's go over to GCP again. Click on the burger menu. Now we'll scroll down, and under Big Data, we'll click on Dataflow. So let's click the burger menu, and right now we're on storage, but let's scroll down, and under Big Data, we'll click on Dataflow. And here's our job, and you can see that it's running. So that's the job that we created to instantiate our pipeline. And if we click on this, we can see even more details about it. So we can see the steps that it's taking right now. We can see some information about the job itself, like the job summary, any auto scaling, as well as some resource metrics, counters, pipeline options, and so on. Okay, so let's go back over to Cloud SDK shell and see what's going on there. So you can see a number of different messages here. And now the current message is stopping worker pool. So it's just cleaning up and finishing up the building of this batch pipeline for us. But if you scroll up through, you can see all of these different messages. You can see the Dataflow runner, run, and so on. So again, let's go back over here to the browser. Go back and we'll see that that job is in fact still running. And it'll be running for a couple of minutes probably. And once it's done, it'll shut everything down. We'll see the status change from running to succeeded. And now after I refresh the page, I see that the status is now succeeded. If I drill down, and I'll see how much time it took for each step in the job. So now the proof is in the pudding. Let's go over to our bucket. So we'll click the burger menu, scroll up, and select storage. And here's the bucket that we use. Let's click there. So here's the output. We can see the output here. So let's click on this one and see what words were discovered. And there they are. Now we'll also see in the staging area a bunch of files that set up our pipeline. So that's it. We've successfully created our pipeline. Now, it's always a good idea to clean up after yourself so as not to incur any additional charges. So in Google Cloud Storage here, click on Buckets, and now click Bucket and click Delete if you want to delete that bucket and not be charged for storage. I'll leave it unchecked for now. The thing is about jobs, there is no way to delete a job at this point, but a lot of admins, including myself, have asked for it from Google, and it may happen eventually. But for now, if you want, you can delete the project and everything goes away. But you have to be careful if you're going to do that too, because if there are resources that you want to use later, once you delete the project, they're gone. So just keep that in mind. In this demo, we'll implement a streaming pipeline with Python. Okay, a couple of prerequisites. I have the README for this video open in my text editor, and here are the two prerequisites. So first we have to activate Google Cloud Shell on Cloud Platform, and we have to enable these APIs. Now I've already enabled them, but I'll show you how to enable those quickly, and we'll activate Google Cloud Shell on Cloud Platform at the same time. So let's go over to the browser. I've logged into Cloud Platform. First, we'll click the Activate Google Shell icon in the toolbar. And while that's connecting, I'm going to click Open in New Window to pop that into a new tab, and I'll go back to Dashboard. And now we need to enable all those APIs, so click on the burger menu, find APIs and Services, and click on it. Click on Enable APIs and Services, and then just search for the APIs. It's pretty simple. Just Dataflow API. We don't even have to type API in there. The Dataflow API tile is the only one that shows up, so click on that. And on this page, if it's already enabled, you'll see this API enabled, and this blue button would be Enable instead of Manage. So again, to save us some time, I've already enabled those. You don't need to watch me enable all those APIs. Let's go back to the dashboard. And now we're into our first step, which is creating a bucket in cloud storage. So I'll just go back over here to the README again. So this is where we're at. And we're actually going to do these next two steps at the same time. Although I've already done them. I'm actually just going to show you how to do that. Okay, so let's quickly go over here, back to Cloud Platform, click on the burger menu, scroll down and find Storage. Under Storage, click Browser. Here's the bucket. To create a bucket, you just click Create Bucket, specify a name, note that it must be unique across cloud storage, and leave the other settings at their defaults and click Create. So again, there's my bucket. Once you've created a bucket, you can create folders quickly and easily by just clicking on Create Folder. So you drill down into the bucket and then you click on Create Folder, specify the name, and click Create, and you're done. So again, I've already created all of the folders that I need. So there they are right there. The next step is to check the Python version. And note here in the comment, we need Python version 2.7 and we need pip version 7.0.0 or newer. And as this comment says, because we're using Cloud Shell, this should be all set up and ready. So let's go check on Python version and pip version. Back to Cloud Platform, over to Cloud Shell. So Python -- version. So 2.7.13 and pip -- version. And there you see, ready to go. Version 9. So let's clear this by typing CLEAR and pressing enter. Okay, so back to the README. The next thing we need to do is install Google Cloud Dataflow. Let's highlight this command right click, select copy over to Cloud Shell, click inside the Cloud Shell and press Ctrl V to paste that command in. And while that's installing, go back to the README. The next thing we're going to do once that's done is we're going to set up some environment variables. So for example, we've got output file here is going to be tilde/my_output. And we're going to set up project, and that's the project ID. And we're going to set up bucket, and that's the URI for the bucket that we just created. Let's highlight those commands, right click, select copy. And we see that it's done. Okay, so let's type clear to clear that and press enter. Okay, so clicking inside here again, Control V to paste those in. And now we've got our environment variables set up. So what we'll do is we'll just echo one of them back. So let's echo back bucket, for example. Echo $bucket. And there you see it echoed back. So our environment variables are now set up. Next step is to run the word count Python example, the pipeline example, locally. And by locally, we actually mean in the Cloud Shell session that we have here. So we'll find the output here. So if I type ls right now, I've got one file, the readme-cloud shell. And when we're done, we're going to have an output here. Just open up the README again. So we set up this output file as tilde_my_output. And what we're going to do is we're going to run this command. This is going to run our word count Python example locally. And the output is going to be $output file. So it's going to get that information about the output file from the output file environment variable. Okay, right-clicking that, selecting copy from the context menu back over to Cloud Shell, and we'll paste this in with Control V. And wow, that was very quick. So it gives us a summary. So you can see that summary down here, these last 3 lines really. And here, especially the second last line, number of empty lines 1663, average word length is 4. So now if I type ls, I'll see that I have a my output file. First, let's clear this by typing clear, pressing enter. And again, there it is, my output. So what we'll do is tab cat my output and press enter, and there is the output. So there are all the words that the word count Python found. Okay, so that's our streaming pipeline locally. So let's do it on the Cloud Dataflow service. So let's clear this again by typing clear and pressing enter. Back over to the README. And there's an interesting comment here that I make, and that's the fact that if you look at this command, basically what we did was we called Apache Beam. And it appears that we're using Apache Beam. And, well, we are, even though we installed Google Cloud Dataflow, in fact, Dataflow is a distribution of Apache Beam. So that's why we call that with Apache Beam. Okay, so now we're going to run the same job remotely. So I'll highlight this command. So here we are. We're calling Apache Beam.examples.wordCount. There's our project. Remember the environment variable. The runner is Dataflow runner. Staging location, temp location, and the results are going to be in the results/output. So let's right click, select copy over to Cloud Shell, Control V to paste in the command and press enter. Okay, and we should see that job coming up. Okay, so it says job state running. So if we go over to Cloud Platform Console, click on the burger menu, scroll down, way down under Big Data, find Dataflow and click on that. And here we are. This is the job that we just created that's running. That's our streaming pipeline. So let's click to open up that job, and you can see the steps in the job. So it's starting. Go back here, and the status is running. Now when that's done, it will, like this other job, report succeeded here instead of just running. So while it's doing that, go back to the README, just a couple of things. We'll wait for that to finish. But here, at the bottom of this README, especially the note here, it's always a good idea to clean up after yourself. And you're going to incur charges for storage only. You're not going to incur charges for a job that's just sitting there doing nothing. But the problem is that you can't just delete a job at this point in Cloud Platform, even from the Cloud Shell. So even though that can't happen, you're not going to be charged for an empty job, or a job that's not running, that is, but you will be charged for storage. So when you're done, you may want to delete the bucket that was created for the demo, or you can delete the project entirely. But just keep in mind, if you delete the project, if you have resources in that project that you need later, then they're going to be gone if you delete the project. Although you can restore it within 30 days, but for all intents and purposes, just remember that deleting a project is deleting a project. It means that everything in it is going to be gone with a 30-day grace period. Okay, so let's go back over to Cloud Platform, see what's going on here. Let's drill down. Okay, and we can see that it's running. It's auto-scaled the workers up to 1, so it's running that job remotely. Okay, and now if we go back over to Cloud Shell, we'll see the message here. Workers have started successfully. So it's running right now. So it starts, it auto-scales to 0 because it doesn't need any workers. It's just starting up. Then it auto-scales to 1 because it needs that worker. Now, if this were a very intensive application, it would scale up for us. The bottom line is that it has started and it is running. Go back over here and we'll go back to the Dataflow page, and we'll wait till the status here says succeeded. Okay, so our job has succeeded. Go over to Cloud Shell and we'll see here that, remember when we ran it locally? Well, there are the same numbers as when we ran it locally. Okay, so let's clear this by typing clear and pressing enter. Go back to the dashboard. We'll click on the burger menu and we'll scroll down. We'll click storage. Click on my bucket. Okay, so now we have some results here. So let's click on results. And here are our results. Let's click on one of these files. So it just stores these words in here. So the word count found this number of words. And we could go through each of these. We're going to find that they each have different data in them. So that's the output. So that is the result of our word count streaming pipeline using Python. In this exercise, you'll practice what you learned about feature engineering and streaming. You will describe the concepts of feature engineering, describe the process of input selection in feature engineering, describe Dataflow triggers and late data, and describe the components involved in real-time stream processing. Now pause the video and perform the exercise, and when you return, we'll go over these exercise tasks. Task 1. Describe the concepts of feature engineering. First, feature creation or feature engineering is a process where we try to create additional relevant features from our data. that are over and above the existing raw features. What we're trying to do here is improve or enhance our training data in order to increase the predictive power of our machine learning algorithm. And we also have feature selection. And this is a process whereby we select a key subset of our original data features. The goal here is to simplify the training problem by reducing dimensionality and eliminating redundant, irrelevant, and non-useful data. Task 2, describe the process of input selection in feature engineering. We have an input dataset, then an engineer typically writes new feature code, then applies it to a sizable raw dataset. The feature code is executed in a scan of the data. And I made a comment that this step can be time-consuming, so just keep that in mind. So the results of this step include a training dataset delivered to a machine learning system, and then the resulting trained model's accuracy is evaluated, typically using a set of human-labeled examples. If the model is considered good enough, then we have a quality function. Otherwise, we return to alter the feature code and repeat this cycle until we're satisfied and we have a quality function. You should also be aware that there are 3 types of methods of input selection. There's filter methods, and these filter methods pre-process features by measuring characteristics of the data statistically to make feature selections. We have wrapper methods, which can be used to score different subsets of features according to their predictive capabilities, typically applying cross-validation to make feature selection, and embedded methods. Embedded methods combine filter and wrapper methods and are executed by algorithms that have integrated feature selection methods. Task 3, describe Dataflow triggers and late data. When Cloud Dataflow collects the data in a pCollection class object, it groups that data in finite windows. Windowing divides the elements in a pCollection by their timestamps, and Cloud Dataflow requires a way to tell when it's time to emit the aggregated results for each window. Dataflow uses a method called triggers, and triggers are used to determine that enough data has been collected in a window. When triggered, it emits the aggregated results of that window. And triggers are especially valuable for handling specific conditions, and these specific conditions include emit early and late data. When you want to emit early results, it means that you want to emit results before all the data within a given window has arrived. When you want to handle late data is data arriving after the watermark passes the end of the window. You should understand the 3 types of triggers. Okay, so there's time-based triggers that operate on a time reference. And this could be the event time or the processing time. Then there's data-driven triggers, which operate by examining the data when it arrives in each window. And we have composite triggers, which combine multiple time-based or data-driven triggers. Okay, task 4, describe the components involved in real-time stream processing. Recall, real-time stream processing typically is used to manage and process streams of data that could come from millions of intelligent devices and sensors in the Internet of Things. Therefore, a platform suitable for real-time stream processing must be able to handle importing the data, that's one component, processing the data, that's another component, storing that data, third component, and the fourth component involves analyzing it. It's also interesting to note here that with real-time stream processing, in the context that we're talking about Internet of Things and devices and sensors, this could mean that you have events numbering in the hundreds of millions per hour. In this video, we'll consider watermarks, triggers, and accumulation in stream operations. When Dataflow collects the data in a pCollection class object, it groups that data in finite windows. Windowing divides the elements in a pCollection by their timestamps. Dataflow requires a way to tell when it's time to emit the aggregated results for each window. And given that time skew and data lag will occur, Dataflow uses a method called triggers to determine when enough data has been collected in a window. When triggered, the aggregated results of that window is emitted. Each is considered a pane. Triggers are helpful for handling certain conditions. For example, when you want to emit early results. And what that means is before all the data within a given window has arrived. And another condition is when you want to handle instances of late data. Dataflow triggers offer a number of methods to determine when to emit the aggregated results of a given window based on a system's data processing requirements. So, when should data be emitted? Here are some considerations. Some systems require rapid or time-sensitive updates. In this scenario, a strict time-based trigger emitting a window every few seconds might be chosen. We say that this type of system favors promptness over data completeness. Other systems may value data completeness over the exact timing of results. In this scenario, a data-based trigger that waits to accumulate a specified number of data records would be used. In either scenario, triggers can be used to handle late data or to emit early results, whatever the system requirements indicate. Dataflow has three major types of triggers. Time-based triggers operate on a time reference. This could be event time, which is given by the timestamp on each data element, or processing time, which is the time when a data element is processed at any point in the pipeline. Data-driven triggers operate by examining the data when it arrives in each window. The trigger fires when a specified data condition occurs. For example, the trigger can be set to emit results from a window once the window has received a specified number of data elements. Composite triggers combine multiple time-based or data-driven triggers. You can set a composite trigger to fire at the point that all triggers are met, like a logical AND, or when any trigger is met, like a logical OR. Now let's consider watermarks. Time-based triggers use a time reference from either event time or processing time. They set a timer that is based on the appropriate time reference. Dataflow uses a watermark to track the arrival of data in a pipeline. The system considers a watermark to be the point when all the data in a particular window can be considered to have arrived in the pipeline, and the window is subsequently closed. One time-based trigger is after watermark. This trigger takes a time reference based on event time. It will emit the contents of a window once the watermark exceeds the end of the window. The watermark is considered a global progress metric. It's Dataflow's idea of input completeness at any point within a pipeline. The pCollection object's default trigger is event time-based. So, again, it emits the results of the window when the watermark exceeds the end of the window. Now, let's consider window accumulation mode. When specifying a trigger, you also set the window's accumulation mode. When a trigger fires, the current contents of the window are emitted as a pane. Because a trigger can fire multiple times, the accumulation mode specifies whether the system will accumulate the window panes when the trigger fires or discards them. You can set a window to accumulate panes generated when the trigger fires by invoking accumulating fired panes when you set the trigger. Similarly, you can set a window to discard fired panes by invoking discarding fired panes when you set the trigger. In this demo, we'll configure storage, BigQuery data, and PubSub in support of a streaming data pipeline. Okay, the first thing to do from here in the README file you can see is to enable these APIs. Now I've already got them enabled, but I'm going to show you quickly how to enable one of them. We'll select Dataflow here. Let's go over to Cloud Platform. I'm logged in under my account. I can either click on this tile or I can click the menu, console menu, and select APIs and Services. And I'll click Enable APIs and Services and just search for Dataflow. And there it is. And then click on that tile, and you'll see here that my account has it enabled for this project. So otherwise, this would be an enable button. So again, that's how you enable those APIs. Okay, so first things first, we're going to go and create a bucket. And keep in mind that that bucket has to be given a unique name across the entire cloud storage ecosystem. So make sure that you do that. Now, what I've done, I've already created that too, but I'm going to show you how to create one anyway from scratch. So let's go over to Cloud Platform again. We'll click on the menu, scroll down, and we'll click on Browser under Storage. Okay, so here's the bucket that I created, and I gave it a name based on my project ID. So that's unique across cloud storage. So to create the bucket, just click on Create Bucket, specify a name, a unique name, and it tells you here unique across cloud storage. Leave multi-regional selected, typically United States, and then click Create. And that's all there is to it. So here's my bucket. Now if I drill down here, you can see that I've also created a folder. So that's one of the other steps that we were going to do, is create a folder. And to create a folder, very simple, just click Create Folder, give it a name, and you're done. Okay, so let's go back to the README. And you can see here, create a folder in this bucket named Weather Data, and I did that. And then upload the file named myweatherdata.json to the new folder. And it tells you that that JSON file is located in the same directory as this README. Okay, so go back to Cloud Platform. I'll click to drill down inside the weather data folder. And you can see I've already got that file here. But what I'm going to do is I'm going to click Upload Files. And here I'm in the directory for this video. And I'm going to click on myweatherdata.json. Now it's going to complain, it's going to ask me what to do. I'm going to replace the existing object. So I'll click Replace Existing Object, click OK, and we're good. All right then, next step, we're going to create a data set and a table to hold our weather data. Essentially, this is like setting up a data warehouse to receive weather data. Okay, so first thing we need to do is navigate to BigQuery. So let's go ahead and do that. Over to Cloud Platform, we'll click on the menu, and you can see I've got BigQuery pinned to the top here. You can also scroll down, and it's all the way down under Big Data. We'll click on BigQuery here. Okay, so now click on the down arrow beside the project name, and then select Create New Dataset. And for this new dataset, we'll give it the name Weather Data. For location, we'll select US, and we'll leave the data expiration at never, and click OK. Okay, so now click the plus sign next to the newly created weather data dataset, and we're going to create an empty table. So click Create Empty Table. And for destination table name, this first part, that is the dataset name. So the table name, this one's going to be Weather Data Table, or TBL. So Weather Data TBL. Now, under Schema here, we're going to click Edit as Text. And let's go over to the README. Okay, and you can see here, Edit as Text, and use this for the schema by pasting it in the schema box. And this is what we're doing here. So this is our schema. Let's highlight this entire line, right-click, select Copy, and let's go back over to BigQuery, and we'll replace what's in there now by highlighting it and then pressing Control-V. Okay, that looks good. So now we can click on Create Table. And you can see the schema of our new table. So at this point, we have set up a data warehouse that can receive weather data. So now let's go and configure Cloud Pub Sub, and we'll configure a topic. Okay, so let's go ahead. Go back over here to Cloud Platform. And again, under Big Data, we'll just click on Pub Sub. And we'll click Create a Topic. And we'll specify here weather data. And notice I didn't capitalize it that time. Okay, so let's click Create. And you can see the message that that new topic has been created. Okay, so what we've done then is we've successfully configured our cloud storage. We've configured BigQuery as our data warehouse to receive weather data, and we've created a pub subtopic. So that way we can have services subscribe to the topic, and we can have data fed into BigQuery tables that we've defined. In this demo, we'll configure a cloud function in support of a streaming data pipeline. Okay, so I have the README open for this demo, and you can see that we've got some prerequisites here, and let's go over to the prerequisites.txt file, and here they are. So basically enabling these APIs, creating a bucket, a folder called weather data, and uploading a JSON file called myweatherdata.json to that folder. Then you need to create a data set and a table to hold our weather data that we'll be creating. And this is the schema. So in BigQuery, you are going to create a table using that schema definition there. Then create a pub subtopic. Okay, and that way we'll be able to have services subscribe to it, and we'll be able to deliver messages or data over to BigQuery. Okay, so let's go over to the README. So from Cloud Console, we're going to go to Cloud Functions under Compute. Okay, so here we are in Cloud Console. I'll click on the burger menu, and let's see, I'm going to scroll up, and under Compute, you'll see Cloud Functions. So I'll click on Cloud Functions. All right, and let's click Create Function. And for a function name, we'll specify function dash weather pub sub to BQ for BigQuery. So that's weather pub sub to BQ. Okay, now in the trigger section, we're going to select Cloud Pub Subtopic. And in the topic dropdown, we'll select weather data. And that was part of the prerequisites creating that topic. So we'll select that. Now make sure that inline editor is selected here. And in the index.js tab, what we're going to do is we're going to paste some code over what's here. So if we click on this icon, we can open in an expanded editor window. So let's do that. I'll click here. And what I'll do is I'll go over to the README, and here's the code that we're going to put in there. Now, this code consists of a lot. So basically what we do is we specify the project ID, and this is my project ID, the dataset ID, and the table ID. And these are constants defined in this code, right? So that doesn't mean you actually take a dataset ID and a table ID, right? So you're going to use the table name and the dataset name. All right, and then basically what happens is this code is actually just ingesting the data, and that data is in a JSON format. So it goes and parses that JSON resource and creates the data based on that. And you can see down here it inserts the data into the table. Okay, so that's good. Let's go ahead and grab that all the way down to here. So we'll right click, select copy. Let's go back over to Cloud Platform. We'll highlight everything, press Control V to replace it all. And now click on package.json and back to the README. And now in package.json, we're going to paste this code over the placeholder code that's there by default. So let's highlight this whole code snippet, right click, select copy. Now let's go back over to Cloud Platform, highlight everything in there we want to replace it, and press Ctrl V. Okay, so click OK. Now under function to execute, make sure that that's subscribe. Okay, that needs to be subscribe. And now we can click create to create that function. Now keep in mind that it might take a couple of minutes for the function to show up as deployed. So I'm going to pause the video at this point, and when it's finished, I'll resume. Well, there, that is published and now ready. So that didn't take very long at all. Actually, it only took a few seconds that time. So now at this point, what we've got is we have connected PubSub to BigQuery via this function. In this demo, we'll walk through the process of building a streaming data pipeline with Cloud Dataflow. Okay, so this demo has some prerequisites. And those prerequisites are here in the prerequisites.txt file in the same directory as this README. So if I click there, you'll see that these prerequisites include configuring or enabling APIs, creating a bucket, a folder, and uploading a data file, creating a dataset and a table in BigQuery to hold our weather data, creating a pub subtopic, and creating a cloud function to tie those things together. So what we're going to do is we're going to simulate data streaming by using a data set that's stored in cloud storage, and we'll feed it into the new pub subtopic that was created, and that's part of the prerequisites, remember. We'll use Cloud Dataflow and integrate a Google template for reading from cloud storage and for publishing to PubSub. Okay, so from the Cloud Console menu, select Dataflow under the Big Data section. So let's go ahead and do that. So all the way down under Big Data, we're going to click on Dataflow. Now we'll click Create Job from Template, and now we have to specify some values. So for the job name, we're going to specify Dataflow-GCS-PubSub. And the region we shouldn't have to change. It should be auto-selected according to where the project is hosted. And for Cloud Dataflow template, we'll select an option. So let's click the down arrow here, and we'll select GCS text to Cloud PubSub. Okay, and now we have a few more parameters. So for input cloud storage files, just let me take you back over to the README for a second. Okay, so that's all specified here. So for input cloud storage files, enter your bucket and the JSON file spec that we uploaded earlier. So what I'm going to do is I'm going to copy this. And remember, your bucket will be named differently because the buckets, again, have to be unique across cloud storage, right? So having copied that, let's go back over here. I'll paste that in here. Okay, and you can see that for the file spec, I just specified star.json. That way, if I had more than one data file, it would read them all. Okay, so I'm going to leave that as is. For the output PubSub topic, the path depends on the project name, but it will look something like this. Let's go back over to the README and you'll see. Okay, so it should look something like this. Projects, the project name, topics, weather data, right? So under prerequisites, I named my PubSub topic weather data. So that's what I'm specifying there. If you didn't name yours weather data, then you would have to change that to whatever you named your topic. So mine is this. So I'm going to highlight this, right click, select copy, over to Cloud Platform, and I'll paste that in. Okay, now temporary location. The temporary location should be set to the name of the cloud storage bucket that we created, along with a file name prefix of TMP. So let's go back over to the README again, and you'll see what I'm talking about here. So we set the temporary location to the name of cloud storage and a prefix of TMP like this, right? So mine is actually this. Your bucket again will be different. So if you're following along, use your bucket name. So I'm going to highlight this, right click, select copy, back over to cloud platform, paste that into temporary location, and we should be good to go. So now let's scroll down and we'll click run job. Okay, back over to the README. Now the Dataflow job should start to run, and we'll check on it in a moment here. But it may take a couple of minutes for the job to complete, and it typically does. It takes 2 or 3 minutes. And so let's just go over what we're going to do after that. So once the job has completed, we can view the Cloud Function logs to confirm that the Cloud Function is being triggered by pub/sub. And we do that using a gcloud beta functions command. And there it is. So let's copy that command. So I'll highlight everything, right click, select copy, and let's go back over to Cloud Platform and see if that's completed. Still running. Okay, so what we'll do here is we'll click on Activate Google Cloud Shell, and I'll click this icon to open it in a new window. Okay, so now that's set. Let's go back over and wait for this to complete. Okay, and now you can see that it has indeed succeeded. So let's go over to Cloud Shell here, and I'll click inside Cloud Shell, press Control V to paste that command in. Okay, so basically it's a beta functions command, and it allows us to read the Cloud Function logs to confirm that the Cloud Function is being triggered by pub/sub. So let's go ahead and run this. I'll press enter. Okay, and indeed we see some inserts going on there. So it looks like everything's working. So basically they indicate that the function is executing and data is being received and that is being inserted into BigQuery. So now let's confirm that data is flowing into our BigQuery table. So let's go over to BigQuery, and under the project name we'll click the weather dataset, and over here in the right pane we'll click weather data table. Then we'll click query table, and then what we'll do is we'll specify a select star from our table, and we'll limit it to 1,000 rows returned. Okay, and so our validator shows that our query is good, so let's run the query. And in the confirm query dialog we'll click run query, and there you can see our data. So we definitely have received data from our subscription. So our pipeline is all hooked up and working. So let's just see how many rows we've got. So let's type select count star from our data set when we don't need this limit, and let's run that query. Okay, so basically we inserted 2,935 rows of data. Okay, that's it. Pipeline is complete. So that's a streaming data pipeline using Cloud Dataflow. In this video, we'll explore batch and stream processes. Batch processing is an efficient method for processing large volumes of data. Typically, these are transactions that are collected over some period of time. Batch processing requires different programs for data input, processing, and output. So one example here, think big data analytical processing. Real-time processing, on the other hand, includes continuous input, processing, and output of data. It's near real-time, meaning very, very short time periods. You can think of this as event processing with low latency messaging. For context, consider a couple of examples where we may want to use batching, such as updating or deleting many objects. Rather than send separate API calls, we can group them into a single HTTP request. There is a 100 call limit for each batch request, so if more are required, you need to use multiple batch requests. The batch request format is like this. You have a main HTTP request that uses a multi-part mixed content type. Within the main request, there are multiple parts, each of which contains a nested HTTP request. Each part opens with its own application HTTP content type header, and each part can also have a content ID header. These headers constitute the beginning of a part. They are separate from the nested HTTP request. Consequently, after the server unwraps a batch request into the separate requests, the part headers are ignored. The body of each individual part forms a complete HTTP request with its own verb, URL, headers, and body. The HTTP headers in the outer batch request, excluding content headers like content type, apply to every nested request, not just the outer request. Note, though, that if you were to specify a given HTTP header in both outer and nested requests, the nested request's header value takes precedence and overrides the outer batch request header's value for that nested request. The batch request response is a single standard HTTP response with a multi-part mixed content type. Each part of the main response is a response to one of the requests from the batch. Incidentally, responses follow the same order as the requests. Now, let's have a look at key stream processing concepts. First, data import is a process. It includes getting information from devices to cloud platform services, and the target of the import, that is, what service, depends on the nature of the information. For example, Cloud Pub Sub messaging service uses topics and subscriptions and could be used to handle incoming data streams from devices. Also, since it natively connects to other cloud platform services, it can integrate the import of data, data pipelines, as well as storage. Stack driver monitoring and logging can be used to monitor and log information relating to the health and function of devices out in the field. Pipelines manage data once it arrives at cloud platform, and Cloud Dataflow can perform all pipeline tasks. And key real-time processing pipeline tasks include transforming data, as well as moving data to one or more final storage locations, enhancing or enriching device-generated data with external data or other metadata, as well as aggregation and data computation. In this video, we'll explore streaming analytics concepts. First, we'll consider some components that provide data analytics on cloud platform. BigQuery is a fully managed data warehouse service with a familiar SQL-like interface. With BigQuery, for example, you can analyze aggregated real-world data from several devices. Cloud Dataflow is capable of performing all pipeline tasks, whether batch or streaming data, and it has native connectors to Cloud Pub Sub, as well as other services on cloud platform and several different storage locations. Often, the value of device-generated data might extend beyond its original purpose. Cloud Data Lab offers an interactive data workbench enabling the exploration of datasets. It uses a notebook approach, which means that you can combine code, commentary, as well as graphs. Cloud Dataprep is a fully managed cluster solution for running big data solutions like Hadoop and Spark, and it supports integrated adapters to other cloud platform products and services. Now let's consider BigQuery key concepts. The top-level container in cloud platform is the project, and BigQuery datasets are associated with particular projects. You can stream data into BigQuery rather than loading it using a job. Typically, streamed data becomes available for real-time analysis within seconds of the initial streaming insertion into a table. However, data may not be available for export and copy operations for as much as 90 minutes. To check whether data is available for copy and export, you can check for a section named Streaming Buffer from the tables.get response. If that section is missing from the response, the data should be available for copy and export. In addition, the underscore partition time pseudo column should have a non-null value in this case. To help safeguard data consistency, an insert ID for each inserted row can be set. BigQuery retains this ID for at least 1 minute. If an attempt is made to insert the same set of rows within that time period and the insert ID property is set, BigQuery will use the insert ID property to attempt to deduplicate the data. Now, considering cloud Dataflow key concepts, when executing a pipeline with the Cloud Dataflow Managed Service, the monitoring interface allows you to view and interact with Dataflow jobs. This allows you to view detailed pipeline information, including an execution graph of the pipeline as it is running on the Dataflow service. That's while and after. The execution graph represents each individual transform that occurs in the pipeline. The transforms are contained in boxes on the graph containing the transform name as well as status information. Composite transforms that contain multiple nested sub-transform steps are present and are expandable. A total execution time metric is displayed showing the time each transform is taking, and this provides a good way to diagnose problems in the pipeline. Dataflow service automatically selects the number of worker instances that are required to run an auto-scaling job. And as the number of worker instances change, you can view that information as well as other detailed information about the auto-scaling job in a summary tab provided by Dataflow. Aggregated errors produced in pipelines are displayed in the Stackdriver error reporting interface. The error report includes a list of errors that occurred, along with the error messages, the number of times each error occurred, a histogram displaying when each error occurred, and the most recent time that the error occurred. Stackdriver monitoring offers real-time streaming metrics. With over 1,000 metric data types and the ability to define custom metrics, it can be used to derive information and insight into key metrics about the service, including the performance of cloud platform services. Stackdriver and Cloud Platform store regular measurements over time for each metric type. These measurements are gathered into time series, and you may aggregate data from several time series for an overall view of resources being monitored. Stackdriver monitoring offers alerting policies, so you can be notified when specific metrics fall out of acceptable operating range. Each policy specifies conditions that indicate an unhealthy state for a resource or groups of resources, an optional email, SMS, or other type of notification, as well as optional documentation for some types of notifications that may help troubleshoot issues. As of Stackdriver Monitoring API version 3, you can define filters to filter by time series, assign resources in a group, list group members, metric descriptors, as well as monitored resource descriptors. In this video, we'll consider big data streaming and BigQuery. As you may be aware by now, you can stream data into BigQuery rather than loading it using a load job. To stream data into BigQuery one record at a time, you use the table data insert all method. This approach enables querying the data right away, so you can avoid delays inherent in running a load job. You must have write access to the dataset containing the destination table, and the table must exist prior to writing to it. That is, unless you use template tables, in which case you can use a template table to automatically generate a table to write to. It's also advisable to check the quota policy for streaming data associated with your account so you know exactly how much data may be streamed. One usage pattern that is quite common for streaming data into BigQuery involves splitting a logical table into several smaller tables. You can use template tables to create smaller tables that aren't date-based, and that way BigQuery can create the tables for you. Template table details include a suffix value comprised of letters, numbers, or underscores. There's a quota that applies to all tables. A TTL, or an expiration time, is inherited from the dataset. And deduplication can occur only between uniform references to a destination table. And neither the template table nor generated tables should be views. You can perform analytics on streaming data in real time, for example, to determine some overall trend in the data or to monitor error conditions. But keep in mind that there may be duplicate data, and this may be removed once you are finished streaming. In this video, we'll explore how to use Google Data Studio. Data Studio uses connectors, and these are known as pipes that provide Data Studio data sources access to information stored in datasets. In order to connect to a dataset, you must authorize access first. When you create a data source using a particular connector, it does not grant direct access to others. Once created, only the owner can edit a connection. And authorization can be removed from Google-provided connectors at any time. There are two types of connectors. Flexible schema is one type, and that is a type of connector where the set of fields is well defined. So a couple of examples here include AdWords or Google Analytics. Fixed schema, on the other hand, is a type of connector where the structure of data is unknown. And a couple of good examples here are BigQuery and Google Cloud Storage. Key features include caching. Every component, in fact, in a Data Studio report gets its data from a cache whenever possible. Data Studio allows you to visualize data using configurable charts and tables, and you can also share and collaborate reports and data sources, as they are both stored as files on Google Drive. So in fact, it's easy to share them with individuals, teams, or even the entire world. You can also embed reports in other pages like Google Sites, marketing articles, or blog posts, for example. Another key feature is that you can manage data sources. So for example, you can add or remove data sources, and you can even alter attributes of the data. You can add aggregations, and for example, you can change data types to suit your requirements. For building reports, you create and manage those reports using an intuitive report editor. Data Studio also includes several sample templates and reports to get you up and running quickly so you can learn about the features of each type of component and special features of reports. To create a new blank report, you first add a data source, then you add components with a toolbar. Once you've done that, then you can start changing colors, changing fonts, adding other components. You can add charts, graphs, tables. It is, after all, a full-fledged data visualization tool. You can share reports or data sources with specific users and groups, or by using a shareable link. However, sharing a report does not provide direct access to any of the underlying data sources. Sharing a report also does not automatically share any data sources. Data sources can be shared, but they must be shared separately. And these are the data sources within Data Studio, not the underlying data sources, right? So when you create a data source using a particular connector, again, you don't grant direct access to others. You can't. And once created, only the owner can edit that connection. Those with whom you share a report can view or edit the report, and you grant the permissions that they have, just like sharing a resource in Google Drive. There is no login required for simply viewing a report. However, for editing, a Google login is required. In this demo, we'll build a dashboard with Google Data Studio. Google Data Studio is a visualization tool that allows you to create impactful dashboards and reports with your data. So what we're going to do, we have a couple of prerequisites here. So you're going to enable these APIs. Now, strictly speaking, you really only need the BigQuery API for this particular demo, but for the path, and I'm talking the entire path here, right? You might as well go ahead and have all these APIs enabled. Okay, so we're also going to need some data to play with. And so I'm going to import some weather data into BigQuery. And that weather data is in the form of a JSON data file. And we'll use BigQuery, and one of its features is to auto-detect the schema. Once we've done that, then we can head on over to Google Data Studio and create a basic dashboard. Note this though, the last comment here, that the account you log in with at Data Studio must have access to the BigQuery data for this demo. So I'm going to log in with the same account into Data Studio as I am in BigQuery. So let's go over to the browser. I've logged into Google Cloud Platform. I'm going to click on the menu, and I'm going to click on BigQuery, which I've got pinned to the top here. And you can also just scroll down to the very bottom, and you'll find it here under Big Data. Okay, so here in BigQuery, what we're going to do first, we're going to click the down arrow here. We're going to create a new data set. That data set is going to be called Weather Data. For location, we'll choose US. We'll click OK. Now, hover over Weather Data, the new data set, and click the plus icon to create a new table. So we're going to create this new table. We're going to leave Create from Source selected. We're going to choose a file upload. So let's choose the file. So if I click on Choose File, it takes me to the directory for this video. I'll click on myweatherdata.json, click Open. The file format is not CSV, it's JSON. So we'll select that. Now we'll give it a name, and the name that we'll give it is Weather Data TBL. So Weather Data TBL. And now we'll select the Automatically Detect checkbox. All right, now let's click Create Table. Okay, so click on Weather Data Table in the left pane, and you can see the schema here, and click on Details. You'll see that we have 2,935 rows. So everything looks good. Now this schema detection is pretty accurate. So I've checked this out, and it looks pretty good. So what's going to happen when we go into Data Studio? Data Studio is going to consider these schema as well, and we'll see an example of that. So let's head on over to Data Studio now that we've got our weather data table created. So click the tab for Google Data Studio, and if you haven't logged in, again, log in with the same ID or the same account, or at least an account with access to that weather data table. So I'll start with a new report. So here under Start a New Report, I'll click on the blank tile, and we'll click Create New Data Source. In the left pane, we'll select BigQuery. We'll select our project, the data set, and the weather data table. Now, after clicking on Weather Data Table, we'll click Connect. And here are our data. Now, we'll change one type here. The rest are all okay. So these are all numbers. Those are good. And the sensor ID is text. But the date, what we want to do is we want to look at hourly data. So instead of date, we're going to click the down arrow here. We're going to hover over date and time. And what we're going to do is we're going to select date hour. Okay, and that's good. Now for aggregations, we're going to aggregate an average value for some of these. Now for zip code, we're not going to aggregate. It doesn't make sense. So we'll select none. For dew point, we'll aggregate the average. For latitude, well, it doesn't make sense to aggregate latitude nor longitude. So we'll quickly click none for that. So these three, temperature, humidity, and pressure, we can average those. Okay, good. Now let's click on Add to Report. And in the confirmation dialog, click Add to Report again. And here now pops up the editor. So what we can do is we can go up here to the toolbar and we can select time series, bar chart, combo chart, pie chart. There's all kinds of different charts and tables that you can use. But what we'll do is we'll keep it simple. We'll just click on time series. Now that activates the time series chart, and what we'll do is we'll just use the crosshair here, hold the mouse button down, and draw a rectangle. And Data Studio automatically picks dew point, so one of the first numbers that's aggregated. Okay, and you can see here it's alphabetical, right? So let's click on dew point, and what we'll do is we'll change that to temperature. Okay, and now we'll click the back arrow, and what we'll do is we'll change the style a little bit. So click on style, and under missing data, we'll change this to line breaks from line to 0. And under left y-axis, axis min right now is 0. So we'll just put our mouse cursor in that field, backspace to cause it to go to auto. And you can see that changed the shape of our graph. Okay, so that's good. Now what we'll do is we'll go over here again, we'll click on this chart and we'll select Control C, and then we'll type Control V to paste that. So we've copied and pasted it here. Now what we can do is we can click on temperature, and now let's click on humidity to change that to humidity. Okay, and you can see because I copied and pasted that, it's going to have the same settings. So for example, if I click on style here, I'll see the missing data is line breaks, and I'll see that axis min is also auto. Now to go from editor to view, just click on view. And this is a fully active dashboard. So actually what we can do is, so we can hover over the graph to see any particular points, right, in our data. Okay, so we've successfully created a simple dashboard in Google Data Studio.
In this video, we'll explore the use of pipelines, p-collections, and transforms. In Dataflow SDKs, a pipeline is a representation of a data processing job. A pipeline comprises a set of operations that read input data, transform that data, and then write the output. Pipelines cannot, however, share any of that data or transforms within the pipeline. Pipelines can dramatically vary depending on the degree of complexity. A set of transforms can be pretty straightforward, executing a set of transforms sequentially, or they can be more complex using branching and merging. Essentially, a pipeline can be seen as a directed graph of steps using loops, conditional branching, or many other common programming constructs. A p-collection represents an immutable and possibly large collection of elements. By immutable, we're referring to the fact that once a p-collection is created, individual elements cannot be added, removed, or modified. A p-collection can be thought of as pipeline data with data flows transforms using p-collections as both inputs and outputs. A p-collection is considered bounded if it represents a fixed data set with a known unchanging size. For example, all orders processed last month. A p-collection is considered unbounded if it represents continuously updating or streaming data. For example, all new orders while they are being processed. Each element that exists in a p-collection has an associated timestamp. And element timestamps in a p-collection are used to establish the notion of windowing. And windowing divides elements in a p-collection corresponding to their timestamps. P-collections may be created with the element type as a custom data type. One example would be if you had to create a collection of a specific class or structure, like a Java class comprising a customer's name and contact information. A Dataflow pipeline transform is a data processing step or operation. That processing step or operation transforms that data. There are several types of transform actions, and they could be, for example, data conversion operations, mathematical computations, aggregations, read-write operations. It could be joining data or a filtering operation. And composite transforms are transforms that contain or invoke other transforms. Dataflow SDK has a group of core transforms supplying the basis for Dataflow's parallel processing model. When using a core transform, you supply the processing logic as a function object. Some factors to consider when creating a function object include they must be thread compatible, since each instance of the function object is accessed by a single thread on a worker instance. That is, unless you create your own threads explicitly. It is also recommended that the function object be made idempotent. In other words, for any given input, the function always provides the same output, and they should be serializable. Types of core transforms include flatten, and this is used for merging collections, and Pardue is used for generic parallel processing. Combine is used for combining collections or grouped values, and group by key is used for key grouping key value pairs. Other transform types include, we touched on this briefly, composite transforms, which are made up of multiple subtransforms. And we also have root transforms, which are specialized transforms for moving data into and out of a pipeline. And these include read, write, and create transforms. Pre-written transforms are provided by Dataflow SDKs in which the programming logic is pre-written. And these are typically more complex transforms, like, for example, performing statistical analysis on the data. Some transforms can accept multiple p-collection inputs or even specialized side inputs. And similarly, a transform can generate multiple p-collection outputs as well as side outputs. In this exercise, you'll practice what you learned about streaming and analytic operations. You will describe batch operations, describe stream operations, describe late data use in stream operations, describe pipelines, p-collections, and transforms, and list key features of Data Studio. Now pause the video and perform the exercise, and when you return, we'll go over these exercise tasks. Okay, task 1, batch operations. Batch operations provide an efficient method for processing large volumes of data, and typically transactions are collected over some period of time. With batch operations, we require different programs for data input, processing, and output. And when you think about batch operations, you can think big data analytical processing. For stream operations, task 2, we consider those to be continuous input, processing, and output of data. They're near real time, meaning very short time periods. So now you can think of this as event processing and low latency messaging. Task 3 was to describe late data use in stream operations. In most systems, data generation and delivery do not reflect an ideal pattern. In fact, data generation and delivery are subject to many time-based or temporal limitations. With data processing systems, there is generally a time lag between when an event occurs, known as the event time, and the actual time that the data element is processed, or processing time. With pipeline data, there is no guarantee that it will arrive in the quote-unquote correct time order, nor is there a guarantee that the data will arrive in a pipeline at intervals that can be predicted. Cloud Dataflow uses a watermark to track the arrival of data in a pipeline. The system considers a watermark to be that point when all the data in a particular window can be considered to have arrived in the pipeline, and subsequently the window is closed. So, data that arrives at some point with a timestamp after the watermark is seen as late data. Next task, describe pipelines, p-collections, and transforms. So first, pipelines. In Dataflow SDKs, a pipeline is a representation of a data processing job. A pipeline comprises a set of operations that read input data, transform that data, and then write the output. Pipelines cannot share any of that data or the transforms within the pipeline. And pipelines can dramatically vary depending on the degree of complexity. A set of transforms can be pretty straightforward, executing a set of transforms sequentially, or they can be more complex using branching and merging. Essentially, a pipeline can be seen as a directed graph of steps using loops, conditional branching, or one of many other common programming constructs. A P collection represents an immutable and possibly large collection of elements. By immutable, we mean that once a P collection is created, individual elements cannot be added, removed, or modified. A P collection can be thought of as pipeline data with Dataflow's transforms using P collections as inputs and outputs. A P collection is considered bounded if it represents a fixed data set with a known, unchanging size. And a P collection is considered unbounded if it represents continuously updating or streaming data. Each element that exists in a P collection has an associated timestamp, and the element timestamps in a P collection are used to establish the notion of windowing. Windowing simply divides elements in a P collection corresponding to their timestamps. P collections may be created with the element type as a custom data type. So one example would be if you had to create a collection of a specific class or structure like a Java class, comprising a customer's name and contact information. And now transforms. A Dataflow pipeline transform is a data processing step or operation that transforms data. The type of transform actions could be data conversions, mathematical computations, aggregations, read-write operations, joining data, or filtering operations. Composite transforms are transforms that contain or invoke other transforms. And now, list key features of Data Studio. First, every component in a Data Studio report gets its data from a cache wherever possible. This speeds up processing and retrieval of data. Data Studio is a tool that can visualize data using configurable charts and tables. And you can share and collaborate. So Data Studio reports and data sources are both stored as files on Google Drive. So it's easy to share them with individuals, teams, or even the entire world. You can also embed reports in other pages like Google Sites, marketing articles, or blog posts. With Data Studio, you manage data sources. So for example, you can add or remove data sources, and you can alter attributes of the data like aggregation settings and even data types. In this video, we'll explore Cloud Spanner replication and instances. First, let's consider Cloud Spanner replication. In Cloud Spanner, replication at the byte level is supported by the distributed file system that it runs on. But Cloud Spanner also replicates data to offer the benefits of data availability and geographic locality. Data in Cloud Spanner is effectively organized into rows, and Cloud Spanner creates replicas of these rows and stores the replicas in various geographic areas. A Paxos-based replication method is used where voting replicas vote on every write request prior to committing the write operation. The result is that globally synchronous replication offers the most up-to-date data from any Cloud Spanner read-write or read-only replica. Paxos, incidentally, is a set of protocols for solving consensus in a network of unreliable resources. Consensus is the procedure whereby a group of participants agree on one result. This is particularly useful when the parties experience failure or communication issues, as can happen with geographically dispersed applications, and hence Cloud Spanner is an excellent solution.
Replicas of each database split are created, a split being a set of contiguous rows in a top-level table, in which rows are ordered by a primary key. All data within a split is physically stored together in the replica, and each replica in turn is served out of an independent failure zone. A set of splits is stored and replicated using Paxos. Within each Paxos replica set, one replica is elected as the leader. Leader replicas are responsible for handling writes, while any read-write or read-only replica can serve a read request without communicating with the leader, though if a strongly consistent read is requested, the leader might, in some cases, need to be consulted to determine a timestamp to read at. Cloud Spanner has three types of replicas: read-write replicas, read-only, as well as witness replicas. Single region instances use only read-write replicas, while multi-region instance configurations use a combination of all three. So some key benefits that are related to the replica service is data availability. Multiple copies of data enhances availability to clients, and Cloud Spanner is capable of serving writes even when some replicas are unavailable, since only a majority of voting replicas are needed to commit a write. Geographic locality. With the ability to place data across different regions and continents, it means that data can be geographically closer to users and services, and therefore faster to access. Single database experience means that synchronous replication and global strong consistency at any scale means that Cloud Spanner exhibits identical behavior, resulting in a single database experience. And easier application development. ACID transaction support and global strong consistency results in freedom for developers to focus on application logic. They don't have to worry about adding extra logic into applications in order to handle eventual consistency. So again, application development and subsequent maintenance become faster and easier. Now let's look at instances. To use Cloud Spanner, the first step is to create a Cloud Spanner instance within a Google Cloud Platform project. This instance is effectively an allocation of resources to be used by Cloud Spanner databases created within that instance. Instance creation includes two important choices: the instance configuration and the node count. These choices determine the location and number of instances serving, as well as storing resources. Note that the configuration choice is permanent for an instance. However, you can change the node count later if necessary. So an instance configuration effectively defines the geographic placement and replication of the databases. When an instance is created, it must be configured as either regional, that means all resources are contained within a single Google Cloud Platform region, or multi-region, with the resources spanning multiple regions. In addition to choosing where your data is stored when you create an instance, you also choose the number of nodes to allocate to that instance. Node count determines the number of serving and storage resources available to the databases in an instance. Each node provides up to 2 tebibytes of storage. A tebibyte is closely related to a terabyte, actually slightly more than 1 terabyte, and is expressed as a power of 2. So for this example, 2 tebibytes would be 2 times 2 to the 40th bytes. The peak read and write throughput values that nodes can provide depend on the instance configuration, as well as on schema design and dataset characteristics. If the serving and storage resources in an instance need to be scaled up, more nodes are added to that instance. Note that the number of replicas is fixed for a given configuration. So adding a node doesn't increase the number of replicas. It does, however, increase the resources available to each replica in the instance. Multi-region instances offer these primary benefits: 99.999% availability, which is greater than the 99.99% availability that Cloud Spanner regional configurations provide. Also, data distribution. Cloud Spanner automatically replicates your data between regions with strong consistency guarantees.
This allows your data to be stored where it's used, which can reduce latency and improve the user experience. In this video, we'll explore Cloud Spanner schema, data types, and best practices. Cloud Spanner supports simple data types like integers, as well as more complex types like array and struct, for example. A Cloud Spanner database can contain one or more tables, and tables look a lot like relational database tables in that they are structured with rows, columns, and values. They also have primary keys. You can define multiple tables in a database, and you can also define parent-child relationships between tables so that Cloud Spanner will physically co-locate their rows for efficient retrieval. Every table must have a primary key, and the primary key can be composed of 0 or more columns of a table. If a table is declared to be a child of another table, the primary key columns of the parent table must be the prefix of the primary key of the child table. This means that if a parent table's primary key is composed of, say, 3 columns, then the primary key of each of its child tables must also be composed of those same 3 columns in the same order and starting with the same column. As a distributed database, Cloud Spanner divides data into chunks called splits when the database grows. Individual splits may move independently from each other and become assigned to different servers, which could be located in different physical locations. A split is a range of rows in a top-level table where those rows are ordered by a primary key. The start and end keys of this range are known as split boundaries. Cloud Spanner automatically adds and removes split boundaries, which changes the number of splits in the database. Cloud Spanner performs load-based splitting to mitigate read hotspots. Now we have split size limits, so it is recommended that the size of every set of related rows in a hierarchy of parent-child tables is less than a few gigabytes, say 10 gigabytes as a general rule of thumb. Cloud Spanner also uses secondary indexes, and these are helpful for quickly looking up data when searching by one or more non-key columns. Now let's consider best practices, and first by looking at schema design best practices. So the best practice is to design Cloud Spanner schemas to avoid hotspots and for optimally loading data into Cloud Spanner. You should be careful when choosing a primary key not to accidentally create hotspots in your database. One way that hotspots are accidentally created is by choosing a column whose value monotonically increases as the first key part. The problem here is that this results in all inserts occurring at the end of the key space. And this is unfavorable since Cloud Spanner divides data amongst servers by key ranges. Consequently, all inserts will be directed at a single server, so you have a hotspot. Schema design best practice then is to not choose a column whose value monotonically increases or decreases as the first key part. Now, when hotspots do occur, you might experience slow inserts and other operations, and one way to fix this is to spread writes over the key space by swapping the order of keys to make the column that contains the monotonically increasing or decreasing value not the first key part. Another technique that Google used to recommend is to hash the unique key and then use the hash or even the hash plus a unique key as the primary key. Although this method does ensure that inserted rows are spread more evenly across the key space, so effectively avoiding hotspots, Google no longer recommends this practice since it results in row keys that are essentially meaningless, and this can lead to nightmare scenarios when trying to debug issues with Cloud Bigtable. Instead, they recommend using human readable values, and if the row key consists of multiple values, separate those values with a delimiter. Still with schema design best practice, it is best practice to use descending order for timestamp-based keys. If you have a table with a timestamp key, you can make the timestamp key descending by appending the DESC or desk keyword to the primary key definition. This makes reading all the history up to some period of time ago, for example, much more efficient, since Cloud Spanner won't need to read all the data to discover where some period of time ago begins. Rather, it can just start reading at the top where the most recent record will be located. Another schema design best practice: do not create non-interleaved indexes on a column whose value monotonically increases or decreases, even if they aren't primary key columns. Under the hood, indexes are implemented as tables. So in this scenario, the resulting index table would use a column whose value monotonically increases for the first key part. However, it is fine to create an interleaved index. And create indexes after you bulk load your data. So if you need to bulk load data, don't create indexes until the data is fully loaded. Creating an index on pre-existing data is a lot faster than incrementally updating index each time a row is loaded. And now, best practice associated with data loading. And what we're talking about here is bulk inserting or writing rows in a table. So, similar to the last best practice that we talked about with schema design, create indexes after bulk loading. Another best practice: ensure that writes are well distributed. So you should avoid writing rows in primary key order. For example, if you are loading data into a table with a primary key user ID, you should make sure that the data load doesn't write all rows in user ID order. Optimally, each data load worker will write to different parts of the key space. That way, writes are distributed to multiple Cloud Spanner servers, not overloading one of them. And load data using multiple workers. So this is somewhat related. So partition the ordered key space into ranges. Then you can have each range processed by a worker that batches the data into that range into somewhere around 1 megabyte or 10 megabyte chunks. It's best practice to have a significantly large number of partitions, and Google recommends 10 times the number of nodes. That way, individual workers won't cause moving hotspots. In this video, we'll look at Cloud Bigtable. Cloud Bigtable is a sparsely populated table on Google Cloud Platform, scalable to billions of rows and thousands of columns. This means that you can store terabytes or even up to petabytes of data in Bigtable. A row key is a single value in each row that's indexed. So Cloud Bigtable is ideally suited for storing very large amounts of single key data with very low latency. Cloud Bigtable supports multiple client libraries, including a supported extension to the Apache HBase 1.x Java library. Consequently, it integrates with the current Apache ecosystem of open source big data software. Now let's consider some benefits and key uses for Cloud Bigtable. Bigtable's powerful backend servers offer a number of key benefits compared to self-managed HBase installations. So, for example, it handles upgrades and restarts transparently, and it also automatically maintains high data durability. That is, the data is stored on Colossus, which is Google's internal, highly durable file system, on storage devices in Google's data centers. So there's no need to run an HDFS cluster or any other file system to use Bigtable. Bigtable scales in a manner that is directly proportional to the number of machines in a cluster. A self-managed HBase installation is hampered by a design bottleneck that limits the performance after a certain volume of queries per second is reached. Cloud Bigtable avoids this bottleneck, and a cluster can scale up to handle more queries by increasing machine count. The size of a Cloud Bigtable cluster can also be scaled up for a few hours, for example, to handle a spike in load, then reduced again without any downtime at all. Data is never stored in Cloud Bigtable nodes. Rather, each node has pointers to a set of tablets stored on Colossus. So the result is rapid rebalancing of tablets from one node to another. Since the actual data itself is not copied, Bigtable just updates the pointers for each node. Recovery from failure of a node is also very fast, since only metadata needs to be migrated to the replacement node. And when a Bigtable node fails, consequently, no data is lost, and that's data preservation. Some examples of key use cases for Bigtable include things like time series data. So for example, CPU and memory consumption over time across multiple servers, or financial data like stock prices, Forex currency rates, transaction history, and so on. Then marketing data is also a good use case. So for example, order history or data concerning customer preferences. And Internet of Things. So for example, usage reports from various sensors in the field. Now let's have a look at the architecture from a high level. Client requests are handled by a front-end server prior to being sent to Cloud Bigtable nodes. In Cloud Bigtable, a table is sharded into blocks of contiguous rows known as tablets. This serves to assist in balancing the workload of queries. So in this manner, tablets are similar to HBase regions. Tablets get stored on Colossus, which is Google's file system, and they're stored in SS table format. Now, an SS table provides a persistent, ordered, and immutable key value mapping where both keys and values consist of arbitrary byte strings. Each tablet is also associated with a specific Cloud Bigtable node. Now further to that, all writes are stored in Colossus shared log as soon as they are acknowledged by Bigtable, thereby increasing durability. Other Bigtable features include the fact that in most cases, Bigtable considers all data as raw byte strings, with the exception of increment operations where the target must be a 64-bit integer encoded as an 8-byte big-endian value. For security and access control, you assign IAM roles to users. So if someone has not been provided with access to your project, or if they don't have an appropriate Cloud Bigtable IAM role, well, they won't be able to access any of your tables. Since data is stored on Colossus, Google's internal highly durable file system, it inherits the native high data durability from Colossus. Now let's consider how some Cloud Bigtable components affect memory and disk usage for an instance. Compaction. This is a process whereby Bigtable periodically rewrites tables to remove deleted entries and reorganize data, which results in more efficient reads and writes. Bigtable does this automatically. Row mutations or changes require extra storage space since Cloud Bigtable stores mutations sequentially and only compacts them periodically. When compaction is performed, values no longer needed are removed. Deletions also require extra storage space. Deletions are really just a special type of mutation, so until compaction occurs, extra storage space is required. Column qualifiers require space in a row. This is because each column qualifier used in a particular row is also stored in that row. Consequently, it is usually efficient to use column qualifiers as data. Empty cells in a Cloud Bigtable table do not consume any space. Each row is basically a collection of key value entries. The key is a combination of the column family, column qualifier, and timestamp. So if a row doesn't have a value for a particular key, the key value entry remains absent. In this video, we'll go over the steps involved in designing a Cloud Bigtable schema. To optimize Cloud Bigtable performance, you have to carefully consider the composition of the row key. Efficient Cloud Bigtable queries use the row key, a row prefix, or a row range to retrieve data. And the thing is, other kinds of queries cause a full table scan, which is, as you can imagine, not very efficient. Typically, you want to keep row keys somewhat short, at least as short as you practically can. Long row keys consume additional memory and storage, and long row keys also increase the time required to get a response from the Cloud Bigtable server. Types of row keys include string identifiers, which are typically used if you are storing data about entities that may be identified with a simple string like customer ID, for example. In this scenario, you can use the customer ID string identifier as the row key or as part of the row key. Reverse domain names are indicated when you're storing information about entities that may be expressed as domain names. In this case, you should consider using a reverse domain name, especially when each row's data is inclined to overlap with adjacent rows. Timestamps are very useful when you commonly need to retrieve data based on the time it was recorded, although it is not recommended to use the timestamp alone as the row key. This could lead to a hotspot. In this case, perhaps consider using a combination of a string identifier with the timestamp as the row key. The sole method for querying Cloud Bigtable efficiently is by row key, and for that reason, it's typically a good idea to include multiple identifiers in the row key. Things to avoid. Consider a scenario where a system assigns a sequential numeric ID to each user. It might seem at first to be a good idea to make the user's numeric ID the row key for the table. The potential problem here is that new users tend to be more active users, so using the row key this way probably is going to push much of the traffic to a smaller number of nodes. A more efficient approach is to use a reversed form of the user's numeric ID, as this will spread traffic more evenly across all nodes. You should also avoid using standard domain names, not reversed that is, as row keys. This causes inefficient retrieval of all rows within a portion of a domain. For example, all rows related to domain.com will be stored in separate row ranges like services.domain.com and products.domain.com, and can also result in less efficient compression. You should avoid using a single row key to identify a value that is frequently updated, and although Google used to recommend using hashed keys, they no longer recommend this practice since it results in row keys that are essentially meaningless and in practice have been seen to lead to nightmare scenarios when trying to debug issues in Cloud Bigtable. As a best practice, the schema design should allow you to stay below the recommended size restrictions. And these size limits are measured in binary kilobytes and binary megabytes. These units of measure are known as kibibytes and mebibytes. So maximum limits include 1,000 tables per cluster, 256 mebibytes of single row values, and that is all values within a single row, and per cell should not exceed 100 mebibytes. And these are maximum limits, so they cannot exceed these limits. Other limits include 4 kibibytes per row key, 16 kibibytes per column qualifier, and 100 column families per table. Now let's look at column design. You can comfortably use up to around 100 column families and continue to see excellent performance. Accordingly, when a row contains multiple values related to each other, it's good practice to group those values into the same column family. Grouping data like this into column families means that you can retrieve data from a single family or from multiple families, as opposed to retrieving all the data in each row. You should also group data as closely as you can in order to retrieve just the information that you need and no more in the most used API calls. And keep the names of your column families short, since after all, they are included in the data transferred in each request. With respect to column qualifiers, since Cloud Bigtable tables are sparse, you're free to create as many column qualifiers as required in each row. There is no space penalty for empty cells in a row. Consequently, it is usually a good idea to treat column qualifiers as data. And it's also a good idea to keep column qualifier names short, again to minimize the amount of data transferred for each request. Other schema design considerations include the fact that rows are sorted in lexical order by row key from lowest to highest byte string. Row keys are sorted in big endian or network byte order the binary equivalent of alphabetical order. There is only one index per table, and that's the row key, so there are no secondary indices. Atomic operations occur at the row level. So for example, say you are trying to update 2 rows in a table. Well, it's entirely possible that one row updates successfully while the other update fails. So you need to avoid schema designs that require atomicity across rows. Both reads and writes should be distributed evenly across the table row space. And since Cloud Bigtable tables are sparse, empty columns don't consume any space. So it's advisable to create as many columns as you want. And this can be a very large number, thousands of columns, even if most columns are empty for most rows. The schema should be designed such that related entities are stored in adjacent rows. This makes for efficient reads. And all information for an entity should be in a single row. However, entities that don't require atomic updates and reads can be split across multiple rows. In fact, splitting across multiple rows is recommended when the entity data is large, like hundreds of MB. In this demo, we'll work with Bigtable instances. Okay, so I'm going to go over to the README for this demo. And you can see we've got a couple of prerequisites here. We need to enable these APIs, so make sure that you've got those APIs enabled. And then what we're going to do is we're going to go to Cloud Bigtable and create an instance. And we'll call that my instance. So let's go over to Bigtable. So click on the menu, and under storage, the first option is Bigtable. So let's click on that. And I've got no instances, so I'm going to click Create Instance. The instance name, I'm going to call it My Instance. The instance ID will leave as the default. The instance type, we're going to select Development. This is low cost for development and testing. We'll leave the cluster ID at the default. Now selecting a zone, click the down arrow, and I'm going to select US West 1C. And now for storage type, we'll leave SSD selected, and we're ready to go. So click Create. And it doesn't take very long at all. In fact, my instance is up already. Okay, so let's dismiss this notification. And now I've got Google Cloud Shell open. And in order to open it, you just click on this icon, Activate Google Cloud Shell. And then when it comes up, you just click on the icon to open it in its own tab. Okay, so here we are in Cloud Shell. Now what I'm going to do, I'm going to go back over to the README here. By default, Cloud Bigtable command line tool is installed in Google Cloud Shell. If you want to see what components are listed there, then just type gcloud components list. So I'll just go back here quickly and go ahead and do that. Gcloud components list. And you can see here installed Cloud Bigtable command line tool. Okay, so I'll type clear and press enter to clear that up. And now what we're going to do is we're going to set up a couple of defaults. You can see those here. So we're going to set up a project default, and we're going to place it in a .cbtrc file. And that will be accessed by the command line tool when we use the Cloud Bigtable command line tool, that is. So let's go ahead, we'll highlight these two commands, right click, select copy. Let's go back over to Cloud Shell, click inside here and press Ctrl V to paste them both. Okay, and then just to see what they are, let's do a cat.cbtrc, and there they are. Those are the values in .cbtrc. So let's type clear and press enter again. And now we're ready to start creating some resources in Bigtable. So first let's create a table called My Table. Makes sense? Okay, so to do that, type cbt create table My Table. Okay, so that's done. Now, if you need some help with any of these commands, just type cbt help, and that lists all the commands that are available to you.
So again, we'll type clear and press enter. Now if you want to list those tables, type cbtls. And we don't have to set the credentials flag because basically we're just using the credentials that we're logged in with on Google Cloud Platform, right? Okay, so you can see that it lists my table. So we successfully created that. So let's type clear and press enter. Now let's create one column family. We'll call that colfam1. So cbt create family my table colfam1. And we can list the column families by typing cbt ls my table. And there you can see the column families. There's just one, colfam1, and it's using the default policy. So let's clear that by typing clear and pressing enter. And now we can place a test string value in row R1, for example, using the column family colfam1 and a column qualifier that we'll call C1. So to do that, we type cbt set my table, and now we specify the row R1, and now the column family colfam1 colon, and we're going to call the column qualifier C1. So C1 equals test dash string dash value. Okay, press enter. And now if we type cbt read my table, we'll see that row, and that's the data that we just added. Okay, so there's the column family, there's the qualifier, the row is R1, and there's the value. And there's the timestamp that it was added. Okay, so now when you're done with this demo, type cbt delete table my table. You don't want to incur any charges. So let's clear that by typing clear, clear, and press enter. And now we'll go over to the Bigtable instances, click on my instance, and now click delete instance. Now we have to type the instance ID, my instance, and click delete. Okay, done, all cleaned and everything. In this video, we'll explore the Google Cloud Platform Security Model. The Cloud Platform Security Model is an end-to-end process. Google uses practices and controls to secure data access, and for example, when retired from service, disks that contain customer information undergo a data destruction process. All services on Google Cloud Platform are managed via a secure global API gateway infrastructure. This infrastructure is accessible only over encrypted SSL and TLS channels, and each request includes a time-restricted authentication token generated through human login or private key-based secrets. Authentication to a cloud platform API can be accomplished using service accounts or by authenticating user accounts. For APIs that don't require authentication, you can use API keys. Cloud Audit Logging maintains two types of audit logs for each project and organization: admin activity and data access. Google Cloud Platform Services write audit log entries to these logs, and they provide answers to who did what, when did they do it, and where. With only a few exceptions, customer data stored at rest is always encrypted on Google Cloud Platform. The encryption is automatic, transparent, and no customer intervention or action is required. Google uses sophisticated data processing pipelines with integrated host-based signals on individual devices, network-based signals from assorted monitoring points across the infrastructure, and signals from infrastructure services. Rules and machine intelligence built on top of these pipelines provide Google's operational security engineers warnings of possible incidents with respect to intrusion detection. Cloud Security Scanner assists App Engine developers to identify common vulnerabilities. Google's secure global network helps to improve the security of in-transit data, and the combination of cloud interconnect and managed VPN means that you can create encrypted channels from an on-prem private IP environment to Google's network. Google maintains high security compliance and standards, providing some of the most secure infrastructure on the planet. And Google regularly has audits of their security, privacy, and compliance controls performed by independent third parties. If you use virtual machines in your projects, for example, Compute Engine or Kubernetes Engine, then you are responsible for keeping the virtual machine operating system and applications up to date with the latest security patches. However, Google maintains security and patching of the host OS environments. Cloud Platform allows the configuration of user permissions at the project level for full control of who has access to what resources and at what level. Google allows the evaluation of the security of your cloud platform infrastructure using penetration testing, and you don't have to contact Google to begin testing. However, you will have to abide by the Google Cloud Platform's acceptable use policy as well as the terms of service, and ensure, of course, that any tests you want to run will only affect your projects and not any other customer's applications. If a vulnerability is found, Google offers their vulnerability reward program for reporting any vulnerabilities discovered. By default, all incoming traffic from external networks is blocked and no packet is permitted into a virtual machine instance without explicit firewall rules. To permit incoming network traffic, firewalls need to be configured, and this allows you to specify the origin and type of traffic permitted to reach any of your compute instances. Data possesses varying levels of sensitivity. Cloud Platform provides fundamental capabilities required to build secure applications. You have the ability, and indeed the responsibility, to enforce appropriate movement and access to sensitive data at application level. Using tools like Google Cloud Logging and Google Cloud Monitoring simplifies the collection and analysis of request logs, as well as the monitoring of infrastructure services availability. In this video, we'll explore identity and access management on Google Cloud Platform. Cloud Identity and Access Management, or Cloud IAM, allows you to manage access control by defining who has what access for which specific resources. With Cloud IAM, admins can grant granular access to specific Google Cloud Platform resources and meanwhile prevent unwanted access to other resources. Cloud IAM allows you to adopt the security principle known as least privilege. Essentially what that means is granting only the necessary access to resources and no more. With Cloud IAM, access is granted to specific members. So let's take a look at these member types. First, a Google group represents a named collection of Google accounts and service accounts. Every group is associated with a unique email address. Google Groups offer an efficient and convenient method for applying an access policy to a collection of users. So you can grant and alter access controls for an entire group rather than granting or altering access controls for individual users or service accounts one at a time. You can also easily add and remove members associated with a Google group rather than updating a Cloud IAM policy to add or remove users. One thing to be clear on, Google Groups don't have login credentials, and thus you cannot use Google Groups to establish identity. A G Suite domain is a virtual grouping of all the Google accounts that exist in an organization's G Suite account. G Suite domains represent your organization's internet domain name. When you add a user to a G Suite domain, a new Google account is created for the user inside this virtual group. Similar to Google Groups, G Suite domains cannot be used to establish identity. Rather, they offer a convenient, efficient method for permission management. A Google account represents an administrator, a developer, or any other individual or person who interacts with Google Cloud Platform. The email address associated with a Google account can be an identity, and this includes gmail.com or some other domain. A service account is one that belongs to a particular application rather than to an individual end user. When running code hosted on Google Cloud Platform, you specify the account that the code should run as. You may create as many service accounts as required to represent the different logical components of an application. A cloud identity domain is similar to a G Suite domain since it represents a virtual group of all Google accounts within an organization. The difference is that cloud identity domain users do not have access to G Suite applications and features. And special identifiers include groups like all authenticated users. This particular special identifier represents any user that is authenticated with a Google account or a service account. Another one is all users, which includes all authenticated and unauthenticated users. You grant access permissions to users for Google Cloud Platform resources. Examples of resources include projects, cloud storage buckets, or compute engine instances. In most cases, you grant Cloud IAM permissions at the project level, and the permissions cascade or apply to all resources within the project. However, some services like Cloud Pub Sub, for example, support the granting of Cloud IAM permissions at a granularity finer than the project level. And permissions define the operations that are allowed on a resource. In most cases, each Google Cloud Platform service has an associated set of permissions for each REST method that it exposes. A role is a collection of permissions. You don't assign permissions to a user directly, rather you grant them a role. By doing so, you grant a user all the permissions that the role contains. There are three types of roles in Cloud IAM. Primitive roles are roles historically available in the Google Cloud Platform console, including owner, editor, and viewer roles. Predefined roles are Cloud IAM roles that provide finer-grained access control than primitive roles. For example, consider the predefined role of pub/sub publisher. It grants access to only publish messages to a Cloud pub/sub topic. And custom roles can be created to customize permissions to the requirements of an organization when predefined roles just don't do the job. The way you grant roles to users is by creating a Cloud IAM policy. This is a collection of statements that define who has access and exactly what type of access they have. A policy is attached to a resource and is referenced to enforce access control whenever a request to access that resource is made. Google Cloud Platform resources are also organized hierarchically. The root node is the organization node, and projects are the children of the organization. Similarly, other resources are children of projects, and each resource has exactly one parent. In this video, we'll explore the security layers on Google Cloud Platform. The hardware security layer is the lowest layer of Google Cloud Platform infrastructure. Google server machines employ various technologies to ensure that those machines are booting the correct software stack. For example, Google uses cryptographic signatures over low-level components like the BIOS, kernel, bootloader, and base OS image. These signatures may be validated in the course of each boot or upgrade. Each physical server in a Google data center has a specific identity that can be associated with the hardware root of trust and the software with which the machine booted. This identity authenticates API calls to and from low-level management services on the machine. Google designs and builds its data centers, and they combine multiple layers of physical security protection. Access to Google data centers is limited to a very small fraction of Google employees, and the multiple physical security layers are used to protect the data center floors using technologies like biometric identification,
cameras, vehicle barriers, metal detection, and laser-based intrusion detection systems. Google data centers are composed of thousands of servers connected to a local network. Both server boards and networking equipment are custom designed by Google. Now let's look at the secure service deployment layer. Google uses cryptographic authentication and authorization at the application layer for inter-service communication. This method provides strong access control at an abstraction level and granularity that both services and administrators can naturally recognize. Each service running on the infrastructure owns an associated service account identity. A service is given cryptographic credentials that can be used to prove its identity when making or receiving remote procedure calls to other services. These identities are also used by clients to ensure that they are communicating with the intended server, and they're used by servers to limit access to methods and data to specific clients. Although they don't solely rely on internal network segmenting or firewalls as the primary security apparatus, Google does use ingress and egress filtering at various points in the network to, for example, prevent IP spoofing. Google uses various isolation and sandboxing techniques to protect a service from other services running on the same machine. For example, they use techniques like Linux user separation, language and kernel-based sandboxes, as well as hardware virtualization. The owner of a service can employ access management features to define exactly which other services may communicate with it. For example, let's say a service wants to offer some APIs only to a specific whitelist of other services. The service may be configured with that whitelist of permitted service account identities. Subsequently, this access restriction is automatically enforced by the infrastructure. Over and above the remote procedure call authentication and authorization capabilities discussed earlier, the infrastructure also provides cryptographic privacy and integrity for remote procedure call data on the network. Finally, when a service receives a specific end-user credential, it passes it to a central identity service for verification. So if the end-user credential verifies, the central identity service returns a short-lived end-user permission ticket that may be used for remote procedure calls related to the request. Now let's consider secure data storage and internet communication layers. Google storage services can be configured to use keys from Central Key Management Service to encrypt data before it's written to physical storage. Deletion of data at Google typically begins by marking specific data as scheduled for deletion instead of immediately removing the data entirely. This allows for recovery from unintentional deletions, which could occur because of a customer-initiated deletion or due to a bug or internal process error. After being marked as scheduled for deletion, the data is eventually deleted in accordance with service-specific policies. When a service makes itself available on the internet, it registers itself with an infrastructure service called the Google front end. The Google front end safeguards that all TLS connections are terminated using proper and accurate certificates and use best practices like supporting perfect forward secrecy. It's also interesting that just the scale of Google's infrastructure allows them to simply absorb a lot of denial of service attacks. However, they do employ multi-layer and multi-tier denial of service protection to further reduce the risk of denial of service impact on a service running behind a Google front end. And the next layer of defense is Google's Central Identity Service. This service is typically expressed to end users as the Google login page. And as you are no doubt aware, a simple username and password is requested. However, the service also intelligently challenges users for supplementary information based on certain risk factors like whether they have logged in from the same device before or from a similar location in the past. After authenticating the user, the identity service issues credentials like OAuth tokens and cookies that may be used for subsequent calls. And operational security layer. For securing development
Google provides libraries to prevent developers from accidentally introducing certain classes of security bugs. One example is libraries and frameworks that eliminate cross-site scripting or XSS vulnerabilities in web apps. Google also provides automated tools for detecting security bugs that include fuzzers, web security scanners, and static analysis tools. Google has invested heavily in protecting their employees' devices and credentials from compromise. Further, they are also heavily invested in monitoring activity to discover potential compromises and illicit or malicious insider activity. For intrusion detection, Google uses sophisticated data processing pipelines with integrated host-based signals on individual devices, network-based signals from assorted monitoring points across the infrastructure, as well as signals from infrastructure services. Rules and machine intelligence built on top of these pipelines provide Google's operational security engineers with warnings of potential incidents. And Google aggressively limits and monitors the activities of employees that are granted administrative access to the infrastructure. They also continually strive and innovate to eliminate the requirement for privileged access for particular tasks. In some cases, this includes requiring two-party approvals for some actions and introducing limited APIs that allow debugging without exposing sensitive information. In this video, we'll consider the data and security compliance associated with Google Cloud Platform. Google annually undergoes audits performed by independent third parties to ensure that they meet certain data and security compliance standards. Let's take a look at some of these standards. And this is by no means an exhaustive list. However, let's first look at ISO standards. So there's 27001, which is concerned with managing information risks. 27017, which is concerned with controlling cloud-based information security, and 018, which is all about protecting personal data. Now, different services on cloud platform comply with these standards. Other key standards include the SSAE 16/ISAE 3402 Type 2 standards, and these concern globally recognized international accounting standards. So you have SOC 1 to 3, and they are as follows. SOC 1 is concerned with controls over financial reporting. SOC 2 is concerned with controls over security, availability, and confidentiality. And SOC 3 is concerned with public report of controls over security, availability, and confidentiality. The FedRAMP, or the U.S. federal government's Federal Risk and Authorization Management Program, is a government-wide program providing a standardized approach to security assessment, authorization, and continuous monitoring for cloud products and services. And PCI DSS is a collection of network security and business best practice guidelines adopted by the PCI Security Standards Council to establish a minimum security standard to protect customers' payment card information. Other key compliance standards include HIPAA, or the Health Insurance Portability and Accountability Act of 1996. Now, this is a federal law that establishes data privacy and security requirements for certain entities and individuals, and the act is designed specifically to protect individuals' health information. CSA STAR self-assessment is concerned with securing cloud computing environments, while NIST 800-171 is concerned with security requirements for U.S. federal-controlled unclassified information. Sarbanes-Oxley Act was designed to improve the accuracy and reliability of corporate disclosures. As part of Sarbanes-Oxley requirements, each U.S. public company is responsible for establishing and monitoring internal controls, including those controls that are maintained by a third party, such as a cloud service provider. And there are also a number of country-specific security compliance standards. And again, this is not an exhaustive list, but here are some of the country-specific security compliance standards. So for Singapore, we have the MTCS Tier 3 certification. Now, this certification has 3 successive tiers to certify cloud providers' operational security. For Japan, we have the My Number Act, which is concerned with protecting personal information and data in Japan, and FISC, which concerns security guidelines for financial institutions in Japan. For the EU, we have the EU Data Protection Directive, and this concerns the protection of EU citizens' privacy and personal data. And for Spain, we have the Esquema Nacional de Seguridad, which is roughly translated as National Security Stream. And this is a tier-based cloud security standard that applies to Spain. And for Australia, we have the Australian Privacy Principles, or APP. And this is all about protecting personal information in Australia. In this exercise, you'll practice what you learned about big data and security. You will describe Cloud Spanner benefits, describe how to choose a row key for Cloud Bigtable, describe the Google Cloud Platform Security Model, describe Cloud Identity and Access Management, and list the Google Cloud Platform security layers. Now pause the video and perform the exercise, and when you return, we'll go over these exercise tasks. Okay, task 1, Cloud Spanner benefits. So first, it's a fully managed service, so there's no need to spend time managing hardware and software. Instead, you can focus on application logic. We also talked about global scale, and that means you can horizontally scale across rows, regions, and continents from 1 to thousands of nodes. It also means that you can scale out your RDBMS solution without complex sharding or clustering, and horizontal scaling can be performed without migration from relational to NoSQL databases. With respect to relational semantics, we talked about how Cloud Spanner supports relational database semantics like schemas, ACID transactions, as well as SQL queries as at ANSI 2011. Other benefits include the fact that it supports multiple languages like C#, Go, Java, and other languages, as well as a JDBC driver for connectivity. We talked about transactional consistency, enterprise-grade security with data layer encryption, IAM integration for access and control, and audit logging. And we also mentioned the fact that high availability is supported with built-in, transparent, and synchronous data replication. Next, describe how to choose a row key. So we spoke about optimizing Cloud Bigtable performance, and in order to do that, you have to carefully consider the composition of the row key. Typically, you want to keep your row keys somewhat short, and the types of row keys include string identifiers, which are typically used if you are storing data about entities that may be identified with a simple string like customer ID, for example. Another type is reverse domain names, and these are indicated when you're storing information about entities that may be expressed as domain names. Timestamps are very useful, of course, when you commonly need to retrieve data based on the time it was recorded, and multiple values. So the sole method of querying Bigtable efficiently is by row key, and for that reason, it's typically a good idea to include multiple identifiers in the row key. You should also avoid using a single row key to identify a value that's frequently updated. And we briefly talked about hashed, and this is something that Google used to recommend to use hashed keys, but they no longer recommend this practice since it results in row keys that effectively are meaningless. Next, tasks. Describe Cloud Platform Security Model. We spoke about the fact that it's an end-to-end process and that Google uses practices and controls to secure data access. And for example, when hard disks are retired from service, those disks undergo a data destruction process. We talked about the fact that all services on Google Cloud Platform are managed via a secured global API gateway infrastructure. We talked about authentication to a Google Cloud Platform API and that it can be accomplished using service accounts or by authenticating user accounts. For APIs that don't require authentication, you can use API keys. And for audit logging, we talked about the fact that audit logging maintains 2 types of audit logs for each project and organization. We have admin activity and data access. And we talked about the fact that with only a very few exceptions, customer data stored at rest is always encrypted on Google Cloud Platform, and that encryption is automatic, transparent, and requires no customer intervention. We talked about the fact that Google uses sophisticated processes and pipelines for intrusion detection, that Cloud Security Scanner assists App Engine developers to identify common vulnerabilities. Google's secure global network also helps to improve the security of in-transit data, and the combination of Cloud Interconnect and managed VPN means that you can create encrypted channels from an on-prem private IP environment to Google's network. And we talked about security compliance. Google maintains high security compliance and standards, providing some of the most secure infrastructure on the planet. And the fact that Google regularly has audits performed on their security, privacy, and compliance controls. And these are performed by independent third parties. Now, describe Cloud Identity and Access Management. Cloud Identity and Access Management, or Cloud IAM, allows you to manage access control by defining who has what access to which specific resources. With Cloud IAM, admins can grant granular access to specific Google Cloud Platform resources and meanwhile prevent unwanted access to other resources. Cloud IAM allows you to adopt the security principle known as least privilege, and essentially what that means is granting only the necessary access to your resources and no more than that. Now list the Google Cloud Platform security layers. So first there's the hardware security layer. Then we have the secure service deployment layer. Then secure data storage and internet communication layers. And then we have the operational security layer.